reaction, and in that case what will happen is simply this 2 will be cut down and the overall cell reaction will be nickel 2 plus 2 silver. So that will be the overall reaction or the cell reaction for these two half reactions. And in the next part of this question we are asked to sketch the experimental setup for this reaction or for this galvanic cell reaction. And to do that, let's first draw our cathode and anode compartment. So let's say that this is our cathode compartment and this is our anode compartment. And in anode we will have a metal strip of nickel, so and which will be our anode actually. So we have a nickel anode here, and in cathode compartment we will have a silver cathode. And then there will be a wire connection between these two electrodes through which the electrons will pass through. So what will happen here is in the nickel electrode, some of the nickel metals will give up some electrons, as we have seen in the reaction here, that some of the nickels will give up 2 electrons to become nickel 2 plus, and that will happen here. So the nickel will give up electron to become nickel 2 plus, and that will be in the solution here, and these electrons being produced will go through this path to reach the cathode. And when the electron will reach the cathode, here we have a solution of silver plus ions. So this silver plus ion will take these electrons to become silver metal, and at the same time, so there will be a shortage of positive silver ions in this solution. And to keep this electrochemical cell active, we have to have a constant supply of the cations in this cathode compartment, and we need a constant supply of anions in this anode compartment. So to do that, we call it a salt bridge. So it will be like this. So in salt base we use a neutral salt solution. In this case we can use maybe a sodium nitrate. So the anions will go in the anode compartment from the salt bridge, and the cation will go to the cathode compartment. So what happens, as we said, that when the silver ions will take up electrons and will become silver metal, there will be shortage of positive ions in this cathode compartment, and at that time these sodium ions will come here in the solution to cover up for that shortage. And what will happen in anode is the nickel is giving up electrons to become nickel 2 plus, so there will be a surge of positive ions in the anode compartment, and to balance positive ions in some of the nitrate ions from the salt bridge will come in this anode compartment, and that will react with this nickel 2 plus ion to form nickel nitrate, and in this way there will be a balance of ions in both the compartments. So in this problem we are given with the galvanic cell reaction, and we are given for this galvanic cell ion concentrations of the galvanic cell, standard cell potential, and we are asked to find out the cell potential at 25 degrees C for this galvanic cell. So let's first write down the galvanic cell reaction equation. copper to copper 2 plus. The reaction equation involves copper in solid state reacting with and plus iron 3 plus standard cell potential 4 and it will give us plus copper 2 plus to Fe2 plus in aqueous state, and if we sum these two values we will iron, so the value for this one is minus 0.34 so now volt, and the value for this find one out is the cell potential at 25 degrees C. We have to apply the Nernst equation, which is, and this will give us a value of plus 0. E is equal to 43 volt. So this is the standard cell potential for this galvanic cell. Now we will just plug in this value in this reaction equation 0.5 or in this formula 92 volt, and if we do that, the number of electrons transferred, our cell potential value, the log Q at the 25 degrees C. So here this E naught is the standard cell potential which we can calculate from the standard oxidation reduction potential values of this galvanic cell, and then the Q is basically the ratio of the ion concentration point on the product side over the reactant side to volt over the number of electrons transferred in between the reactants and products. And we can see that from here we can easily see that copper was converted to copper 2 plus. That means copper has donated 2 electrons, and these 2 electrons are taken up by this Fe3 plus. 2 of this Fe3 plus took those 2 electrons to become 2 Fe2 plus ions. So that means the number of electrons that were transferred in the process is 2, and that's why our value for N is also 2. So we'll place 2 as the value for N, and now we have to write down the log of the product concentrations over the reactant concentrations, and here our products are copper 2 plus and Fe2 plus, and since we have 2 Fe2 plus, we'll have a square there for these 2, and at the bottom we will have Fe3 plus, and since we have 2 Fe3 plus, we will put a square for this one too. And since copper is in solid form, it will not be included in this ratio here, so that's all we need to plug in the formula. And if we calculate these values, we'll get 0.43 volt minus, if we calculate this part, it will be 0.178 volt. And the answer will be 0.252 volt. So this is the cell potential at 25 degrees C for the galvanic cell given.
In this reaction, the cell given at anode, copper is oxidized to copper ion and give electrons, while at cathode the reduction of MnO4 take place in the presence of hydrogen ions and gain electrons forming Mn+2 ion and 4 water molecules formed. To make the number of electron loss and gain equal, so we will multiply the anodic half reaction with 5, so we can write that 5 copper ion copper atoms, oxidizes, forming 5 copper plus 2 ions and release 10 electrons. While we will multiply the cathodic half by 2 to make the number of electron equal, so we can write that 2 MnO4 minus ion and 16 hydrogen ion can 10 electrons forming 2 Mn plus 2 ion and 8 water molecule. So the nearest equation for every still is written as E is equal to E naught minus 2.303 RT over NF and log of Q. As we know that 2.303 RT over F is equal to 0.0592 volt. Putting this value in the above equation, we can write that E is equal to E naught minus 0.0592 volt over N, where log of Q is equal to the concentration of the copper ions raised to the power 5 divided by the concentration of Mn2 plus ions raised to the power 2. Now in the first case, if the concentration of copper ion is reduced by a factor of 100, so we can write the equation that E is equal to E naught minus 0.0592 volt, where N is the number of electron lost and gained. So in the above equation we see the number of electron is 10 and log of the concentration of copper ion is reduced by a factor of 100, so it is minus 100 as the concentration has been reduced. We can also write for the copper ion that the concentration has been reduced by a factor of 100. Simply we can also write that it has been reduced by a 10 raised power minus 2 for the copper ion raised to the power 5, where there is no change in the concentration of manganese, so we take it 1 square. It is 1 molar. So calculating this equation, we can write E is equal to E naught minus 0.0592 volt divided by 10, where log of 10 raised power minus 2 multiplied by 5, so it is equal to 10 raised power minus 10. We can also write this equation in the form that E is equal to E naught minus 0.0592 volt divided by 10, where it is the principle of log that the power is equal to base, so minus 10, and log of 10, where log of 10 is equal to 1, so we omit log of 10. So we can write the equation that E is equal to E naught. We multiply both the minus signs because they are in multiplication, so we can write plus, and we cut the 10, cancel with each other, so 0.05 0.0592 volt. So when we reduce the concentration of copper ion by a factor of 100, the voltage of the cell will be increased by a 0.0592 volt. On the other hand, if we write the equation for the manganese and we reduce the concentration of the manganese ion, so the equation will be like this, that E is equal to E naught minus 0.0592 divided by 10 and minus log of, now there is no change in the concentration of copper ion, so we write it 1 power 5, and the concentration of manganese ion has been reduced by a factor of 10, so 100, so we can write 10 raised power minus 2 and we taking the square of that. So writing the equation, we write E is equal to E naught minus is equal to E naught minus 0.0592 divided by 10 minus log of 1 divided by 10 raised power minus 4. E is equal to E naught minus 0.0592 divided by 10 multiplied by log of 1 over 10 raised power minus 4 is equal to 4. So E will be equal to E naught minus, so multiplying 0.0592 with 4 and divide by 10, we get the answer 0.0236 volt. So by reducing the concentration of manganese ion by a factor of 100, the potential of the cell will reduce by 0.0236 volt.
So in this problem given with a galvanic cell and its standard cell potential, we have to find the pH of the solution in the anode compartment. So to do that, first we have to write down the cell reaction from the cell notation given, and then from there we'll have to calculate the cell potential for the anode compartment or the hydrogen compartment, and then we have to use the Nernst equation to find out the pH of the solution in anode compartment. So let's first write down the reaction equation from the cell notation, and the reaction equation will be hydrogen gas reacting with lead 2+ ion, and this will give us solid lead and hydrogen ion. So this is the cell reaction for the cell given, and the cell potential for this cell would be the standard cell potential for the anode compartment, and that would be from hydrogen to hydrogen plus, so from here to here, and we will add up the cell potential for the cathode compartment. That would be the cell potential for, or the standard reduction potential of Pb2 plus 2Pb. So this value is given as 0.28 volt. We have to find out this value. So EH2 so H plus, and we can find out this value from the chart, and from the chart we can see that the standard reduction potential for lead 2 plus 2 lead is minus 0.13 volt. So now we got out these two values. If we just do the calculation, we will get the cell potential for the anode compartment, and this will give us a value of 0.41 volt. So this is the cell potential for the anode compartment. Now we have to find out the pH of the solution in the anode compartment, and for that one we'll just utilize the Nernst equation. And as you know that for writing down the Nernst equation for the anode compartment, let's first write down the half cell reaction of the anode compartment. So the half cell reaction here will be so this is the half cell reaction for the anode compartment here, and we will write down the Nernst equation for this, and it will be cell potential of H2 to H plus, and so this is our Nernst equation. So it will be equal to standard cell potential for this half cell minus, we'll just write down the formula as 0.0592 volt over the number of electrons which is transferred in the process, and we see that the number of electrons transferred in the process or reaction is 2. So we'll place it 2 here, and then we will take the log of H plus ion concentration, and since the H plus ion concentration here has a coefficient of 2, so we'll place 2 here, and at the bottom we'll get the pressure of the hydrogen gas. It will come from here, and if we just take this, so this is the log of H plus ion square by the hydrogen pressure. So now we know all the values here, as we know that so we know this value as 0.41 volt. So this value is basically 0 if we look at the standard reduction potential charge. The value for hydrogen gas to hydrogen plus ion, the standard reduction potential is 0 for that. And if we just calculate this part, we'll have to let's just write down it for now. Over 2 times log of, let's see, place of the value for, we'll place the value for the hydrogen pressure, which is 1, and then if we just calculate the entire thing, we can get the value of the log of H plus as equal to, if we solve this equation, we will get 0.41 volt equal to 0.0592 pH. So we can write another line in between here. So we can make it 0.592 volt over 2, and we'll write down this one as 2 log of H plus. And now, as you know, that log of H plus is the pH, so this is our pH value. So if we just solve this equation, we will get the pH value of this as 6.92, and this is the pH of the anode compartment, or the pH of the solution in the anode compartment of the cell given. So in this problem, we are given with a cell reaction, and we are asked to find out the equilibrium constant for this cell reaction. So to do that, what we have to do first is we have to set up a relation between the equilibrium constant and the standard cell potential, because the information given here, if you want to find out the equilibrium constant from the information, we have to set up the relation between the standard cell potential and the equilibrium constant, and the relation is as follows. The standard cell potential is equal to 2.303 RT over NF times log of K, where K is the equilibrium constant and A naught is the standard cell potential. And since we are asked to find out the value in 25 degrees C, as we know that at 25 degrees C we have a value for this part, which is 0.0592. So we can rearrange this to write down the, or find out the equilibrium constant value, and this will give us N E naught over 0.0592 volt. So now we have to know the standard cell potential value, and we have to know the value of N. If we know these two values, we can find out the equilibrium constant. So to find out the value of standard cell potential, let's write down the half cell equations, and from there we'll be able to find out the entire cell potential. So our anode half reaction here would be Fe2 plus, in aqueous form it will become Fe3 plus by donating 1 electron, and the standard cell potential for this half reaction is equal to minus 0.77 volt. And then for the cathode half reaction, we have oxygen reacting with 4 hydrogen, and it will require 4 electron to give us 2 water molecule. So as you see that we need 4 electron to reduce the oxygen, and so that means we'll have to multiply the first equation by 4, so that we'll get 4 electron here. So if we just write this as 4, so it will be 4, and then 4 here and 4 here. And the standard cell potential for this reaction is minus 0.77 volt. So if we now just sum up these two values, so this 4 is with this, so it is 4 Fe. So if we now add them up, we'll get 4Fe2 plus oxygen plus 4H plus, and we will cut off these electrons, and on the right hand side we will get 4Fe3 plus in aqueous plus 2H2O, and then the overall cell potential will be the summation of these two. So the overall cell potential is minus 0. Okay, so the standard cell potential for the standard cell potential for this reaction is 1.23 volt. So now if we just sum them up, we'll get a value of 0.46 volt. So this is the standard cell potential for the reaction given, and now we just have to plug in these values in the formula here. And we know the value of N. The value of N here is 4 because we have 4 electrons transferring in between. So if we just plug in the values, we'll get log of E naught, no, log of K give us 4 times 0.46 over 0.0592, and this will give us a unitless number of 31.08. And then if we take the antilog of this equation, we will get K is equal to 10 to the power 31.08. So this is the equilibrium constant for the cell given. So in this problem, we are given with a redox reaction, which involves the transfer of 2 moles of electrons, and we are given the equilibrium constant of this reaction. We have to find out the standard cell potential for this redox reaction. So let's first, to do that, we have to know the relationship between the standard cell potential and equilibrium constant, and we know that the relationship between these two is log of standard potential. The log of equilibrium constant is equal to number of electrons involved in the reaction or transferred in the reaction times the standard cell potential over 0.0592 volt. So this reaction equation is valid at a temperature of 25 degrees C. So we are given the number of electrons involved in a redox reaction, and we are given the equilibrium constant value. We have to find out the standard cell potential value from here. So if we just plug in the values we are given with, we can get, so we are given the value of equilibrium constant as 1.8 times 10 to the power minus 5, and we are given the value of N as 2, as the number of electrons transferred is 2. So if we just plug in these values, we will get log of 1.8 times 10 to the power minus 5, and on the right hand side we'll get 2 times the standard cell potential and over 0.0592 volt. And then from here we can get the value of E naught as, if we just solve this equation, we'll get the value of E naught as minus 0.140 volt. So the standard cell potential for this redox reaction given is minus 0.140 volt.
In Leclanche cell, is also called dry cell. The following reaction occur at electrode at anode. As we know, at anode always oxidation take place, so zinc metal is oxidizes into Zn2 plus ion and release 2 electron. On the other hand, at cathode, the manganese dioxide MnO2 in the presence of ammonium ion NH4 plus ions gain these 2 electron and is reduced, forming Mn2O3 molecule, where the manganese has been reduced from +4 oxidation state to +3 oxidation state. At the same time, ammonia is formed and a molecule of water is formed. In case of alkaline cell, at a node, zinc react with hydroxyl ion from the alkali, so zinc is oxidized, forming Zn zinc hydroxide, and 2 electrons are released. At cathode, the manganese dioxide in the presence of a water molecule gain these 2 electron, forming Mn2 manganese ion form Mn2O3 molecule, and 2 hydroxyl ions are produced in the reaction. Here the manganese from +4 oxidation state has been reduced to +3 oxidation state. In case of nickel cadmium battery, at anode, cadmium is oxidized, taking 2 hydroxyl ion from the base. It is oxidized to Cd plus 2 ion, where it reacts with the hydroxyl, forming Cd cadmium hydroxide, and 2 electrons are released by the cadmium in this process. At cathode, nickel at cathode, the reduction of the nickel take place, where nickel oxygen hydroxide NiOH in the presence of water molecule gain an electron, forming nickel hydroxide, and a hydroxyl ion is formed. To make the electron loss and gain equal, we will multiply the cathodic reaction with 2. The whole reaction will be multiplied by 2, so we will make the loss and gain of electron equal. In case of lithium battery, at anode, X number of lithium atom oxidizes into X number of lithium ion and gave X number of electrons. At cathode, manganese dioxide react with the X number of lithium ion and also gain the X number of electrons, forming LiX MnO2 complex. In case of lithium ion battery, at anode, graphite anode, LiXC6 oxidizes, forming X Li ions plus 6 carbon atoms and gave X number of electrons. At cathode, Li1 minus X COO2 react with X Li ion and gain the X number of electron, forming LiX CO2 complex.
In this problem, we are asked to find out the similarities and the differences between a battery and a fuel cell. So the basic similarity between a battery and a fuel cell is both of them are galvanic cells. That means they convert chemical energy to electrical energy by a redox reaction. So if you write them down, we can make two columns, one for battery and one for the fuel cell. And the similarity is both of them are galvanic cells. That means they convert chemical energy to electrical energy by utilizing a redox reaction. And the basic difference between these two cells is, in case of a battery, the reactants are contained in the cell. So reactants, in case of a battery, reactants are contained in the cell, but in case of a fuel cell, the reactants are not contained in the cell. They are continuously supplied from an external source. And these are two the main similarity and the difference between a battery and a fuel cell.
In case of fuel cell, the following reaction take place at electrodes. At anode, the oxidation of the hydrogen molecule take place in the presence of hydroxyl ion. It form water molecule and 4 electrons are released in the process. On the other hand, at cathode, oxygen molecule is reduced, gaining these 4 electrons in the presence of 2 water molecule. Here it form 4 hydroxyl ions. As we know that the oxidation potential of hydrogen is 0 volt, while the reduction potential of oxygen in this case is 0.4 volt. To combine both the reaction, adding both the reaction, we can cross the electrons on either side. Also the hydroxyl ions on either side, and we can cut 2 water molecules, so we can say that 2 hydrogen react with an oxygen forming 2 water molecule, and the overall cell potential E cell is equal to the oxidation potential plus reduction potential, so it is equal to 0.4 volt. In case of proton exchange membrane cell, PEM, proton exchange membrane cell, PEM. At anode, the water molecule, the hydrogen oxidizes, form hydrogen ions, and 4 electrons are released. At cathode, oxygen molecule in the presence of these 4 hydrogen ions gain the 4 electrons, forming 2 water molecule. As again we know that the oxidation potential of hydrogen is 0 volt, while in case of proton exchange membrane, the reduction potential of oxygen is 1.23 volt. Combining both equation, adding the 2 equation, we can cross hydrogen ions and electrons on either side of the equation, so we can say 2 hydrogen molecule react with an oxygen molecule, forming 2 water molecule, and overall cell potential is equal to the sum of oxidation and reduction potential, which is 1.23 volt. In case of corrosion of iron, the iron is first oxidized into ferrous ion, where it gave 2 electrons. In the next step, the ferrous ion react with the oxygen molecule in the presence of hydrogen ions, where it further oxidizes into ferric ion. Here 4 ferrous ion oxidizes into 4 ferric ion in the balance equation and gave 2 water molecule. Then the ferric ion react with water molecule, forming Fe2O3 monohydrated rust molecule, and hydrogen ions are formed in the reaction. So here rust is formed in this reaction. In case if magnesium is present, so the oxidation potential of magnesium is high than the iron, so magnesium is oxidized to magnesium ion and release 2 electrons. The electron released by the magnesium keep the iron Fe 3 plus ion in the reduced form, that is iron. To make the reaction balance, we will multiply the magnesium and the number of electron released by magnesium with 3 and the iron and the number of electron gained by iron with 2, so the reaction will be balanced. In case of magnesium, when magnesium is oxidized, and release 2 electrons, the electrons are gained by the oxygen and it form water molecule. So when magnesium is present, we will find the iron in the reduced form and there will be no corrosion of iron. This is called cathodic protection.
Today we are going to be looking at the electrolysis of potassium hydroxide, and in part A we will be labeling the anode, cathode, and ion flow, and in part B we will be labeling the reaction at the anode, cathode, and overall. Let's start by understanding what electrolysis is. So this is the process of electrically splitting an electrolyte. Currently our electrolyte is potassium hydroxide, which is going to break down to give us potassium and the hydroxide ion. If we look at what the anode and cathode are in the next steps, typically in our voltaic cell equations, we noted the anode as negative and the cathode as positive. However, in this, our cathode will be negative and our anode will be positive. Additionally, at the anode, we're going to be having oxidation, and at the cathode, we will be having our reduction occurring. By looking at Leo Szöger, we can understand what's happening with our electrons. So at the anode, we are going to be having oxidation, so a loss of electrons. And at the cathode, we are going to be gaining electrons. And we're flowing from anode to cathode in terms of our electrons. Next, we are going to draw out what is going on here. So we are going to go and draw our 2 electrodes, and we are going to submerge them under molten potassium hydroxide. We're going to go ahead and label our electrode on the left as our cathode and our electron on the right as our anode. And as we have previously discussed, our cathode is going to be labeled as negative and our anode as positive. Based on the electrolysis of potassium hydroxide, it's going to break into K plus and OH minus. And due to the fact that opposites attract, K plus is going to flow towards the cathode and our ion flow for hydroxide will be towards the anode. And now we have completed part A. Next, we're going to write out our reaction equations. So we'll start with potassium at the cathode, and this is going to be a gain of electrons. So we're going to have our positive potassium ion reacting with an electron to give us elemental potassium. And this is our cathode equation. Now at the anode, we are going to have the hydroxide ion, and it's going to be losing electrons, that is, it is oxidation. And in order to see what this will split into, if we draw out our hydroxide ion splitting, it's 2 parts, oxygen and hydrogen will form H2O and O2 as compounds, and as I'm going to draw out now, we can see how the two H's and an O are going to group together, and how 2 O's are going to group together to form diatomic oxygen. Now we have to balance this equation as we have an uneven number of oxygen and hydrogen on either side. So to do this, we are going to put a 2 in front of H2O because this will give us an even number of oxygens to be working with. And if we are going to balance this out, we're going to write a 4 in front of the hydroxide ion on the left. We now have 4 hydroxide ions we're dealing with, so we're going to be losing 4 electrons. Now, for the overall reaction, we need to have an even number of electrons on either side of the equation so that we can cross them out. So because of this, we're going to multiply our cathode reaction by 4. And then we will be able to write our overall reaction. So it's 4K plus 4OH minus. That will give us 4 potassium plus oxygen plus 2 H2O. And that is our overall equation. That will be in blue. In green is our anode equation. And in red will be our cathode equation.
Alright, so problem 31 here. We're given 2 bases, and we're asked to name the base and also figure out if it's seen in DNA, RNA, or both. Okay, so the way we go about this is to just look at the different function groups or different atoms that are connected to our kind of a main ring, right? So starting with part A here, we see that we got this group sticking out of our ring, and everything else would just be hydrogens, right? The white spheres represent hydrogens. So this is an NH2 group. So whenever you only have NH2 and nothing else connected to the ring, you got an adenine, right? And also adenine would have this 2 rings connected to each other. That's also characteristic of both adenine and guanine, actually. Okay, so this NH2 tells us it's adenine. So where do you see adenine? Do you see it in DNA, RNA, or both? And we know that the only difference between DNA and RNA is the uracil and thymine. So adenine would be found in both. Okay, so part B right here, we see that we got 2 oxygen atoms connected to our ring. So whenever you see 2 oxygen atoms connected as such, immediately we think either thymine or uracil. Okay, so those are the only bases in DNA or RNA that has that kind of structure. Okay, so what tells us whether it's T or U is whether we have this methyl group right here. So this is CH3. Okay, so if you have that CH3, that means you have a thymine. So this structure right here is a thymine. If you don't have that CH3, then you have a uracil. Okay, so where do you see thymine? Do you see it DNA, RNA, or both? And we know that thymine could be found in DNA only, because in RNA we have uracil and not thymine. Okay, so those are our answers for this one. Okay, problem 40. What are functional groups? Okay, so functional groups are little compounds or molecules that are connected to a larger molecule. Okay, so it could be just one atom, okay, or it could be a compound. Okay, and it is connected to a larger molecule. Now, why are they important though? So they are important because these functional groups exhibit their own chemical properties. Okay, they have their own chemical properties. And those properties affect the larger molecule. Okay, so their chemical properties affect the chemistry of the larger molecule that they are connected to. Okay, so hopefully that gave an emphasis on why we care about functional groups. so problem 41 is asking for us to describe the structure of the given functional groups. So starting here with part A, okay, so starting with part A, we have alkene. And an alkene is characteristic of a double bond between two carbons. So we got a double bond between two carbons, and since each carbon could handle 4 bonds, we can have 2 more other things connected to each of our carbon. So that would be the structure for an alkene, okay? Part B, we got alcohol, okay? So part B, alcohol is characteristic of having an OH connected to a carbon. So we're going to have this carbon, and it will be connected to an O and H, okay? So we're going to have OH connected to carbon, and as usual, that carbon could handle more bonds to other atoms, okay? Next, part C. Part C, we have an ester. And an ester is very similar to carboxylic acid, right? Where we have a carbon double bonded to O, and then we have another oxygen right here. And as usual, it would be connected to a carbon. Okay, so what makes ester different is that instead of having hydrogen, you know how carboxylic acid would normally have H bonded to oxygen right there. So instead of having a hydrogen, we're going to have another carbon. All right. So, and as usual, these carbons can be connected to other atoms as well. So this would be an ester. And finally, we have part D, which is amine. Okay. So amine is, as you probably remember, would have a nitrogen in it. So we have a carbon, and it will be connected to NH2, okay? Or if you want to write that out, we're going to have 2 hydrogen atoms with nitrogen, okay? And as usual, that carbon have space for 3 other bonds, okay? So that would be our structure for amine.
Let's propose a structure for the following conditions. For A, we need a ketone, which will have the formula C5H10O. So one possibility here is going to be CH3, CH2, C double bond O, which is our ketone, CH2, CH3. So there's one possibility for that molecule. For B, we want an ester with the chemical formula C6H12O2. So this could be one possibility, CH3, CH2, CH2, C double bond O, OCH2CH3. So there's our ester with the formula C6H12O2. And for C, we want an amine and a carboxylic acid, which has the chemical formula C2H5NO2. So this molecule could look something like H2N, CH2, C double bond OOH for the carboxylic acid. Let's draw structures for the following molecular formulas. For A, we have C2H7N, and a possible formula can be CH3, CH2, NH2, and that could be a structure that can exist. For B, the formula is C4H8, and a possible structure could be CH3 CH. We'll include a double bond here, CH3. For C, we have C2H4O, and a possible structure here is CH3CHO as an aldehyde. And for D, we have CH2O2, and a possible structure here can be HCOOH as a carboxylic acid. Let's draw the isomers of C3H8O. We can have CH3, CH2, CH2OH. We can have CH3, CH, CH3OH, and we could also have CH3, CH2, OCH3. So there would be the three isomers of C3H8O.
Problem 45, we are identifying function groups. Okay, so we have here the structure of cocaine, right? Structure of cocaine. And we are given both the line bond structure and the molecular model. Okay, so whatever is helpful or easier for you to use, just go for it, right? And I'm just going to use the line bond structure right here. So I'm using line bond, okay? So the way I want to do these types of problems is just to go on every carbon in the molecule, okay? So this first carbon right here is ACH3, so I'm not as interested, but it is connected to an oxygen, so maybe watch out a little bit, right? But once we get to this second carbon right here, we see that it is a carbonyl carbon, and it's actually a part of this larger function group, including the first CH3, right? So that makes it our ester. Okay, that makes it our ester. And after this carbon, we have this cyclic alkane, right? We got this ring right here. And in that ring, we see a nitrogen, okay? We see this nitrogen right here. But it's not next to any carbonyl carbon, so that makes it our amine, right? So it's not an amide. It's not an amide. Okay? And then once we get to this carbon right here, right, we see that it is connected to an oxygen, and then right next to that is another carbonyl carbon. Okay? So this group together would make another ester. Okay? And finally, we see this aromatic ring right here. We got a benzene included in this molecule, so that would be our aromatic ring. Okay? So at this point, we've gone over every single carbon in this molecule, and that's all our function groups. Okay, so problem 46. We're asked to differentiate straight chain versus branched chain alkane. Okay, so straight chain alkane is pretty straightforward. You just need to have all your carbon atoms in one straight chain, hence the name straight chain, right? So what I mean by that is, if you have any molecule at all, you'll just have all your carbons in one chain, like that. Okay, now you could have other atoms that kind of sort of work as branches, like maybe you can have a nitrogen here, an oxygen here. It doesn't really matter as long as all those carbons are in one chain. Okay, meaning you don't have any carbons sticking out of the main chain. Okay, so moving on with branch chain alkane. Well, branch chain, as the name suggests, has carbons branching out from the main chain. Okay, so if you have a bunch of carbons in your molecule, okay, say this would be your main chain, there would be a carbon somewhere sticking out. Okay, so maybe you got one, maybe you got two, like that, and this would be a CH2, CH3. As long as there's carbon that is outside this main chain, right? So here we see a carbon and another carbon right here. That would be a branch chain alkane. Okay, but what I want to point out here, excuse me, is say we got something like this, right? Got that, and we got maybe we got a carbon, and then maybe you'll have an O, right? OH. Okay, so that would be just an example I came up with. Okay, so now is this a branch chain alkane? Okay, so is this gonna be your main chain, and then is that gonna be your branching group? And the answer is no. Okay, remember, the main chain is the longest chain you could find. So if you find the longest chain here, it's actually the carbon. Okay, so that OH is going to be outside your main chain. So actually this molecule right here is a straight chain molecule. Okay, so try not to be confused. And I know it's not exactly a straight line, but they're all in one main chain. So hopefully that explanation was helpful.
Problem 47 is asking for us to differentiate alkane and an alkyl group. Okay, so an alkane is a molecule that contains only CH bonds. Okay, it contains only CH bonds, and all are single bonds. Okay, all are single bonds. Okay, an alkyl group is a substituent, right? It's a substituent that is derived from an alkane. Okay, derived from an alkane. Okay, so if we have, for example, an ethane, right? So an ethane would be 2 carbons, right, and 3 hydrogens each, right? That would be an ethane, right? If this ethane would be connected to a larger molecule, say we have this very large molecule right here, and here we connect our ethane, right? Okay, so once that ethane is connected to a larger molecule, we don't call it ethane anymore. We call it an ethyl group. Okay, so it is derived from the ethane, but since it's now connected to a larger group, we call it an ethyl group. Okay, so that's the same for every single alkane and its corresponding alkyl group. Okay, also one thing to notice is that the alkyl group is missing one of the hydrogens. Okay, so it's missing one of the hydrogens because it's now connected to the larger molecule. Okay, so hopefully that helped clarify the difference between the two terms.
Okay, so for problem 48, we have a molecule here that is proposed with a chemical formula of C3H9. So whereas, why would scientists be skeptical about this molecule? Okay, so obviously this molecule is supposed to be an alkane, right? And it only has carbons and hydrogens. And the formula that we use for alkanes would be CN H 2n plus 2. Okay, so what I mean by that is if carbon has a subscript of 3, or meaning you have 3 carbons in your molecule, right? So you got C3. So n equals 3 right here, okay? So that means your hydrogen is going to have to be 2n plus 2. So 2 times 3, which is n, plus 2 would have to be 8, okay? So this is supposed to be your alkane if you have 3 carbons. And that's precisely why scientists would be skeptical about this molecule, is because it has 9 hydrogens, meaning it has 1 extra than what the carbons could handle. For problem 49, we have a set of molecules given in condensed structures, and we're asked to find what's wrong with it. So there's one thing that is wrong in each of these, and we have to find that. Alright, so starting with part A, we have a carbon double bonded to another carbon here, and we see that this first carbon has 3 hydrogens. Alright, so it has 3 hydrogens, but at the same time it's also double bonded to carbon number 2, right? So if we rewrite this, we're supposed to have carbon double bonded to another carbon with 3 hydrogens in it. Okay, and that doesn't make sense because here carbon has 5 bonds around it, and that just violates our octet rule here. And so this part right here is what's wrong with molecule A. Okay, so this part, okay, carbon 1 has more hydrogens than it can have. So part B, okay, carbon 1 is CH3 single bonded to carbon 2, nothing suspicious. Alright, and then we got carbon 2 being CH2, okay, and then bonded to carbon 1 and carbon 3, again nothing suspicious. So let's move to our double bonds here. Okay, so what I want to do is redraw this part. Okay, so we have a carbon double bonded to another carbon, and then double bonded to an oxygen. Okay, and then this carbon is bonded to, let me number our carbons so we don't confuse ourselves here. 1, 2, 3, 4, 5. Okay, so I'm drawing carbon 3 here. So this is carbon 3, and it is bonded to carbon 2. Okay, and then we have a hydrogen with it. And then carbon 4 here is bonded to CH3. Okay, so now that we drew everything, we could clearly see what is wrong here. We see a carbon, and it has 5 bonds with it, right? It is double bonded with oxygen, it's double bonded with a carbon, and then it still has this bond with CH3 right here. So that's what's wrong here. This carbon number 4 has more bonds than it's supposed to have. Okay, so let's I'm actually gonna go and start counting our carbons here. So we could talk about it easy. So 1, 2, 3, 4, 5. Okay, so carbon 1 here, right? Carbon 1 is CH3 bonded to a carbon. Nothing suspicious about that, right? Carbon 2 seems to be the same. Okay, so again, we come across our triple bond here, and I want to redraw that and see if there's anything wrong with it. Okay, so we got carbon 3, triple bond, C, and then this carbon 4 has 2 hydrogens in it, right? And then it is bonded to ACH3. And then on the left, we got CH2 bonded to carbon 3. So CH2. Okay, so is there anything wrong here? Well, yes, and it's pretty intense compared to part A and part B here. Here we got a carbon having 6 bonds, right? Got 6 bonds. It has a triple bond with carbon 3, and at the same time it still has 3 single bonds with it. So that's just whack. Okay, so that's what's wrong with this molecule. Okay, carbon 4 has just way too many bonds than it's supposed to. Okay. Alright, so we have the structure of vitamin C here on our screen, and we're asked to figure out all the functional groups that are in this structure. So again, the way I want to go about doing these kind of problems is to just go on every single carbon in the molecule and see if they have functional groups connected to them. Okay. So starting with this carbon right here, looking at everything that's connected to it, we see an OH group right here. So we got an alcohol group, right? So that's pretty much it for this carbon. Moving on to the next carbon right here, we'll look at everything attached to it. We got carbons, hydrogens, and this another OH group right here. So another alcohol group. Okay, so moving on, I'll start using a different color here. Moving on to our next carbon. There's really no immediate functional group that comes out of this carbon, so I'll go and proceed to this next carbon right here, which is a part of an alkene, right? So this would be an alkene. Alright, so, and then in this alkene, we see 2 alcohol groups connected to it, right here, okay? So, this is an alcohol group, this is also an alcohol group, okay? And then moving on to our last carbon right here, we see that this is actually part of an ester right here, right? With these kinds of functional groups, we have to be a little bit careful because sometimes it just looks like a carbonyl group, but we see that it's actually an ester, right? So this is an ester, a cyclic ester to be exact, because it is part of a ring. Okay, so at this point we've gone over every single carbon in our molecule, and I think we've got all our functional groups. Alright, so problem 50, we're naming some alkanes, right? Okay, so let's go for it, starting with part A here. So again, first step is to find the longest chain we could find, okay? So looking at the structure, this seems to be the longest chain, right? And next is we number according to where we have the first branch point. Okay, so I think it's pretty clear that the first branch point is closer if you count from the right instead of from the left. Okay, because if you count from the left, this would be your first branch point. But if you count from the right, this is your first branch point, and this is just closer to the end. So, hopefully I explained that well. But anyways, let's go ahead and count. Got 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so we got 8 carbons, meaning we have an octane, right? We got an octane for 8. Next is, let's go and find our alkyl groups, okay? So here on carbon 3, we have a methyl group. So we have 3 methyl, okay? And on carbon 4, we have an ethyl group, okay? So we have CH2, CH3, which is ethyl. Okay, so we got 4 ethyl. Okay, so now that we have that, we can go ahead and combine every information that we have. Okay, so we go by alphabetical, and since E goes before M, we start with 4 ethyl. So we got 4 ethyl, 3 methyl octane. Okay, so 4 ethyl, 3 methyl octane. Next, part B. Again, find the longest chain, and I think this would still be our longest chain. Alright, and as usual, it looks like the first branch point is closer to the right side. Okay, so it's closer if we count from the right side. So let's go ahead and count. Got 1, 2, 3, 4, 5, 6, 7. Okay, we have 7, meaning we have a heptane. Okay, we got a heptane. Let me box this answer from part A so we know it's separate. Okay, so we have a heptane. Next is we look at our branch points. Okay, so we see that on carbon 2 we have a methyl group. So we have 2 methyl. And next on carbon 4 we have this 3 carbon chain, which is an isopropyl group. So we got 4 isopropyl. Okay. Alright, so hopefully you remembered what isopropyl looked like. So finally, we've gone over all the branch points, and we could combine all the information we have. Okay, so I goes before M in the alphabet, so we get 4 isopropyl. Oops. Isopropyl, 2 methyl heptane. Okay. Alright, so that's for part B. Going for part C, I want to do this on the left side since we're kind of running out of space here. Okay. It looks like this would be our longest chain, right? And this time, I think the branch point is closer from the left side. We can't really confirm that, I think we just have to count from both sides and see. Okay, so we got 1, 2, 3, 4, 5, 6, 7, and if we count from the left side, 1, 2, 3, 4, 5, 6, 7. Okay, so the first branch point is always, looks like either way, you're going to have it on carbon 2 first. But what makes it different is that this carbon has 2 methyl groups in it, right? So it has 2 methyl groups. Let me remove that. And if we count from the left, or sorry, if we count from the right, if we follow the green counting system, we're going to end up having 2 methyl groups on carbon 6, right? But if we count from the left, if we follow our orange counting here, we're going to have our 2 methyl groups on carbon 2, okay? So remember, we still want the least kind of numbers as possible in our naming. So if we follow green, we're going to end up with let me get our highlight here, 2 and then 6, 6, right? But if we do the orange counting, we're going to have 2, 2, and then 6. So having 2, 2, 6 would be better. In fact, that would be the only correct way. Okay, so let's start counting from the left then. Got 1, 2, 3, 4, 5, 6, 7, right? Since we have 7, that means we have a heptane. Okay, and now on carbon 2, as we mentioned, we got 2 methyl groups. Okay, so we got 2 methyl, and I'm just gonna separate them for now. Well, we're gonna combine this later. And we also have that methyl group on carbon 6, so we got 6 methyl. So this is what I'm talking about earlier. If we counted from the right going to the left, we're gonna end up having 2 methyl, 6 methyl, and then another 6 methyl. So if you add these, that's pretty much how I remember it. If you add these, this would be a larger number. It's going to be 14. If we add this is only 10. So we want this, okay? We want the lower number. All right, so at this point, I think we have everything that we need, so we could combine our information. Okay, so we have all methyls. So this is going to make a tri-methyl, right? So we got 2, 2, 6, tri-methyl heptane. Okay, there we go. All right, on to our last problem here. Okay, let's find the longest chain. This looks like it's gonna be our longest chain, right? Okay, so again, we count from left and then count from the right and compare. 1, 2, 3, 4, 5, 6, 7, 8, and then 1, 2, 3, 4, 5, 6, 7, 8. Okay, so our first branch, if we count using blue, the first branch point would be on carbon 5. Okay, be on carbon 5. If we count following green, the first branch point would be on carbon 4. So we're following the green counting here. So I'll erase everything and leave the green counting system, I would call it. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, meaning we have octane, right? For 8 octane. Okay, so our first branch point here, in fact, our only branch point, we got two things attached to it. One is a methyl group. So we got 4-methyl. And the other one is an ethyl group. Okay, so we got 4-ethyl. Okay, so at this point, we could combine all the information we have. Okay, so we got ethyl and we got methyl, and E comes before M in the alphabet. So we got 4-ethyl, 4-methyl octane. Okay, so alright, so finally we have named all the molecules we have for problem number 50. Alright, moving on to problem 51. Okay, we're still on IUPAC naming, and this time we are naming isooctane. Okay, so we are getting the IUPAC naming for isooctane. This is the common name for it. Okay, so first step is find the longest chain, and I think it's easier with the condensed structure right here to see that this is the longest chain that we have. Okay, so I'm going to number from the left and then from the right, and let's see where we hit our first branch point. We got 1, 2, 3, 3, 4, 5, and then from the right we got 1, 2, 3, 4, and 5. Okay, so it looks like either way we're gonna hit our first branch point on carbon number 2. Okay, but as you see, if we follow the green numbering, if we count from the left, once we hit carbon 2, we have 2 groups attached to it. Okay, as compared to when we count from the right side, when we hit our first branch point, we only have 1 group attached to it. So this counting from the left side would be our priority. Okay, and I'll explain a little bit more of that as we go. Alright, so we're counting from the right, as I mentioned, and I want to deal with this using our molecular model, since it has more space and it's easier to just write. Okay, so we got 5 carbons in our main chain, which means we have a pentane. Okay, we have a pentane. So on carbon 2 right here, we have 2 CH3 groups. Alright, so that's a methyl group. So we have 2-methyl and another 2-methyl. I'm just going to separate them for now, and we'll combine them later. Okay, and then we have carbon 4 here with another methyl group. So we have 4-methyl. Alright, so at this point, we've gone over all our branch points, and we could combine the information we have. So we have 3 methyls, which gives us trimethyl. Okay, and then we're just listing the numbers in order. So we have 2, 2, 4, trimethyl pentane. Okay, if we have counted from the right side and following this orange numbering right here, we're gonna have 2, 4, 4 trimethylpentane, and as you could see, this would give us a lower total number, so that's why we counted it that way. Okay, but anywho, this is our IUPAC name for isooctane.
Alright, so problem 52, we are writing condensed structures. Okay, so let's just go for it. Part A. Okay, part A says we have 3 ethyl hexane. So hexane means we have six carbons in our molecule, right? So 1, 2, 3, 4, 5, 6. Okay, and then 3 ethyl here means we got an ethyl group on our 3rd carbon. So this would be my 3rd carbon, and I'll go ahead and add CH2, CH3. So that's your ethyl group, okay? And all that's left to do here is to add those hydrogens, okay? So our first carbon here on the left could handle 3 more hydrogens, okay? And then the second one could handle CH2. And this 3rd carbon currently has 3 carbons bonded to it, so it can only make 1 more bond with hydrogen, okay? And then this 4th carbon could handle 2 more, as well as this carbon, and the last carbon only has one carbon connected to it, so it could make 3 more bonds with hydrogen atoms, okay? So that should be part A. Part B, okay, we got 2,2,3 trimethylpentane, okay, pentane. So pentane means we got 5 carbons. So I'll go ahead and write 5 carbons here for 5, okay. 2,2,3 trimethyl means we got 3 methyl groups, and they're on carbons 2, 2, and 3. So carbon 2 has 2 methyl groups, and carbon 3 has 1, okay. So I'll go ahead and fill those bonds with methyl groups, okay, CH3, and another CH3, okay. So now that we have all our groups connected, all we have to do is fill up the carbons with hydrogens, okay. So this first carbon would be CH3, right? The second carbon already has 4 carbons connected to it, so it can't handle another bond, so we could leave it alone, right? This 3rd carbon right here has 3 carbons connected to it, so it could handle 1 more hydrogen, okay? And this 4th carbon could connect or could bond with 2 hydrogens more, and our last carbon can be CH3, okay? So that's it for our part B, okay? So just as a reminder for everyone that these spaces are not supposed to be part of our condensed structures. That's just an extra space that was left after my work, but when you write your structures, please make sure you don't have those spaces, okay? So part C, we got 3-ethyl 3,4-dimethyl heptane, okay? So whenever I try to read these structures, I kind of start ignoring the groups first, and then I focus on the first thing that I need to know, which is how many carbons are there, okay? So now I know there's 7, so I'll go ahead and write 7. 1, 2, 3, 4, 5, 6, 7, okay? Now I got 7. Now I worry about the groups, right? So I got 3-ethyl. So I'll go to the 3rd carbon and add an ethyl group, okay? So I'll put it up here. Ethyl would be CH2, CH3, okay? 2 carbons. And then I have 3,4-dimethyl. So I got 2 methyl groups. One would be on carbon 3 and one would be on carbon 4. So CH3 here and CH3. So 3,4-dimethyl, okay? So now that we have all our alkyl groups connected, we fill those bonds with hydrogen atoms, okay? So what I mean by that is that carbon needs to have four bonds around it, and we fill those bonds with hydrogen if they're missing some, okay? For example, this first carbon here, has 1 carbon connected to it, so that means it needs 3 more bonds and that's going to be filled up by hydrogen. Okay, so second carbon would be CH2. This third carbon already has 4 carbons connected to it, so it doesn't need any more bonds with hydrogen. Okay, fourth carbon here could handle 1 more hydrogen. Okay, these next 2 carbons could handle 2 hydrogens each, and our last carbon here would have 3 hydrogens connected to it. Okay, so that should be our structure for part C. And finally, we have structure part D. Okay, we got 5 isopropyl 2-methyl octane. So again, as you notice, I just kind of ignored all the groups there and went to the part where it says octane. Okay, so that means I have 8 carbons. So let's go ahead and draw 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and then I have an isopropyl group on carbon 5. Okay, so 1, 2, 3, 4, 5. This is carbon 5. And I have an isopropyl group. So hopefully you remember what isopropyl looks like. Okay, so this is what it looks like. It has a carbon that splits and connects to two more methyl groups. Okay, and finally I have the 2-methyl right here, so I'll go to carbon 2 and add a methyl group. Okay, all that's left for us here is to make sure that every carbon is connected to 4 things. If it's not, then fill it up with hydrogen. Okay, so first carbon here needs 3 more bonds, so we're filling that out with 3 hydrogens. Okay, second carbon could handle 1, then we have CH2 for the next 2 carbons. Okay, this 5th carbon has 3 things connected to it, 1 on the left, 1 on the right, and 1 below. Okay, so that means it could handle 1 more hydrogen. Then we have CH2 for the next 2, and our last carbon here would have 3 hydrogens connected to it. So there you have it. That's all our structures for this problem. Alright, problem 53. We are drawing structures, and as you would probably notice by now, they're all cyclic structures. Okay, and the reason that I have these cyclic structures pre-drawn below is because I'm not very good at drawing polygons, so hopefully you are. But there you have it. I have our cyclic structures pre-drawn, so let's just go for it. Right, starting with part A here. Part A says cyclooctane. Okay, so that just means cyclo meaning you have a ring, and octane that means you have 8 carbons. Okay, so 8 carbons in a ring would give you an octagon, right? So outside of chemical or chemistry context, that's called an octagon. So you're just gonna have to draw an octagon. Okay, which is what I have here in part A. So I have a cyclic structure with 1, 2, 3, 4, 5, 6, 7, 8 carbons in it. Okay, so that's pretty much it for part A. Part B is a little more complicated. We have function groups now attached to it, right? We got 1,1-dimethyl-cyclopentane. Okay, so pentane means we have 5 carbons, and cyclo means they are in a ring, hence this pentagon that I have right here on the right side. Okay, and then we have 1,1-dimethyl. Okay, 1,1-dimethyl means we have 2 methyl groups, and both of them are on carbon 1. Okay, so at this point you're assigning numbers to carbons, and it's arbitrary, right? So you could use any of these carbons as your carbon 1. So I'll just choose this carbon right here. Okay, so I'll choose that, and there are 2 methyl groups attached to this carbon. So I'll go ahead and add those methyl groups. So there you go. That's 1,1-dimethyl cyclopentane. So this is part B. Okay. So moving on to part C here. We got 1, 2, 3, 4 tetramethyl cyclobutane. Okay. Cyclo meaning you have a ring, and butane means you have 4 carbons in your ring. So it's kind of like a square, right? So so first is you draw that square or diamond, whatever you want to call it, and which we have right here. And we have 1, 2, 3, 4 tetramethyl. Okay, so that means we have 4 methyl groups, tetramethyl, and they're on carbons 1, 2, 3, and 4. Okay, so each carbon here is gonna have a methyl group. So for this example, doesn't matter how you count it because they're all gonna have the same methyl group, right? So you can choose which of these carbons would be your carbon 1, which would be 2, 3, and 4. In this case, it doesn't matter. Okay, so there you go. We have 1, 2, 3, 4 tetramethyl cyclobutane. So that is part C. Finally, here we have part D, and we got 4-ethyl 1,1-dimethyl cyclohexane. Okay, so whenever we are drawing structures, I think it's very important to start with the base structure, which is cyclohexane here. So as you noticed, I kind of just skipped over all the groups, all the function groups, and I'll just pay attention to those later. So this is part D. So we have a cyclohexane, which is outside of chemistry concept, that would be called a hexagon. Okay, so you got six carbons in one ring, cyclohexane, and then we got 4-ethyl 1,1-dimethyl. So I want to go ahead and just number my carbons here, and again, doesn't matter which one is carbon 1, so I'll just choose that to be carbon 1, 4, 5, 6. Okay, so now that they're numbered, I can go ahead and put my groups. I have 4-ethyl, so I'll go to carbon 4 here and add an ethyl group. So I'll have CH2, CH3. Okay, so that's ethyl. And I have 1,1-dimethyl, meaning I have 2 methyl groups and both of them are on carbon 1. So this is methyl group and another methyl group. So there you have it. Those are all our structures for problem 53. Alright, problem 54 is asking us about aromatic compounds, and why is it that when a compound is aromatic, why is it that it doesn't necessarily mean that it smells nice? Okay, so why is that the case? Well, that's because the term aromatic refers to a class of compounds that is made of a 6-membered ring that has 3 double bonds. Okay, so this is what the term aromatic means. It does not mean it has anything to do with the smell. Okay, so it is made for these types of compounds. Okay, so hopefully that clarified that term.
An addition reaction is an organic reaction in which the reagent adds to the multiple bond of the unsaturated reactant to yield a saturated product.
Okay, problem 56. We are writing structural formulas for these molecules that they described for us. Okay, so there's a lot of different answers for these kind of problems, so I'm going to come up with one, but if it's not the same as the one you came up with, it doesn't mean it's wrong. Okay, so these descriptions have many other isomers that could come with it, so I'll just write what I have in mind, and we'll go from there. Okay, so starting with part A. Part A says we want an alkene with 5 carbons. Alkene with 5 carbons. Okay, so that's exactly what I'm gonna do here for part A. I will write my 5 carbons. Okay, 1, 2, 3, 4, 5. Okay, and I want a double bond somewhere, and I don't know, I just want to put it here on the very first carbon. Okay, so now that we have that, I actually need to rewrite that. Now that we have this double bond on the first carbon, right, we could fill up the rest of the bonds with hydrogens. Okay, so this bond would have CH2, right, could handle 4 bonds, and the same, oh, not the same, the second carbon could only handle 1 hydrogen because it has 3 bonds before that. Okay, so then we have CH2, CH2, and CH3. Okay, so that's the structure that I came up with for part B, and again, that double bond could be anywhere else in this structure, so that's just where I wanted to put it. Part B. Okay, part B, we got an alkyne with 4 carbons, so I want to start with having 4 carbons, right? 1, 2, 3, 4. Okay, so I have 4 carbons, and we have an alkyne. We have an alkyne, meaning we have 3 bonds, or a triple bond. We have a triple bond somewhere, and I'm just deciding to put that again on the first carbon. Okay, so now that we have that triple bond, let's go ahead and fill it out with hydrogens, right? This first carbon can handle 1 more hydrogen, plus those 3 bonds gives it a total of 4 bonds. This second carbon is saturated with 4 bonds, so we could leave it alone. So I'll just write the next carbon right next to it, right? And then we have this carbon, which could handle 2 more hydrogens, and finally we have CH3 at the end. Okay, so that's what I came up with part B. Again, if yours doesn't look like this, it doesn't mean it's wrong. Okay, so there should be isomers that are possible for this molecule. Okay, part C. Part C, we got a substituted aromatic compound with 8 carbons. Okay, so, well, I know one very, very common aromatic compound, right? I have benzene, right? So what I want to do here is just to draw that benzene. Okay, draw that benzene. Okay, so it says that we need 8 carbons total, and benzene has 6, right? Benzene has 6 carbons, so we need 8 total. So 8 minus 6, meaning we need 2 more carbons in this molecule. And it also says substituted aromatic compound, meaning it does have alkyl or functional groups that come with it. So I need 2 more carbons, and well, I'll just add 1 ethyl group, right? Ethyl group has 2 carbons, so CH2, CH3. So there you go. Is my aromatic compound substituted? Yes, it does have this alkyl group. Okay, does it have 8 carbons total? Yes. I have 6 from the aromatic ring, and then I have 2 from the ethyl group. So it satisfies all the requirements for part C. Again, all of these structures are just what I came up with. They do have isomers that are also correct. Okay.
There are 3 dienes with the formula C3H8, and these are, so diene is a compound with 2 double bonds. CH3, so 1, CH3, CH, double bond CH, CH, double bond CH2. So there's, sorry, this is C5H8, not C3H8. Let's fix that. C5H8, dienes with C5H8. Second diene will be CH2, double bond CH, CH2, CH, double bond CH2. So there's the second diene. And the third diene is going to be CH2, double bond CH, C, double bond CH2, and a methyl substituent here. So those would be the 3 dienes that can be formed from C5H8.
Problem 58, we're still on IUPAC naming. Okay, so let's go and start with part A. As usual, let's go and find the longest chain we could find, and I think for this one it's pretty obvious. All right, and here we have a double bond, right? And the rule is whenever we have a double bond or a triple bond, we count from the side where we're closer to that bond. Okay, so what I mean by that is this double bond right here looks like it's closer to the right side. And I mean, you don't really have to estimate. You could check, but I think it's pretty clear to see that there's only 2 carbons on the right side of the bond and there's 3 on the left. So it's closer to the right side. So we count starting on the right side. So let's go and count. We got 1, 2, 3, 4, 5 on our main chain. Okay, so let me give a space for part A down here. Okay, so we got 5, meaning we have a pentene, right? So pent for 5 and pentene because we have a double bond. Okay, and that double bond starts on carbon 2, right? Starts on carbon 2. So this would actually be 2-pentene. Okay, just kind of ran out of space there, but okay, so we have 2-pentene. Next is we check our branch points. And we see here on carbon 4 that we have a methyl group branching out. So we have a 4-methyl. 4-methyl, okay. So now that we have all the information we need, we could combine all of it and come up with our answer. Okay, so we have only one group that we need to take care of. So we got 4-methyl, 2-pentene. Okay, so that should be our answer for part A. Let's go to part B now. So part B. Alright, so again, as usual, let's find the longest chain, and this looks like our longest chain right here, right? We got 2 carbons up here compared to just one if we go along a straight line, okay? And again, we count from where our double bond is closer, and for this one, it's pretty obvious that it's on the right side. Okay, in fact, it's at the end of the right side here, okay? So we're counting from the right side here, 1, 2, 3, 4, 5, okay? So next is we take care of our branch points, and for this one, we actually only have one. We have a methyl group connected to carbon 3, okay? So we have, let me use a different color pen here, okay? We have 3 methyl, 3 methyl, okay? So I think that's all the information we need, and we could proceed to combining all these information. Okay, so we have 3 methyl. We name our branching group first. So 3 methyl, 1 pentene. And that's our answer for part B. Okay, so part C now. We have a benzene ring, and connected to our benzene ring are 2 chlorine atoms. Okay, so we gotta count 1 on the carbon where our functional group is, or our atom is, so this would be 1, and we gotta count 2 on the closest branching group as well, so this has to be 2. Okay, because if we count 2 here, then this chlorine would be carbon 6, and we don't want that, so this chlorine would be on carbon 2. Okay, so we have dichloro, right? So we have 1, 2, 1, 2, since that's where we have our chlorine atoms, and we got dichloro for having 2 chlorine atoms, right? Dichloro benzene. Okay, alternatively, the way that they are positioned, since they are next to each other, we could also name that ortho. Ortho. Okay, so we write O for ortho. O dichlorobenzene. Okay, so there's two possible IUPAC names for part C. Alright, moving on to part D. Part D, as usual, let's find the longest chain. And I think for this one, it looks like it doesn't matter, right? So even if you get this methyl or this methyl, it's going to be the same length, since it's just one methyl for both choices. Okay, so let's just take the straight chain. I think it's simpler. And let's count and see where we hit our double bond first. Okay, so if you count from the left, we got 1, 2, 3, 4. And if we count from the right, we have 1, 2, 3, 4. Okay, so either way, looks like either way, I know it's kind of getting messy here, but either way, our double bond is going to hit carbon 2 first, okay? But if we count from the right and follow the green numbering, once we hit carbon 2, not only do we hit our double bond, we also hit this branch point right here, okay? So kind of shooting 2 birds in 1 stone right there. So we are going to count from the right on this one. So let's count from the right. We got 1, 2, 3, 4. And since we have 4, that's a butene because of the double bond. And it starts on carbon 2, right? Double bond starts on carbon number 2. And that gives us 2-butene. Okay, and I didn't write that well, but you get what I mean. That's 2-butene, and we have this methyl group sticking out from carbon 2 as well, so we have a 2-methyl. So combining all those information, we have 2-methyl, 2-methyl, 2-butene. Okay, and that would be our answer for part D. Alright, finally we are on part E here. Okay, and again, find the longest chain, and it looks like it's pretty obvious. This whole thing here is our longest chain. So again, we are counting from where our triple bond is closest. Okay, so this applies to both double and triple bonds. So it's closer to the left, so we're counting from the left first. 1, 2, 3, 4, 5. Let me rewrite that. 5, 6, 7, and 8. So we get 8. And our triple bond starts on carbon 3. So we got 3 oct. Rewrite that. Got oct for 8 and YNE because of the triple bond. So we got a 3 octane. Okay. And last thing that we need to do here is to account for our methyl group sticking out from carbon 7. Okay. So we got a 7-methyl group. Okay. Alright, so time to combine all the information that we have. We got 7-methyl, 3-octane. Okay, so that's our answer for part E. And finally, we're done here. We have named all the molecules we have for problem 58. Okay, so we're drawing structures for problem 59. So let's just go for it, starting with part A. We got cis-2-hexene. So hexene meaning we have 6 carbons, and 2 and ENE means we have our double bond on carbon 2. Okay, so I actually want to start drawing this with carbon 2 having the double bond with carbon 3, right? And it says cis, meaning our hydrogens would be on the same side, or our carbons connected to carbons 3 and 4, or 2 and 3, sorry. This would be carbon 2, and this would be carbon 3. Okay, so cis, meaning our carbons connected to it would be on the same side, as well as our hydrogens, right? So if this is carbon 2, meaning we're going to have carbon 1 connected to it. Okay, so this is carbon 1. And then we're going to have that carbon 4 connected to it as well. Okay, so that's what we mean by cis. They're going to be on the same side, and the same is true for the hydrogens. Okay, so this carbon is going to have hydrogen, this is going to have a hydrogen, and they're going to be on the same side. Okay, so carbon 1 would have 3 hydrogens connected to it, that because we've pretty much gone over the important part on this molecule. So everything that we're going to do here is just filling up those carbons and hydrogens that we have left. Okay, alright, so we got carbon 4, and this is most likely going to be CH2, right? And then we got carbon 5, and finally we have carbon 6, which will be a CH3. Okay, so there we go. That's our cis-2-hexene. Moving on to part B. we got 2-methyl-3-hexene. Okay, so as usual, we got a 6-carbon molecule with a double bond on the third carbon. So again, I want to draw that starting with carbon 3, right? Starting with carbon 3, then we have it double bonded to carbon 4. So this is carbon 3, this is carbon 4, and it doesn't tell us about it being cis or trans, so we don't really have to show it just like how we showed part A. So as long as we know that carbon 3 would be a CH, right, and carbon 4 would also be a CH, okay, and that would be connected to CH2 being carbon 2 and a CH3 for carbon 1, okay, so this is carbon 1, carbon 2, 3, 4, and then actually we'll edit that a little bit later, but let's go forward with carbon 5 and 6 for now. So we'll have, don't need that bond, we'll have CH2 for carbon 5 and CH3 for carbon 6, okay, so we got 5, 6, and now we take care of that 2-methyl right there. So on carbon 2 we have a methyl group sticking out, so let me erase this number 2 right here, and we have a methyl group sticking out, which means we're going to have to reduce the number of hydrogens that we have, okay, so instead of CH2 we're only going to have CH, okay, so that should be our structure for part B. So next and finally we got part C, right? We got 2-methyl-1,3-butadiene, okay, so that's a pretty long name. This but tells us we have 4 carbons, right? So I want to go ahead and write 4 carbons here. We got 1, 2, 3, 4, okay. 1, 3 tells us we have the double bonds on carbon 1 and then another one on carbon 3, okay. So we have 2 double bonds on this molecule. That's also why we have this diene in our naming. So carbon 1 would have a double bond with carbon 2, and then carbon 3 is going to have a double bond with carbon 4, okay. Alright, now that we got that, all we have to do is take care of the 2-methyl group, okay. So carbon 2 would have a methyl group with it, and after that we could go ahead and fill out the missing hydrogens, okay. So the first carbon would have 2 hydrogens, okay, and carbon number 2 here already has 4 bonds, so it's good to go. Our carbon 3 is missing a hydrogen to make it 4 bonds, and this last carbon here needs 2 hydrogens, okay. So that should be our answer for part C. Alright, so finally we have the structures for all our molecules here. Alright, so for problem 33, we have this molecular model and we're asked to provide a condensed structure, okay? So before we start, I want to remind everyone with what the specific spheres mean. So whenever we see a black sphere, that represents a carbon atom. Whenever we see a white sphere, that represents a hydrogen atom. And the red sphere represents oxygen, okay? And also I want to go ahead and number our carbons. That makes it easier for us to talk about it, right? So let's go ahead and count carbons. 1, 2, 3, 4, 5, 6, and I'll call this carbon down here 7, okay? So let's go for it and start. So carbon 1, we see that it has 2 hydrogens attached to it, right? There's 2 white spheres. So let's go ahead and write CH2. And we see that it is double bonded to carbon 2. So let's go represent that double bond. And then carbon 2 doesn't really have any hydrogens attached to it. So we're writing just C for now. Okay. So it is connected to carbon 3 with 2 hydrogen atoms right here. So let's write CH2. Right. I'll just go ahead and rewrite. I feel like I'm not writing it well. So CH2. Okay. And then we also see that carbon 2 is connected to carbon 7, right? This is carbon 2. Oops. This is carbon 2 right here, and it is connected to carbon 7. And carbon 7 has 3 hydrogens in it. 1, 2, 3, right? So we'll have a bond here on carbon 2, and we'll have a CH3 attached to it. So this CH3 would be our carbon 7. Okay, excuse me. Proceeding to carbon 4. Carbon 4 also has 2 hydrogen atoms, so we're writing CH2. Carbon 5 has 1 hydrogen atom attached to it, right? So for now we're just writing CH, just 1 hydrogen atom. And then it has this functional group connected to it, and as mentioned, this red sphere is an O and this white sphere is an H. So we have an alcohol group coming out of it. So let's go ahead and add that to our structure. So I'll just put it down here, and it is connected to an OH, right? Doesn't really matter if you put it below the C or above. At least for condensed structures, it doesn't really matter. And finally, we have carbon number 6. Carbon number 6 here has 1, 2, 3 hydrogen atoms. So we have CH3 at the end of our structure. And we're pretty much done here. This is the condensed structure of the given molecular model. Okay, so problem 60. We have 3 molecules here, and we're asked which of these is capable of cis-trans isomerism. Okay, so we got 1 hexene, 2 hexene, and 3 hexene. And I do have those molecules pre-drawn in here just so we could talk about it easier, okay? So, starting with 1 hexene, we have this double bond between carbon 1 and 2, hence the name 1 hexene. And the way that this structure is drawn, it doesn't show you the hydrogens, right? So I want to go ahead and draw that just so it's easier for us to see. And before I draw the hydrogens, I want to remind that there's a carbon in here and a carbon right there. Okay, so go ahead and draw the hydrogens. Okay, so there's 2 hydrogens in there, and then that carbon is double bonded to carbon 2. Okay, so carbon 2 has 1 hydrogen, right? So it could only handle 1 more hydrogen. So now we can analyze this molecule if it's capable of cis-trans isomerism. And as you can see, carbon 1 is connected to 2 hydrogens. It's connected to 2 hydrogens, and carbon 2 is connected to 1 carbon. Okay, so 1 hexene is not capable of cis-trans isomerism because there is no carbon connected to carbon 1 here. Okay, so the answer for A is no, it's not capable of cis-trans isomerism. Okay, so proceeding to 2 hexene here. Okay, again, I want to go ahead and draw those hydrogens along the double bond, right? So we got one hydrogen here on carbon 2, and we have one hydrogen here on carbon 3, okay? And then as you can see, you have carbon 4 right here and carbon 1 right here, and they are on opposite sides of the double bond, okay? Right there on opposite side. This one's, if you could think about it, this carbon 4 is kind of going up the double bond, and carbon 1 is kind of going down. Now, is there another way to draw this? Well, I think there is, right? We could draw one of this carbon 1 right here going up like that, right? So, and this is what that is gonna look like. Okay, so if we draw carbon 1 going up, this is what it's gonna look like. Okay, so in this molecule, both the carbons connected to carbon 2 and 3, so we got 1 and 4. Carbons 1 and 4 are on the same side of the double bond, right? They're kind of on the same side. They're both going up. So this would be your cis for same side, okay? Cis isomer and trans isomer. Sorry about that. Okay, so well then, yes, 2-hexene is capable of cis-trans isomerism. There's 2 ways to draw those bonds around the double bond. Okay. Next is 3-hexene right here. So we have carbon 3 and 4, hence the name 3-hexene. Okay. And as you can see, carbon 2 right here is kind of going up the double bond if you think about it, and carbon 5 is going down. Okay. So since they're going on opposite directions, that can be our trans isomer. Now, this can only be trans isomer if we could prove that we can draw this any other way, okay? And the other way that we could try to draw is to draw these carbons going on the same direction, and this is what it's gonna look like, okay? So here, we still have that carbon 3 and 4, and they're double bonded to each other. And then we have 2 and 5 right here, both going on the same direction, okay? So they're on the same direction, so that would be our cis isomer, okay? So, as you can see, we only have 2-hexene and 3-hexene that's capable of cis-trans isomerism. Therefore, our answer would be B and C, okay? So, I need to box that, I think. So, B and C are capable of cis-trans isomerism.
So we're asked which of the following can exist as cis-trans isomers. A can exist as cis-trans isomers. So the cis configuration for A will be with the 2 hydrogens on the same side, CH3, and this would be CH, CH3, and H3C. So there's the cis configuration for A. The trans configuration for A will be this configuration here, where the hydrogens are opposite, and we will get this configuration here for the trans. So A can exist as cis-trans isomers. B cannot exhibit cis-trans isomerism. So there cannot be, so as the CH2 group on the right end has 2 hydrogens attached, so we can't have different groups there. C does exhibit cis-trans isomerism. So for C, the cis isomer will be this configuration here. There's chlorine there, and then the trans isomer we can draw as this isomer here. And so this one does exhibit cis-trans isomerism. So A and C are able to show cis-trans isomerism, while B for A, let's write the reaction of 2,3-dimethyl-2-butene. So 2,3-dimethyl-2-butene. And it's going to be reacted with H2 in the presence of a palladium catalyst, and this would yield CH3 CH3, and we would get CH3 CH3 H and H. For B, again 2,3-dimethyl-2-butene. And this would be reacting with bromine, Br2, and this would yield CH3C CH3, and this would be H. Oh no, not H and H. These would be Br, CH3, and CH3. And for C, 2,3-dimethyl-2-butene. And this is going to react with H2O with a H2SO4 catalyst, so the presence of acid, and this would yield CH3C CCH3. This would be CH3 CH3 OH and H. So there are our completed reactions. Let's complete the following reactions of paradichlorobenzene. For A, we have a halogenation, so paradichlorobenzene is going to react with bromine in the presence of FeBr3, and this will yield the bromine group being attached here. So there's the halogenation. For 2, we're going to show a reaction of paradichlorobenzene with HNO3. And we're using H2SO4 as our catalyst. And this is a nitration. So this will yield this molecule here, Cl, Cl, and NO2. And for C, we have paradichlorobenzene, and it's going to react with Cl2 in the presence of FeCl3 as a catalyst. This is another halogenation, which will yield Cl, Cl, and Cl.
Okay, so problem 64 are drawing structures. Okay, so let's go for it, starting with part A. Part A here we have 2,4-dimethyl-2-pentanol. Okay, so we have that pent right there, meaning we have 5 carbons. So I want to start with drawing 5 carbons here. 1, 2, 3, 4, 5. Okay, and then next we got this suffix "-ol", meaning we have an alcohol, and that alcohol group is on carbon 2. Okay, hence 2-pentanol. So let's go ahead and put that alcohol group on carbon 2, right? So there you go. Next, we got 2,4-dimethyl. Okay, we got 2,4-dimethyl, meaning we have methyl groups on carbon 2 right here, and carbon 4. Okay, now this methyl group could be below carbon 4, but I just chose to put it above it. Okay, so now we have all our functional groups, and all that's left for us to do is fill it out with hydrogens. Okay, so carbon 1 here is only connected to carbon 2, so it can handle 3 more hydrogens, so it's going to be ACH3. Okay, carbon 2 already has 4 things connected to it. It has this carbon, and then carbon 3, and then 2 more groups right here. Okay, so it can't handle any more hydrogens. Carbon 3 right here has 2 other carbons connected to it, so it can handle 2 more hydrogens, right? And then carbon 4 has 3 things connected to it, so it can handle 1 more. Okay, it can handle 1 more hydrogen. And then finally our carbon number 5 here could handle 3 more. Okay, so really the key here is to make sure every carbon is connected to 4 things. If not, then fill it out with hydrogen. Okay, so moving on to part B. Okay, part B, we got 2,2-dimethyl cyclohexanol. Okay, so that cyclohexanol means we have this 6-membered ring right here, and we're gonna use that. Okay, so cyclohexanol, meaning we have the cyclohexene, and then it has an alcohol group. Okay, so let's go ahead and add that alcohol group. Just want to add this here on top. Okay, so whenever you have a cyclohexanol or whatever functional group your ring has, that carbon would be your carbon number 1. Okay, that will always be your carbon number 1. So let's go ahead and count our carbons here. 1, 2, 3, 4, 5, 6. Okay, and then next we got 2,2-dimethyl. Okay, so meaning we have 2 methyl groups on carbon 2, right? So this would be our carbon 2, and we just have 2 CH3 groups in there. Okay, CH3, CH3. Okay, and that's pretty much it for part B. Okay, again, the key here is setting this carbon as carbon 1. Okay, next is part C. Okay, part C, we got 5,5-diethyl-1-heptanol. Okay, heptanol right here tells us that we have 7 carbons. So let's go ahead and start with 7 carbons. 1, 2, 3, 4, 5, 6, 7. Okay. And then we got 1 heptanol, meaning we got the alcohol group on carbon 1. So let's go ahead and add that. And finally we got 5,5-diethyl. So diethyl meaning we have 2 ethyl groups and they're both on carbon 5. So this is carbon 5 right here, and we are going to have 2 ethyl groups. So CH2, CH3. That's 1 ethyl group, and then another one up here. Okay, so now we have all the groups that we need. All that's left is to fill out with hydrogens. Okay, carbon 1 has 2 things connected to it right now. It has the alcohol group and this carbon, right? So let's go ahead and fill it out with 2 more hydrogens. Okay, carbon 2 can be CH2. Same is true for carbon 3. Carbon 4 as well. Okay, so for carbon 5, it doesn't really have any more spots. It's currently connected to 4 things already, so we'll leave it alone. We got CH2 for carbon 6, and finally carbon 7 could handle 3 more hydrogens. Okay, so obviously we have the space here. That's just extra space. If you rewrite your molecule, you're not supposed to have any space there, but that's what we have for part C. Finally, we got part D, right? We got 3-ethyl, 3-hexanol. Okay, so we got 6 carbons from hex right here. So I'm gonna go and draw 6 carbons here. 1, 2, 3, 4, 5, 6, and it says 3-hexanol. So carbon 3 has an alcohol group, right? And we got 3-ethyl. Okay, let me change the color for that. Let's use pink. So 3-ethyl, meaning carbon 3 also has an ethyl group. So CH2, CH3. Okay, so that's pretty much it for part D. All that's left for us to do is fill out with hydrogens. Okay, so first carbon would have 3 hydrogens. Got CH2 in here. Carbon 3 has 4 things connected to it right now. Okay, got 1, 2, and then it's connected to this carbon and that carbon as well. So we can leave it alone. Okay. And then we got carbon 4, can handle 2 more hydrogens, carbon 5 as well. And finally, carbon 6 right here would have 3 hydrogens. Okay. Then again, as I've mentioned, we don't really have this space right here. That's just extra space from that we have. Okay, so when you rewrite this molecule, it's not supposed to have that space right there, but that's all our structures. Okay, so problem 65, we're still drawing structures here and we're dealing with amines. Okay, so I'm starting with part A. We got propylamine. Okay, propylamine, and the way I want to start doing this is to start with the amine backbone. Okay, so what I mean by that is we just have this basic structure of an amine. So we have a nitrogen with 3 bonds to it, and part A says we have a propyl group attached to this amine. So propyl meaning we just have 3 carbons, right? We got CH2, CH2, CH3. Okay, so that's our propyl group, and of course we got 2 more bonds here which would be connected to hydrogens. Okay, so that should be propylamine for us. Moving on for part B here, we have diethylamine. Okay, so I realize I have this cyclohexane in the wrong spot here. Okay, so part B, we got diethylamine. So again, I want to start with kind of the basic structure for an amine, right? So just a nitrogen connected to 3 things. So it says diethyl. diethyl, meaning we have two ethyl groups attached to nitrogen. Okay, so we have one ethyl group right here, CH2, CH3, and another one right here. So it doesn't really matter where you put it, right? And of course, that last bond would be connected to hydrogen. Okay, so that should be our diethylamine. Part C is a cyclohexylamine. Okay, cyclohexylamine. Okay, so that's why I have this cyclohexane right here, and it's going to be connected to one of the bonds with nitrogen. Okay, so since I already have this cyclohexane right here, I just want to connect that to nitrogen, right? And of course, nitrogen is going to have two more bonds, and those bonds would be filled up with hydrogen. Okay, so that should be cyclohexylamine for us, and I think we all have our structures here. Problem 66 is asking for us to compare aldehyde versus ketone. Okay, so before we start comparing, I want to go ahead and draw what we have. So an aldehyde would be a carbon connected to an oxygen via a double bond and a hydrogen, and it's going to be connected to another carbon right here. Okay, so this could be anything. So that would be aldehyde. Okay, ketone would have a carbon and then another carbon and another carbon, and this middle carbon would be double bonded to oxygen. Okay, and this carbons at the end could be connected to anything. Okay, so that should be our ketone. So I think the difference is pretty clear here. Okay, for it to be a ketone, it has to be somewhere in the middle of the molecule, right? So it has to be in the middle of two carbons, hence it will be somewhere in the middle of your molecule. Okay, and for aldehyde, for it to be an aldehyde, it kind of has to be at the end, right? Because this is hydrogen right here, and it's not going to be connected to anything else. So for it to be an aldehyde, it has to be a terminal group. Okay, so I guess the biggest difference between aldehyde and ketone is that aldehyde would be a terminal functional group, meaning it's always at the end, and ketone would always be in the middle. Okay,
Carboxylic acids, esters, and amides all undergo carbonyl group substitution reactions.
problem 68, we are identifying the carbonyl groups on all of these structures that are given. Okay, so starting with part A, I think part A is pretty clear right here. Okay, so what we just have a ketone right here. Right, so part A would just be a ketone. Okay, part B right here may be a little bit tricky. First of all, it's terminal, meaning it's connected to the very end carbon. Okay, so we have two choices here. It could either be an alcohol, or an aldehyde. Okay, and so the safest way here is to just count how many things are attached to carbon. Okay, so we got 1, this is attached to our carbon, and then we have one hydrogen, right? So it has two things attached to it, so that oxygen has to be double bonded to carbon in order to fill those 4 bonds to carbon, right? So that means since we have a double bond, that means we have an aldehyde, okay? And another easier way or faster way to identify if it's an alcohol or an aldehyde is that an alcohol would always be written as OH, right? And aldehyde would always be HO, okay, or CHO, okay? So if it's OH, it's definitely alcohol. If it's written as CHO, then it's aldehyde, okay? Part C. So here's our oxygen right here. And again, this question stem already tells us we have a carbonyl group, but if it doesn't tell you that, this oxygen could either be an ether, or because it's somewhere in the middle of the molecule, it could be a ketone. Okay. So as discussed in a previous problem, if a carbonyl group is somewhere in the middle of a molecule, then it is a ketone. So part C here would be a ketone, okay? Since we know it is a carbonyl group. If you want to make sure it's not an ether, then you can go ahead and count the bonds connected to carbon, and you'll see that it needs to be double bonded to oxygen. Okay. Part D. Part D is right here. And I think it's pretty clear. We know that this is a carbonyl group, right? So it's going to be a C double bonded to oxygen. And we have that nitrogen in there. So that makes this group our amide. Okay. Okay, on to our last part, part D. We got 2 oxygens, okay? So we really only know 2 functional groups with 2 oxygens in it. One would be a carboxylic acid. That's a hydrogen. We rewrite it. Carboxylic acid, or an ester. Right? The only difference would be either you have a hydrogen connected to your oxygen or another carbon, okay? In this case, as we see, we have this carbon connected to our oxygen, right? Meaning our functional group here would be ester. Okay.
For A, we are to draw 3 amides with the formula C5H10NO. So one amide could be CH3, CH2, CH2, CH2C double bond O and H2. So there's one possibility. Second amide is CH3, CH2, CH2C double bond O, and H in the CH3 group here. And a third amide could be CH3, CH2C double bond O, and CH3, CH3. So there's 3 amides with the formula C5H10NO. And for B, we're going to draw 3 esters, and these esters are going to have the formula C6H12O2. So one ester is going to be CH3, CH2, 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 C double bond O, OCH3. So there's one possibility. A second ester can be CH3, CH2, CH2, C double bond O, OCH2, CH3, and a third ester can be CH3, CH2, C double bond O, OCH2, CH2, CH3. So there are three esters with the formula C6H12O2.
Alright, so problem number 34 is asking us to identify the functional groups that we have in the given molecular models. Okay, so let's start with part A here. And as usual, I just want to go and go over every single carbon in the molecule and see if they're connected to any functional groups. So starting with this carbon, this first carbon here, this is just CH3, so I'm not as interested, but we see that it's connected to an oxygen atom, right? So this whole part right here is our ether, right? And moving on with this carbon, sorry, let me box that again. Okay, so moving on with this carbon, it's only connected to other carbons and hydrogen, so I'm not as interested. Moving on with this carbon, that should be the same thing. But this next carbon right here, you see that it is connected with an oxygen atom, right? So this red sphere is an oxygen. So that represents our ketone, right? That represents our ketone, okay? And then moving on to the next carbon, we see that it is double bonded to the carbon next to it. So that would be our alkene. Okay? And they're both just connected to hydrogen atoms, so no other functional groups there. And moving on to our last carbon here, this last carbon, we see that it's only connected to hydrogen atoms, so there's no functional groups there either. So that's it for part A. We got three functional groups. We have an ether, a ketone, and an alkene. So part B now, again, just going through the carbons one by one. So starting with this carbon, right, we see that it has 3 hydrogen atoms, so no functional groups there. Moving on to this next carbon right here, we see that it is double bonded to a carbon, so that would be our alkene. Okay. Next, moving on to this carbon, only connected to hydrogen, so no functional groups. Next would be this carbon, and we see that it is connected to this structure right here, and this blue sphere represents a nitrogen. Okay, so now we got a nitrogen connected to 2 hydrogens, NH2, so this makes it our amine group. Amine. Okay, last carbon here. Okay, last carbon, we see that is connected. It is connected to 2 oxygen atoms, right? So this whole part right here is our carboxylic acid. Okay, carboxylic acid. So those oxygens, those red spheres are oxygens, and there's this hydrogen atom right here. So that's a carboxylic acid. And at this point, we've gone over every single carbon in this molecular model for part B. So we ended up with 3 functional groups. We have an alkene, an amine, and a carboxylic acid. Alright, problem 70. So we're still on drawing structures, and as you probably noticed, all our molecules here has a suffix of O8, or I guess not for part C, but O8 means we're dealing with esters, right? Okay, so let's go ahead and start. Part A, we got methyl pentanoate, so pent, meaning we have 5 carbons. So I'm going to go ahead and draw 5 carbons first. 1, 2, 3, 4, 5. And we have that O8, right? Got that O8, so meaning we have an ester going on here. So we're putting our ester here as carbon 1. Okay, so whenever you have an ester, the carbon connected to your oxygens would always be carbon number 1. So our countings would be like so. Okay, and we got methyl right here. So for esters, whenever we have a alkyl group connected, we always connect that to our terminal oxygen right here. So this is where our methyl would be. Okay, so all that's left for us to do here is to fill out those missing hydrogens, right? So carbon 5 is at the end, so it could handle 3 hydrogens. Okay, and carbon 4 would be CH2, same for carbon 3, and finally for carbon 2 as well. So we got all our hydrogens now, and you could go ahead and confirm by counting how many bonds you have on carbons, but I'll leave it right there. Okay, so part B, we got butanoate, meaning we have 4 carbons. So I'll go ahead and write 4, right? 1, 2, 3, 4. Okay, and O8, got this O8 again. So we have an ester. Okay, so we're gonna have something connected to that oxygen right there. Okay, so we have 2-methyl. Okay, 2-methyl. Let me use a different color. We got 2-methyl butanoate. So again, whenever you have an ester, the carbon connected to oxygens would be carbon number 1. And let's proceed counting to carbon 4. So we got 2-methyl, meaning we have a methyl group on carbon 2. Okay, so CH3 right there. Okay, and finally we have isopropyl. So meaning our oxygen right here is going to be connected to an isopropyl group. Okay, so isopropyl is just one of those structures that you need to memorize. So that is what an isopropyl group looks like. Alright, so all that's left for us to do is fill it out with hydrogens. Okay, so this would be CH3, CH2, oops, CH2. Carbon 2 here has one alkyl group connected to it, so meaning it can only handle 1 more hydrogen. Okay, and carbon 1 already has all those 4 bonds filled out, so that would be our part B. Okay, so I'll go ahead and let me write those parts just to make it clearer. Okay, finally we got part C. Okay, we got cyclohexyl acetate. So let's start with the acetate. Okay, so an acetate is pretty much a kind of a nickname, sort of, for your ester with one more carbon connected to it. So what I mean by that is we have CH3 and then we have our ester. So that's it. That's all we have for an acetate. So whenever you have an acetate on your molecule name, this would be the kind of the base structure. for it. Okay, so that's your acetate, and we're told that it has a cyclohexyl group connected to it. Okay, so as usual, that alkyl group would be connected to our oxygen, and I do have our cyclohexyl group right here that is ready to be connected, just right there. Okay, so that's it. That is cyclohexyl acetate. Problem 71, we are still drawing structures, and this time we have amides. Okay, we're dealing with amides. So part A, we got 3-methyl pentanamide. So I want to start by drawing just 5 carbons for pent, right? So we got 1, 2, 3, 4, 5, and we have that amide, and I want to put that amide right here. Okay, so it's always going to be terminal, but as usual, just like in esters, this would be your carbon 1. Okay, 2, 3, 4, and 5. All right, and we're told that we have a methyl group on carbon 3. So let's go ahead and add that methyl group on carbon 3. Okay, and at this point, we have all of our branch points or alkyl groups connected. All that's left for us to do is fill this out with the missing hydrogens. Okay, so carbon 5 would have 3 hydrogens. Then we have CH2. Carbon 3 has 1 group connected to it, right? We have this methyl group, meaning it can only handle 1 more hydrogen. And then we got CH2 for carbon 2. And carbon 1 is already saturated. And then we have NH2 for our amide. Okay, so that's for part A. Part B, we got phenylacetamide. Okay, so I want to remind everyone about acetate. Okay, so whenever you see that acete, kind of like aceta, which is from acetate, so we could go ahead and draw an acetate molecule. So we got CH3, right, and we have an ester. Okay, but because we have acetamide right here, this oxygen is going to be changed to a nitrogen. Okay, so that would be acetamide, and then we have a phenyl group. Okay, so unlike esters where alkyl groups are usually connected to the oxygen, here it's never connected to the nitrogen unless specified. Okay, so the naming is going to be different if it is connected to nitrogen. So that phenyl group would be connected to this carbon 2 right here. So I'll go ahead and draw a 6-membered ring. Okay, so there we go, that's our benzene ring right there. So we got phenylacetamide, and if you notice, since we added this bond right here, we have to reduce the number of hydrogens we have. Okay, so this carbon now could only handle 2 hydrogens, and as usual, this N right here could handle 2 more hydrogens. So there you have it, that's our phenylacetamide.
Hi everyone. Uh, functional groups. Functional groups present in Novocaine are okay, are first one is ester ester, that is C double bond O O. Then second one is amine. Of course, amine again. One is NH2, that is primary amine. The next one is tertiary amine. Then next functional group is aromatic ring. So the structure of alcohol and carboxylic acid used for synthesis of this, that is, this is NH2 C double bond O O C2H5, that is ethyl 4-aminobenzoate. Ethyl 4-aminobenzoate obtained from 4-aminobenzoic acid, plus another one is HOCH2 N C2H5. This is diethyl aminoethanol. Diethyl aminoethanol. Whenever they are treated with sodium ethoxide, C2H5O minus Na plus, you can say. So they gives Novocaine. NH2, then C double bond OO, CH2 N C2H5 plus C2H5OH. So this is Novocaine. It is also called Procaine. So these are the two structures of, one is alcohol diethyl amine ethanol, and second ethyl 4-aminobenzoate obtained from 4-aminobenzoic acid. Now 4-aminobenzoic acid cannot be used directly for synthesis of this, but that can be used in the form of ester.
Let's draw the structure of soap molecules, and this is a saponification reaction. So we have our reactants CH2 OC double bond O, CH2 14 CH3 CHO C double bond O, CH2 7, CH double bond CH, CH2 7 CH3, and CH2O, C double bond O, CH2 16, CH3 plus 3KOH, and this is going to yield CH2OH, CHOH, CH2OH plus CH3, CH214, COO minus K plus, and CH3, CH2 7, CH double bond CH, CH2 7, COO minus K plus, and CH3, CH2 16, COO minus K plus. And that would be our saponification reaction between a fat, so this is our fat, potassium hydroxide, and we will produce an alcohol, which is glycerol, and a mixture of potassium salts. And these would be our 3 potassium salts breaking apart the fat.
Problem 74 is testing your memory of amino acid abbreviations, right? So I think this problem is pretty straightforward. It's just something that you have to memorize, right? So part A is SER. So there's really only one amino acid that starts with SER, which is serine, okay? So we have serine. Part B is THR, or threonine. So threonine. PRO for proline. Part D is PHE for phenyl, right? Phenylalanine. And finally, we have CYS for cysteine. Okay? So hopefully that wasn't too hard for you and you've memorized your amino acids.
Problem 75, we are drawing amino acids. So for each of these parts, we have a requirement, and then we need to draw an amino acid that satisfies that requirement. Okay, so part A, we need an amino acid that contains an isopropyl group, right, which is underlined right here, isopropyl group. And before we start doing that, I want to go ahead and draw the base structure for an amino acid, right? We have this NH2 group right here, and it's connected to CH, and it's connected to carboxylic acid, okay? And below this middle carbon is where our R group is going to be, okay? Okay, so our R group has to have an isopropyl group, okay? So the easiest I could think of is valine, okay? So valine is exactly what that is. Valine is an isopropyl group, right, connected to this base structure for amino acid, okay? So that should be part A. That's not the only amino acid with an isopropyl group, but that's the easiest that came to my mind. Okay, next. Again, before we look at that, let's go and draw our base structure for amino acid. Okay, and then we're ready for our R group. So we need something that contains an alcohol group, okay? And the easiest I could think of is serine, because serine just has a CH2 group and then it ends with an alcohol group, okay? So that's serine. Moving on to part C. Again, before we look at our requirement, I'll go ahead and draw our base structure. Okay, so now we're ready for that R group. We need one that contains a thiol group. So thiol is an SH group, and there's really only one, right? We only have cysteine. That's the only amino acid that has a thiol group. It's not the only amino acid that has a sulfur. Methionine has sulfur, but it's not a thiol group. It's not SH, right? Okay, finally we have part D. We want something that contains an aromatic ring. Okay, so let's go ahead and start with our base structure. And we want an aromatic ring, and the easiest I could think of is phenylalanine, right? So phenylalanine has this CH2, and then it has a benzene ring. Okay, and there you have it. Again, let's just go around and name these amino acids that we drew. So part A is valine, part B is serine, part C is cysteine, and part D is phenylalanine. Okay.
Problem 76, we are identifying amino acids, okay? So we are given this massive molecule right here and we're asked to identify amino acids, okay? So what's nice about this molecule though is it's drawn in a way that we have our backbone in a straight line, right? And everything outside this box would be our R groups, okay? So those are R groups that's going to help us to identify our amino acids. And since we have 6 R groups, as you can count those blue circles, meaning we have 6 amino acids, okay? So I'll go and erase those blue circles to make it easier to see, and let's go for it. Okay, so our first group right here, okay, we have a CH, so we have a C connected to 2 more methyl groups, okay? And if you notice, it looks like a V, an upside down V, and that's how I remember the amino acid valine, okay? It looks like a V, okay? Next group right here, we have a CH2OH, okay? So I think this is just something you have to memorize. That would be serine. So you have 1 carbon and then it ends with a alcohol group, okay? All right, then our third R group here is very unique. It has that phenyl group attached to it. So from phenyl, it has a phenyl group that tells us this is phenylalanine. And it gets that name because alanine only has CH3 as an R group, and then you connected a benzene ring to it, or you connected a phenyl group. So hence the name phenylalanine. Okay. Next, our fourth R group right here. As you can see, it has a sulfur. So meaning we could only have either cysteine or methionine. Okay. But since our S is in the middle of carbons, that means we have methionine, okay? Methionine. If it was cysteine, that S is going to be the very end atom, okay? So we're going to have SH if it was cysteine. Next, we got this R group, and you see that it has alcohol in it. Okay, so if you have an alcohol in your R group, you could either have serine or threonine. Okay, so serine, as we already saw on this R group, it only has one carbon with it. Okay, so meaning this would be our threonine. Okay, and finally here we have a very simple R group. We just have a CH3, so that would be our alanine. Okay, so we have six amino acids on this molecule, and if it helps, let's go ahead and write it as one molecule. So we have valine, we got serine, we got phenylalanine, we got methionine, we got threonine, and finally we have alanine. Okay, so hopefully that was helpful. Problem 78. We're asked to name all the tripeptides possible, given methionine, isoleucine, and lysine. Okay, and my technique whenever we have this kind of problem is to just pick one of the amino acids to be the first amino acid in the chain. So let's choose methionine first. So I'll go right met for methionine. Okay, we're also asked to use the 3-letter abbreviations. So I'll follow that with isoleucine, and we got lysine left. Okay, and for the second tripeptide, I want to keep methionine as the first amino acid, and we have to flip lysine and isoleucine. Okay, so we got lysine as the second amino acid this time, and then we have isoleucine last. Okay, so next I want to have isoleucine as the first amino acid. Okay, so I'll have isoleucine right here, and then I have methionine and lysine left. So I'll just write methionine as second and then lysine. And then next I want to keep isoleucine being the second or the first amino acid, sorry. And then I still have methionine and lysine left, so this time I have to flip it. I need to put lysine as the second amino acid and then methionine as the last. Okay, and finally I want to have lysine as the first amino acid, so I'll put lysine. And then I have methionine and isoleucine left, so I'll just put methionine first, and then isoleucine would be last. And then again I want to keep lysine being the first amino acid, and this time isoleucine has to go second, and then methionine would be last. Okay, so there you have it. We have 6 tripeptides possible total. So we have 6 different combinations possible. Okay, so that's pretty much it. Problem 79. We are given 4 amino acids here. We got alanine, serine, leucine, and glutamic acid. Now we are asked 2 things. One is how many tetrapeptides are possible. So how many different combinations can we have with these 4 amino acids? Of course, assuming you could only use each once. Okay, and we are also asked to name 3 out of all those possibilities. Okay, so we have this pretty neat formula for that. We got number of peptides, or a number of different possibilities, equals and factorial. Okay, and n is the number of amino acids that you have. Number of amino acids. Okay, so in case you don't remember what n factorial means, so let me explain that a little bit. So we got 4 factorial here, right? We got 4 factorial from having 4 amino acids, okay? So in math, that means we do 4 times 3 times 2 times 1, okay? So if you got 5 factorial, you're going to have to do 5 times 4 times 3 times 2 times 1, okay? So now that we have that, all that's left for us to do is solve that, which would equal to 24, okay? So there are 24 possibilities of combinations for these 4 amino acids, okay? So out of those 24, we're asked to name 3, okay? So I think it's pretty easy to come up with 3, right? So I'll just write what we have here in order. So we got alanine, right? And then serine, and then leucine, and glutamic acid. Okay. So that's for the first one, and then second, maybe I'll just rewrite the same thing and then flip the last 2, right? Glutamic acid and then leucine, right? And then I need one more. So maybe I'll flip the first 2, right? I'll get alanine. Oops. I just said I'll flip those first 2. So I'll have serine first, and then alanine second, and then I'll just go on with glutamine and then leucine, or glutamic acid, sorry. Okay, so that's it. We got 3 out of 24 possibilities, and I hope that was helpful. Alright, problem 80. Okay, we are asked to define the structural difference between an aldose and a ketose. Okay, so right off the bat, we could see that these are sugars. Okay, because of the suffix OSE. So that's a suffix we use for sugars. And then what I have down here are 2 different structures of sugars. And this is not included in the problem. This is actually from a previous problem in the same chapter, but I thought they would be good examples for this problem. Okay, so we got the OSE, which stands for sugar, and then we got ald for aldose, and then ke for ketose. Okay, so aldose, from the prefix ald, that means we got aldehyde. Okay, means we got aldehyde. And then ke for ketose means we have a ketone. So that gives us our structural difference, right? An aldose would have an aldehyde, and a ketose will have a ketone. And so we look at our sugars here. We look at part A, and we see that does it have a ketone? No. Our carbonyl group here is at the end, and it's attached to a carbon and then attached to a hydrogen, which means we have an aldehyde. Okay, so this would be an aldose. And then we look at part B. Does it look like it has a ketone or an aldehyde? And it looks like it has a ketone, right? We have a carbonyl group in the middle, and then this carbon is connected to 2 other carbons, so that would be our ketone, and that means the sugar would be a ketose. Okay, so that is the structural difference between an aldose and a ketose. Alright, so for problem 35, we are on systematic naming. So we're asked to name these molecule models according to IUPAC rules. Okay, so starting with part A, we want to start with numbering our structure. So first we got to find the longest chain we could find, and then so let's start and do that. And I think from looking at it, I see that this would be my longest chain, right? And then I'll have 2 groups attached to it. Okay, and then we start counting from the end where the first branch point would occur. What I mean by that is, if we start counting from the right, we got 1, 2, 3, right? So the first branch right here, the first branch point would occur at carbon 3. But if we start counting from the left, we start with 1, 2, we see that the first branch point would be on carbon 2. So we got to start counting from the left because we want the branch point to occur first. Okay, so we want it to occur number 2 and not 3. So let's start counting from the left here. I'll go and erase everything I've got so far. Okay, so let's count from the left. We got 1, 2, 3, 4, 5. Okay, so we have 5 carbon chains. We have 5 carbons in our chain. And they're all single bonds, right? We don't see any double bonds. So that would be our pentane, right? That would be our pentane. Okay. Next is we figure out the branch points and see what we have connected. So for carbon 2, we see that we have a CH3, which means we have a methyl group attached. So that's going to be our 2-methyl, right? 2-methyl. And then next is we have, for carbon 3, right here, we have another methyl group coming out. So that's going to be 3-methyl, right? So since we have both methyl groups, we have to combine those, right? We have to combine these two and call it dimethyl. Alright, so now we've gone over all the branch points, and I think it's time to combine everything we have in here. Okay, so as far as numbering is concerned, we write 2 before 3. Okay, so we got 2, 3, and then we have dimethyl, right? Dimethyl pentane. Okay, so this would be your final answer for part A. So moving on to part B. Again, let's find the longest chain we could find before everything else. So from looking at it, I think this should be the longest chain, right? Actually, it doesn't matter, even if I counted this, and this would be the attached group. It doesn't matter. It will be the same amount of carbons in the chain. So we got 1, 2, 3, 4, 5, 6 carbons in the chain. But as you could see, the first branch point would be here, and also this is where our alkene is, so it's closer to the right side. Okay, so we need to start counting from this side. Okay, so let's go and erase everything we have so far and count from the right. Okay, so let's go for it. We got 1, 2, 3, 4, 5, and 6. Okay, so we have 6 carbons in our chain, and we have a double bond. So 6 would be hex, and since we have a double bond, that would be a hexene. Alright, so also the hexene, right? The hexene starts on carbon 2 right here, so we're gonna have 2 hexene. Alright, and also on carbon 2 we have our only group attached, right? We don't have any other branch points. This would be the only one, and we have a CH3, which is a methyl group. So we're gonna go ahead and write 2-methyl because it's found on carbon 2. Okay, so at this point I think we're done, and all we have to do is combine the information that we have. So as usual, we start with the the attached group. So we have 2-methyl, 2-methyl, and then we have 2-hexene. Okay, so this would be your final answer for part B. For problem 81, we are classifying carbohydrates. Okay, so whenever we're classifying carbohydrates, we have two criteria. Okay, so one is it an aldose? Is it an aldose? Or is it a ketose? Okay, that's question one. And second is how many carbons? So number of carbons. Okay, so those two would be like our criteria for classifying carbohydrates. Okay, so let's start with part A here. So first question, does it look like it has a ketone or an aldehyde? Okay, so we have our carbonyl group right here, and we see that our carbon double bonded to O is connected to a hydrogen. So here we have an aldose. Okay, so that this is an aldehyde. So we have an aldose. And we name carbohydrates by starting with either aldo or keto. Okay, so this would be an aldo because it has an aldehyde. And next we count the number of carbons. Okay, we got 1, 2, 3, 4, and 5. Okay, so for 5 carbons we got the prefix pent, and we got that OSE, meaning we have a sugar. Okay, so that's just a suffix for sugars. So part A is an aldopentose. Moving on to part B. So again, we look at the carbonyl group. Does it look like it's an aldehyde or a ketone? Okay, so this is our carbonyl group, and I think it's pretty clear that it is an aldehyde. So that means we start it with the prefix aldo. Okay, and next is we count the number of carbons. Got 1, 2, 3, 4, 5, and 6. So for 6 we got the prefix hex, and we got that suffix OSE suffix for carbohydrates. Okay, so we got aldohexose. Part C. Let's look at our carbonyl carbon. This is right here, and since it is at the middle, that means we have a ketone, right? So we start our naming with the prefix keto, okay, and then we count our number of carbons. 1, 2, 3, 4, 5, and 6. Okay, so we have 6 carbons in this sugar, meaning we have hex. We use the prefix hex, and again we've put OSE, meaning we have a carbohydrate. So part C is a ketohexose.
Problem 82 is asking for us to draw an open chain structure of a ketotetrose. Okay, so tetrose meaning we have a sugar with 4 carbons in it, right? And then keto meaning we have a ketone as opposed to an aldehyde. Okay, so I want to start by drawing just the 4 carbons. So 1, 2, 3, 4. Alright, and I just chose this carbon to be my carbon number 1. Okay, so that would be our carbon number 1. And whenever we have a keto sugar, the carbonyl group is going to be on carbon 2, right? So I'm going to put it on carbon number 2. And then all the other carbons are going to have an OH group. Okay, so they're all going to have an OH group. So let me add this OH group on this carbon, and then another OH group. So basically just an OH group for each carbon. Okay, so this OH group is for this carbon. I just left some space there that we're going to need for the hydrogens. Okay, so now we have all the oxygens that we need for this molecule, we could proceed to filling out the rest of the bonds with hydrogens. Okay, so starting with carbon number 1, it's connected to carbon 2 here, and then the OH group, so it could handle 2 more hydrogens. Okay, so it's gonna be CH2OH. Okay, this carbon 2, let me number our carbon so I don't confuse anyone. It's gonna be 1, 2, 3, 4. Okay, so that's the numbering for our carbons. Carbon 2 already has 4 bonds, so it's not gonna have any hydrogens in it. Carbon 3 currently has 3, so it can handle 1 more hydrogen. And finally, we have carbon number 4, which is currently connected to 1 carbon and 1 oxygen. Now, so it could handle 2 more hydrogens. Okay, so obviously this space right here is not supposed to be there, so when you rewrite your molecule, just make sure you don't have that space. But this should be our open chain structure for a ketotetrose. Problem 83 is asking for us to draw an open chain structure of a 4-carbon deoxy sugar. Okay, so before I even deal with this new term deoxy right here, I just want to go ahead and just draw that 4-carbon sugar. Okay, and let's just deal with the deoxy part later. So I want to start with having those 4 carbons, right? 3, 4, and this sugar, I just chose to make it an aldose. Okay, so that was just my personal preference, so I'm gonna have this aldehyde right here. Okay, so that would be my aldose. And then if you have a regular sugar, you're just gonna have alcohol groups on all of the other carbons. Okay, so let's actually go ahead and just add those alcohol groups on every carbon right here, right? And then we fill it out with hydrogens. Okay, so every other bonds that are left shall be filled out with hydrogen. So carbon 1 is already is an aldehyde, so it's saturated. Okay, the next carbon currently has 3, so it could handle one more hydrogen. Okay, same thing for this carbon. Okay, and this very last carbon right here could handle 2 hydrogens. Okay, so deoxy, right? Term deoxy means we remove 1 oxygen, so just minus 1 oxygen. Okay, so we have this, and usually it's the oxygen on the 2nd carbon. Okay, so we have to get rid of this oxygen. Okay, and that oxygen is gonna be replaced by a hydrogen. Okay, so that should be a 4-carbon deoxy sugar, and normally it would be expressed as just an H2 here. Okay, we don't have to see that hydrogen separately connected like that. Okay, so instead of a CHOH, this changed into CH2. Problem 84, what is a fatty acid? Okay, so very straightforward. Basically, a fatty acid is just a long chain of carboxylic acid. Okay, so if you have a carboxylic acid right here, okay, then you're just gonna have a very long chain of that. Okay, so we could have maybe this is still your carboxylic acid part. Okay, and then you're gonna have that long chain with it. You could probably have some double bonds in there, right? So doesn't matter, but that is basically what a fatty acid is. Problem 85 here is asking what does it mean when we say that fats and oils are triacylglycerols? Okay, so what does that mean? So triacylglycerol is just a description of the structure of fats and oils. Okay, so this glycerol right here, so glycerol is a molecule in itself, and it looks like this. Got a CH2, got a CH, another CH2, and we got alcohol groups on all of that. Okay, so this is a glycerol molecule. Now triacyl, okay, triacyl means you have 3 fatty acids. 3 fatty acids. Okay, and as mentioned before, a fatty acid is just a very long chain of carboxylic acid. Okay, so I'm trying to draw it fast there, but that's what it looks like. Okay, and so since we have 3 fatty acid molecules, all those fatty acids would be connected to this part of the glycerol. Okay, so one fatty acid on this alcohol, one on this alcohol, and one on this alcohol. Okay, and as we react, of course, as you've probably seen in other reactions, that hydrogen is going to go away, and it's going to be connected to this carboxylic acid. So let's see what that looks like. Okay, so now that we've reacted our glycerol, that hydrogen is gone, and it's going to be connected to a fatty acid. Okay, so we'll have this one fatty acid chain right here. Okay, and then we'll have another one right here. This one's shorter and probably has a double bond. Okay, and then we have one more. Okay, so this one is a lot longer and has a lot more double bonds. Okay, so that's what it means when we say that fats and oils are triacyl glycerols. It basically just describes this general structure right here. Okay, so problem 86, we are asked to draw glycerol myristate. Okay, and we are also given its components. We are told that it has a glycerol molecule and it has 3 myristic acid molecules. Okay, which I have in here. So this is the structure of myristic acid, which I got from a table in your book. Okay, so let's go ahead and try to draw this molecule. Okay, so we're starting with glycerol. Okay, so glycerol is just 3 carbons, right? Got 3 carbons right here, and they all have an alcohol group in there. Okay, so now that we have that, we have to react this myristic acid with glycerol. And if we react an alcohol with, let me change that. So if you react an alcohol with a carboxylic acid, you'll have an ester, right? So you'll have the C right here, and then you'll have your ester just like that. Okay, so this would be the carbon where the alcohol is. Oops. This is the carbon where the alcohol is, and this is where the carboxylic acid is. Okay, so we're gonna do the same thing with glycerol and myristic acid. So let me erase these alcohol groups for now and replace them with oxygen only. Okay, and now we're connecting it to our myristic acid. So again, we're gonna have that ester, right? We're gonna have that ester right there, and then we're gonna have that CH2, and we're gonna have 12 of those, and a CH3. Okay, and since we have 3 myristic acid molecules, that means each oxygen right here is gonna be connected to that myristic acid. Okay, so CH3, and one last connection here. CH2, 12, CH3, 3. Okay, there we have it. That should be our molecule for glycerol myristate. Okay, problem 87. We are asked the structure of spermaceti, okay? And we're told that its structure is made out of cetyl palmitate, which is an ester of palmitic acid, okay? And we'll explain a little bit more of that later. And so cetyl palmitate and cetyl alcohol, which is a 16-carbon alcohol, okay? So what I have here in blue is cetyl palmitate, okay? So it's an ester of two palmitic acid molecules, okay? So palmitic acid, as you would see in your table, is a 16-carbon fatty acid. So as you could see, this is one of those palmitic acids, and this is the second one, right? This is the second one, and of course we're gonna lose some of those oxygens in the process. So this second palmitic acid right here doesn't have the oxygens connected to it originally, okay? So that is our cetyl palmitate, okay? This is the ester bond that the book is talking about, okay? So let's clear that out a little bit. Okay, and next we have a cetyl alcohol, which is a 16-carbon alcohol, okay? So it's just straight chain 16 carbons, right? So we have 15 CH2s and 1 CH3 at the end, and we'll have that alcohol group right there, just ready for our reaction, okay? So if we react an ester with, this is an ester, with an alcohol, so what's going to happen is this oxygen is going to replace this oxygen, right? And this whole group right here is basically going to be kicked out, okay? And this ester would be connected to this alcohol instead, okay? So let's go ahead and draw it down here in our page, okay? Let me use green. So we'll have the CH3. So we'll have the first part of the ester, right? CH2, 14, and then we'll have this carbonyl group right here, okay? So that is this part, okay? And we'll connect it with this part, okay? So we'll have the oxygen, and then we'll have the CH2, and we'll have 15 of those, and we'll have CH3, okay? Again, obviously this OH is gonna have to go, okay? Or this oxygen, but one of those is gonna have to go. All right, so this is actually our final structure here. This is the structure of spermaceti. For problem 88, we are asked to draw the isomers of a fat molecule, and we are given its components. So we have a glycerol, right? We have a glycerol, and we have 1 palmitic acid and 2 stearic acids, okay? So what I have on the right here are the fatty acids that we need, okay? So palmitic acid is a 16-carbon fatty acid, right? So it's this green structure right here that has 16 carbons, okay? And stearic acid has 18 carbons. It's an 18-carbon fatty acid, okay? And we have 2 of those, but this is what the structure looks like, okay? So let's just draw one for now, and let's figure out the isomer later. So starting with glycerol, okay, we got CH2, CH, and another CH2, and all of those have alcohol groups, but I'm not gonna draw the hydrogens anymore because we know that when we combine it with fatty acids, that hydrogen is gonna have to go anyway, okay? So we have 1 palmitic acid, so I want to go and just connect that with our first oxygen here on glycerol. Okay, so we're gonna have that ester bond. We're gonna have those 14 CH2s, right? CH2, and we have 14 of those, and we have CH3. Okay, and we have 2 of the stearic acids. So same thing for that. We got the ester, and then we're gonna have 16 of those CH2s, right? 16 and CH3. Okay, and we have one more. We have one more of that ester bond, and 16 CH2s and a CH3. Okay, so this is one of those. This is one of those isomers, and we have to think of the other one. And the only thing that I see that I could change here is the arrangement of our fatty acids, right? So instead of having these stearic acids right next to each other, I can move one of the fatty acids and move it on this top oxygen here, or top part of the molecule, I would say, and this palmitic acid would be in the middle. Okay, so let's try that. So again, I'm just exchanging these two. Okay, so again, starting with our glycerol molecule. Okay, I'll give us a little bit more space this time. And we have those oxygens. Okay, and we have the stearic acid first. So let's have that ester bond, right? And we have CH2, and we got 16 of those, and a CH3. Okay, and then we have the palmitic acid as our second ester bond here. Okay, CH2, got 14 of those, CH3. And finally, we have our last fatty acid, again another stearic acid. Okay, CH2, 16, CH3. Okay, and there we go, that we have our 2 isomers of this fat molecule. So problem 89 here is giving us this massive fat molecule, and it's asking for us to react it with KOH and give the products. Okay, so what we have here is a triacylglycerol. Okay, and whenever we're reacting triacylglycerol with a base, it makes a split like so. Okay, so probably not trying that, but it makes a split in this molecule, and what it does is it gives us back our components for a triacylglycerol, which is 1 glycerol molecule and 3 fatty acids. Okay, so let's go ahead and split this molecule. So we're splitting it, right? So now we're gonna have hydrogens on these oxygens, right? So these oxygens are gonna be grabbing hydrogens. Okay, so now we have our glycerol and 3 fatty acids. So let's go ahead and name our products here. So we have a glycerol molecule. Okay, and here we have an 18 carbon fatty acid. Okay, we got 16 CH2s, and we got 2 more carbons in here. So 18 carbon fatty acid with no double bonds is going to be stearic acid, right? So this is just information that you could find in your book. Okay, so that's a stearic acid. Next, we have a fatty acid with 1 double bond. Okay, so that makes it our oleic acid. Oleic acid. And finally here we have this fatty acid with 3 double bonds. So it's got 3 double bonds, which makes it our linolenic acid. Linolenic acid. Okay, so there you go. That's all our products. Problem 90. What is a nucleotide? And we have to name its 3 components. Okay, so a nucleotide is basically the monomer for nucleic acids. Okay, so monomer for nucleic acids. So nucleic acids, namely DNA or RNA. Okay, so it has 3 components, and what I have right here is a portion of a nucleic acid. Okay, so let's look at this molecule and find the 3 components. Okay, so here's one of its components. So we have a phosphate group. Okay, so we got a phosphate, and then we also have an aldopentose. Okay, so 5 carbon sugar, aldopentose. Okay, so for DNA we have deoxyribose, and for RNA we have ribose. And as you could see with this sugar, we have this oxygen right here, which tells us this is an RNA molecule. Okay, and lastly we have this amine base. Okay, so we have adenine, guanine, cytosine, thymine, and uracil for RNA. Okay, this specific one is adenine. Okay, this one is adenine, but in general we have an amine base. In general we have an amine base. Okay, so there's our 3 components. We have a phosphate, an aldopentose, and an amine base.
Okay, so for problem number 36, we're asked to identify the amino acid given the molecular model. Okay, so before we start, I want to remind everyone with the main chain for amino acids. We start with an amine group, and then we got a carbon, and then we have another carbon that is part of a carboxylic acid. Okay, so this is an amine group right here. And then this is where we would have our side chain, right? The other one would be a hydrogen. So the side chain is going to help us identify the amino acid. In fact, that's the only way we identify it when it comes to structures. Okay, so let's start with part A. Let's find that main chain, right? So here we have the blue sphere, which represents our amine group, and this would be our carboxylic acid. So that means this whole part right here would be our main chain. So that leaves us with this part being our side chain. So let's see what we have in our side chain. Okay, so we have a carbon connected to 2 hydrogens. So we have a CH2, right? And it is connected to an oxygen atom, and which is connected to a hydrogen atom. So we have an alcohol group. Okay, so we have CH2OH, which you probably remember is the side chain for serine. Okay, serine. Moving on to part B. Again, let's look for our amine group, which we see right here, and this part is our carboxylic acid, which means that this part would be our main chain for amino acid, and everything that's left would be our side chain. Okay, and in case you didn't notice, I actually didn't point it out. Here's the hydrogen atom connected to our carbon right here, right? So this hydrogen I'm boxing on the left represents this hydrogen, and same thing for part B. Here's that hydrogen. Okay, so everything outside the blue box here would be our side chain. So let's see what we have, right? We have ACH2 right here, right? And then we have another CH2, right? And then we have this yellow sphere, which represents a sulfur atom, okay? And finally, we have a CH3. Okay, so there's only two side chains with a sulfur. One would be a cysteine and one would be methionine. Okay, and as you probably remember, a cysteine would have an SH at the end, so the sulfur atom would be the very last atom. And we see here that we have a methionine because we have a methyl group after sulfur. Okay, so this amino acid would be methionine. Okay, so hopefully that was helpful.
Okay, so for problem 91, we are asked to name the sugars in DNA and RNA. Okay, so for DNA, we call the sugar deoxyribose. Okay, so deoxyribose, and I actually have the molecule right here to the right. So this right molecule is deoxyribose. Deoxyribose. Okay, so that's for DNA. And next is for RNA. We got the sugar ribose, which is actually this structure here to the left. So ribose. Okay, so what's the difference between the two? Well, there's only really one. Okay, an oxygen. That's it. Okay, so we have a ribose, right? You take away that oxygen, we call it deoxyribose. Okay, so that's the only difference. Nothing more, nothing less. Okay, and I hope that was clear. Problem 92 is asking for us to show the phosphate sugar bond in nucleic acids. Okay, so I just have the sugar here. This one is specifically ribose, and it already has the base attached to it. So now we just have to connect the phosphate group that we are missing. Okay, so there's going to be two phosphate groups attached to this molecule. Okay, so one would be here on the 5' carbon, right? So our phosphate is going to be connected to this oxygen, right? Let me actually just put it up. So this is where going to be our phosphate is. You're going to have that double bond and that single bond and so on and so forth. Okay, so this top part is going to be connected to another sugar. Okay, and then on the 3' end of this sugar, let me erase that part. Okay, so on the 3' end, which is this part, I'll go and erase our hydrogen, right? And we are going to be connecting this oxygen to another phosphate group that is going to be a part of the next nucleotide. Okay, so here we're going to have our phosphate group, right? We're going to have this double bond right here. We're going to have this oxygen with a negative charge on it, and then there's going to be another oxygen, and this is where we're going to have our 5-membered ring or our sugar. Okay, and so on and so forth. So this would be the second nucleotide at this point. Okay, but there we go. There's how phosphate is connected to our sugar here. Problem 93 is asking for us to show the sugar amine base bond. Okay, so what I have right here is a phosphate group connected to our ribose here, and we have a uracil molecule here on the right, which needs to be connected to this sugar. Okay, so this this uracil or amine base molecule is going to have to connect to the sugar, and where this arrow is pointing at is actually where this base is going to attach. Okay, so what I want to do here is to remove this OH group, right? So we're deleting that OH group and we are connecting our base. Okay, so and the part of the base that is going to connect with the sugar is the nitrogen. Okay, so this carbon right here is going to be connecting to that nitrogen. Okay, so I'm not drawing the length of the bond to scale here because of just the constraints of our drawing, but this is where that amine base is going to connect. So there you have it. So problem 94, we are given a DNA strand and we're just asked to give the complementary strand of this DNA. Okay, so just as a reminder, when it comes to DNA, G pairs with C and A pairs with T. Okay, so our first base here is a thymine, so that's going to be pairing with A pairs with T, C pairs with G pairs with C, and A pairs with T. Okay, so that should be our complementary strand. For problem 95, we are given the DNA strand and we are asked to come up with the complementary RNA strand. Okay, and so before we go ahead and answer that, let's just go over the pairings for DNA and RNA first. Okay, so when it comes to RNA, it's just like DNA, G pairs with C and C pairs with G, right? And A, unlike DNA here, when it comes to RNA, A pairs with U, which is uracil. Okay, but T still pairs with A. Okay, so this would be if you have your DNA and this is the corresponding RNA bases. Okay, so let's go for it. We have this first base here, which is thymine. So again, thymine still pairs with adenine, right? So A, however, pairs with U when it comes to RNA. C still pairs with G, just like DNA. G pairs with C, and A again pairs with uracil. Okay, so problem 96, we have polypeptide chains, right? One of them has 21 amino acids and one of them has 30 amino acids. So there we go, 21 and 30. And we are asked how many nucleotides would be needed to code for each of these polypeptide chains. Okay, so this question is actually pretty straightforward. It's pretty simple. Okay, as long as we know that one amino acid, I'm gonna abbreviate it with AA. Okay, so one amino acid is coded by 3 nucleotides. Okay, let me write that. So one amino acid is coded by 3 nucleotides. Okay, so that's just the crucial information that we have to know. But now that we know that, okay, we have 21 amino acids, and in order to calculate the number of nucleotides needed, we just multiply it by 3, right? And the same thing for 30 amino acids, we just multiply it by 3, because again, 3 nucleotides are needed for 1 amino acid. Okay, so polypeptide chain with 21 amino acids would need how many? 63, right? Needs 63 nucleotides. And following the same process, 30 amino acids would need 90 90 nucleotides. Okay? And that's it. That's our final answer for this problem. Problem 97. We have sea urchin DNA here, and we are given its composition. Okay? So we are told that adenine comprises 32% of its DNA, and guanine comprises 18% of its DNA. And we're asked to calculate the percentage of thymine and cytosine in the DNA. Okay, so before we go ahead and do that, just wanted to mention that this information is irrelevant, right? We didn't have to know that it's a sea urchin. We just had to know that we're dealing with DNA. Okay, so I think it's very important to be knowledgeable of what information you need or you don't. Okay, so anyways, so we have adenine here, and I just wanted to remind everyone that adenine pairs with thymine when it comes to DNA, and guanine pairs with cytosine. Okay, so it's safe to assume that since A pairs with D and G pairs with C, A here is always going to have the same amount as D, right? For every A that you have in your DNA, you have the same amount of thymine. Okay, so if A comprises of 32%, then it's only logical to think that thymine would also comprise of 32% of DNA, right? And following that same logic, because guanine occupies 18% of the DNA, then every guanine would have a cytosine associated with it, then cytosine should also occupy 18%. Okay? And if you want to verify that information and see if you got the right numbers, you could go ahead and add all the percentages that we have, and all of these should total to 100%. Okay?
Let's draw the following compounds. For A, we have 2-methylheptane. So this would be a heptane, CH3, and a methyl group at carbon 2, carbon 3, carbon 4, carbon 5, carbon 6, 2, 3, 4, 5, 6, carbon 7 for the heptane parent, 2-methylheptane. For B, 4-ethyl, 2-methylhexane, this would be CH3, CH, carbon 2, there's a methyl group, CH2, CH, carbon 4, there's an ethyl group, carbon 5, carbon 6. So there would be 4-ethyl 2-methylhexane. For C, we have 4-ethyl 3,4 dimethyl octane. So carbon 1, carbon 2, carbon 3, so methyl group, carbon 4, there's a methyl group and an ethyl group, carbon 5, carbon 6, carbon 7, carbon 8. For D, 2,2,4 trimethylheptane, CH3, carbon 2, there are 2 methyl groups, CH, or sorry, 2, 4, 4. Let's go backwards. Not 2, 2, 4. 2, 4, 4 trimethylheptane. So CH3, CH, so 1 methyl group, CH2, carbon 4, there are 2 methyl groups, carbon 5, carbon 6, carbon 7. There's my heptane 7 carbon parent. For E, we have 1, 1 dimethyl cyclopentane. So draw cyclopentane, 5 carbon ring, carbon 1, 2 methyl groups. So there's 1, 1 dimethyl cyclopentane. And for F, we have 4 isopropyl, 3 methylheptane, and this would be CH3, CH2, CH, carbon 3, we have a methyl group. Carbon 4, we have an isopropyl group. Carbon 5, carbon 6, carbon 7. And there would be 4 isopropyl, 3 methylheptane. Let's provide the IUPAC names for the following alkanes. For A, we have 2, 3 dimethyl hexane. For B, we have 4 isopropyl octane. For C, 4 ethyl, 2, 4 dimethyl hexane. For D, 3, 3 diethyl pentane. And for, no, there is no E, we'll end with D. So there are our IUPAC names for the following alkanes.
Alright, so problem 100, we are asked to draw the structure of carnauba wax, okay? And we are told that its composition is made of a C32 straight chain alcohol and a C20 straight chain carboxylic acid, okay? So we're making an ester out of those components. And before we go do that, I just wanted to remind everyone of what the basic structure of this would look like, okay? So let's say we have this carboxylic acid, right? We got carboxylic acid and it's connected to an alkyl group, which I'm just going to label R1, okay? So we have this carboxylic acid right here, just like that. And then we have an alcohol right there with R2, okay? So if you combine these into an ester, we are gonna get a structure that looks like this. Okay, so this would be our ester, and this would be the R2, okay? So we see that we kind of combine these two alcohol groups into just one oxygen, okay? So following that pattern, let's go ahead and start drawing our C20 carboxylic acid. Okay, so I want to go ahead and start with this one, starting with the carboxylic acid. Okay, so C20, so let's start with ACH3, right? And then we're gonna have 18 CH2s in between. We got 18, so that's a total of 19 right now, and we'll have that 20th carbon as a carboxylic acid. Okay, so since we already know what base structure we're looking for, I'm gonna go ahead and start drawing the alcohol connected to it already. Okay, so I'll be drawing this C32 straight chain alcohol. Okay, so this would be the alcohol part. We got 32 carbons, so we're gonna have 31 CH2s, right? We're gonna have 31 of these, 31, and then the 32nd carbon would be a CH3. Okay, so as you see, this follows our pattern that we established earlier. Okay, so hopefully that was clear.
Let's draw the 3 resonance forms of naphthalene. So one resonance form would be placing the double bonds in this configuration here. Second resonance form would be placing the double bonds in this configuration here. And the third resonance form would be placing the double bonds in this configuration here. So these would be the 3 resonance forms of naphthalene. Let's solve for the minimum molar mass of this enzyme cytochrome C. So we're told that cytochrome C is 0.43% iron. So if we assume that we have 100 grams of cytochrome C, that would yield 0.43 grams of iron. So starting from 0.43 grams of iron, let's solve for the moles. So this would be molar mass, 55.85 grams of iron in 1 mole of iron, and this would yield 0.0077 moles of Fe. Now we're going to assume that this is the minimum molar mass, that each cytochrome C has at least 1 Fe atom present. So we'll assume a 1-to-1 mole ratio. Therefore, if we found that 0.0077 moles of iron, and if it's a 1-to-1 mole ratio, we'd have 0.0077 moles of the cytochrome C. And so the molar mass for for cytochrome C would be equal to the 100 grams that we assumed divided by the 0.0077 moles, and therefore this would yield a molar mass of, now 2 sig figs, 1.3 times 10 to the 4th grams per mole. Let's write a full structure of the following peptides. So we have valine, phenylalanine, and cysteine, and then we'll also indicate the position of the amide bond. So we're going to have NH2, CH, CH3, CH3, C double bond O, and H, CH, CH2, and aromatic ring, C double bond O, and H, CH, CH2, SH, C double bond O, OH, and our amide bonds would be here and here. So these would be where the amide bond is formed. For B, we're going to have the polypeptide glue, pro, ILE, and U. So here's our peptide. So we've got NH2. I'm going to do this one fairly small to make it fit. CH, CH2, CH2, COOH, C double bond O, N, CH. This would be structure here. C double bond O, and H, CH, CH, CH2, CH3, CH3, C double bond O, and H, CH, CH2, CH, CH3, CH3, C double bond O, OH. So the amide bonds here, I am going to just outline them. We have an amide bond here, we have an amide bond here, and we have an amide bond here. There are 3 amide bonds joining the amino acids together. For A, let's write the representative structure for a fat. We have CH2, CH2, O, C, double bond O, CH2, CH2N. Now we can have a long chain here of a long carbon chain. O, C, double bond O, CH2, CH2N, CH3. So again, a long carbon chain there. O, C, double bond O, CH2, CH2N, CH3. So there would be kind of a representative structure for a fat. For vegetable oil, is going to look very similar. CH2, CH, CH2, O, C double bond O. Now there's going to be some unsaturation here. So we could have a long chain, CH, CH double bond here, and this could yield another, so we can have different levels of unsaturation in a sample of vegetable oil. CH double bonds present. So we can have these double bonds in these long carbon chains, and that would be kind of a representative structure of vegetable oil. And for C, we're looking for a general structure for an aldotetrose, and an aldotetrose would have a structure C double bond O H, C O H H, C H H O, C O H H, and H. So there would be kind of a representative structure for an aldotetrose.
Problem 104, we are given a DNA strand and we are asked to come up with the complementary DNA strand. Okay, so just to refresh everyone's memory, when it comes to DNA, G pairs with C and vice versa. C also pairs with G, and A pairs with T and vice versa. Okay, so let's go for it. We got A and that pairs with T, G pairs with C, T pairs with A, C pairs with G, A pairs with T, T pairs with A, C pairs with G, and finally we got G pairs with C. Alright, problem 105, we are asked to draw the structure of jojoba wax, right? And we are told that the structure of this wax is an ester. It's an ester of stearic acid and a C22 straight chain alcohol. Okay, so if you look back to your table in your book, you'll see that stearic acid is a C18 straight chain carboxylic acid. Okay, so I want to go ahead and start by drawing that stearic acid. Okay, so C18, so we're starting with CH3, and we'll have 16 CH2s in between. Got CH2, we got 16 of those, and our final carbon is going to be that carboxylic acid. Okay, OH. Okay, so just as a reminder as well, whenever we have a carboxylic acid and an alcohol, and we react them as an ester, we're gonna end up having a molecule that looks like this. Okay, so this would be the carboxylic acid, and this would be the alcohol. Okay, so following that pattern, I would go ahead and delete this hydrogen right here and draw that C22 straight chain alcohol, so this part, right? So we have 21 CH2s, right? We have 21, and that 22nd carbon, since we have C22, would be a CH3. Okay, so we could count the carbons just to confirm, but this should be the final structure for jojoba wax. Alright, problem 106. So we are given this molecule, methylphenidate, okay, and we are asked to do two things. One is to identify the function groups, and second is to predict the products after reacting it with an aqueous base. Okay, so let's start with the function groups. That should be pretty straightforward. Okay, right off the bat we see this huge aromatic ring right here. So we have this benzene ring, so that would be our aromatic function group, right? And we also see this nitrogen, right? See this nitrogen right here, so that makes it our amine, right? We don't see any carbonyl carbon next to it, so that should be our amine group. And finally we have this carbonyl group right here, and as you notice, it is not connected to hydrogen, but it is connected to a CH3 group, so that makes it our ester. Okay, so let me write our function groups over here to the left so I could erase what we have in there. So got aromatic, we got amine, and we have an ester. Okay, so we are going to react this molecule with an aqueous base, so I'm going to need all this space, and I need to clear all of that writing. Okay, so what we have here is an ester. Okay, we have an ester. So just like what we have when it comes to fatty acids or triacylglycerol, whenever we react an ester with an aqueous base, it makes a split down this oxygen, right? And it gives you a carboxylic acid on this side and an alcohol on this side, right? So what I'm going to do here now is to make that split, right? So let me erase, I'm going to erase this methyl group right here, right, and replace that with an oxygen, or I'm sorry, a hydrogen. Okay, so that would be the carboxylic acid side of this molecule. And since we deleted that methyl group is going to have its own alcohol connected to it. Okay, and there you go. So these are our products after reacting this molecule with an aqueous base. We have a carboxylic acid and we have an alcohol. Okay, so problem 107, we are asked to draw the line bond structure of these two molecules, oleic acid and elaidic acid. Okay, so starting with oleic acid, a couple of things that we need to do, or we need to know, is that one is it has 18 carbons. Okay, it is a cis isomer, and the double bond is on carbon 9 and 10. Okay, and oleic acid is the trans isomer of oleic acid, so that double bond is also in C9 and C10, but it is in trans isomer, okay, or trans configuration. So let's start with drawing our oleic acid. So I always, whenever I draw fatty acids, I always want to start with the carboxylic acid. Okay, so that's our carbon 1, and this is our carbon 2, right? 2, 3, 4, 5, 6, 7, 8, 9. Since this is our 9th carbon, we want to go and do that cis configuration. So carbon 10, 11, 12, 13, 14, 15, 16, 17, and 18. And of course that double bond is going to have to be here. Okay? So this should be our oleic acid. And next, we are drawing the trans isomer of the exact same molecule. Okay? So again, we're starting with carboxylic acid. That's carbon 1, and this is carbon 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And I believe, actually, let me just go ahead and count. Got 1, 2, 3, 4, 5, 6, 7, 8, and 9, and 10. Okay, so our double bond has to be between carbons 9 and 10. And there you have it. That should be our oleic acid.
Let's solve for the empirical formula of fumaric acid. We're going to assume 100 grams, which will yield 41.4 grams of carbon, 3.5 grams of hydrogen, and 55.1 grams of oxygen. Let's convert all of these to moles. 12.011 grams of carbon in 1 mole will yield 3.45 moles carbon, and 1.008 grams of hydrogen in 1 mole will yield 3.5 moles of hydrogen, and 16.00 grams of oxygen in 1 mole will yield 3.44 moles of oxygen. Divide by the least, which is 3.44, and the nearest whole number ratio would be 1, 1, and 1. Therefore, our empirical formula for fumaric acid will be CHO. For B, we're asked to find the molecular mass. So for B, let's first solve for the molarity by rearranging the formula for osmotic pressure. We're given the osmotic pressure at 240.3 millimeters of mercury, but we have to convert this to atmospheres, and 1 atmosphere is equivalent to 760 millimeters of mercury. And in the denominator, ideal gas constant, liters, atmospheres per mole Kelvin, and told the temperature here is 298 Kelvin. Therefore, the molarity here will work out to 0.0129 moles per liter. And now we can find the moles of fumaric acid. The moles would be equal to C times V. Concentration we just got 0.0129 moles per liter times the volume. We're told that we have a volume of 100 milliliters, so this is 0.1 liters, so our moles will be 0.00129 moles. And now we can calculate our molar mass, which will be equal to, we have 0.1500 grams of the fumaric acid over the 0.00129 moles, and this will yield a molar mass that's equal to 116 grams per mole. So there's our molar mass for the fumaric acid. For C, we're asked to draw 3 possible structures. We first have to calculate the molecular formula before we draw the structures. So N, molar mass, divided by empirical mass. Molar mass, 116 grams per mole, we just calculated. The empirical mass, which is based on our empirical formula, CHO, which is 29 grams per mole. This will work out to 4. So that's our whole number ratio. So our molecular formula for fumaric acid is equal to 4 times CHO, which will be equal to C4H4O4. So our 3 structures that we can come up with here, structure number 1 would be structure here. So there's one structure, second structure. And our third structure is going to be OH, C, double bond O, C, C, O, OH, double bond CH2. So there's our 3 structures for fumaric acid. And for D, we're told that if it contains a trans double bond, so fumaric acid contains a trans double bond. Therefore, from part C above, structure 2 is correct. For A, we're asked which group is more acidic. So the pKa for the carboxylic acid group is equal to 2.34, and the pKa for the NH3 plus group is equal to 9.69. So the group with the lower pKa is more acidic. Therefore, the CO2H group is more acidic. For B, what percentage of each form is present at pH 4. So we've got H2A plus, and this would be represented by pKa1, which is equal to 2.34 to H2A, or sorry, that would just be HA, and this would be A minus pKa2, which would be pKa of 9.69. At a pH equal to 4, the predominant species are H2A plus and HA, as the pH is closest to pKa1. So we'll have to use the Henderson-Hasselbalch equation here, which is the pH is equal to the pKa plus the log of HA over H2A plus. The pH is 4, the pKa is 2.34, plus the log of HA H2A plus. So the log of HA over H2A plus is equal to 1.66. Solve this mathematically here. HA over H2A plus would be equal to 10 to the 1.66, which would be equal to 46. Let's write this as ratio. It would be 46 over 1. Therefore, the percent of HA would be equal to 46 over 46 plus 1 times 100%, and this would be equal to 98%, and the percent of concentration, and then the percent of the molarity of H2A plus would be equal to 1 plus 46 plus 1 times 100% according to the ratio, and this would be equal to 2.1%. So there would be the percentage of each at a pH of 4. For C, at a pH equal to 8.50, the predominant species are HA and A minus, as the pH is closest to pKa2. So let's apply the Henderson-Hasselbalch equation again. pH is equal to pKa plus the log of A minus over HA. The pH is going to be 8.50. pKa is 9.69 plus the log of concentration ratio, the log of A over HA minus over HA would be equal to minus 1.19, and so the ratio here, A minus over HA, is equal to 10 to the minus 1.19. Solving this, we will get this is equal to 0.065 over 1. Now, using this ratio here, the percent of A minus would be 0.065 over 0.065 plus 1 times 100%, and this would work out to 6.1%, and the percent of HA would be equal to 1 over 0.065 plus 1 times 100%, and this would be equal to 94%. For D, at what pH is the neutral form present in maximum amounts? So the neutral form would be present when we average the pKa values. So the pH is equal to the pKa1 plus pKa2, and divided by 2 would give us the average there. So this would be 2.34 plus 9.69 over 2. And solving this, we get a pH that's equal to 6.01. Therefore, the maximum amounts of the neutral form of the amino acid is at a pH equal to 6.01. For A, let's calculate the mass of the iodine. Starting from, we have 25 milliliters, which will be 0.0250 liters, times the molarity, which we're given as 0.2 moles per liter, times the molar mass. 1 mole of iodine has a molar mass of 253.8 grams, and this would yield the mass of I2, which would be 1.27 grams. For B, let's calculate the mass, or the mass of I2 reacted and how many grams are in excess. To do so, we'll need the balanced equation, and the balanced equation is 2Na2S2O3 plus I2 to produce 2NaI and Na2S4O6. And first, let's find the moles of the Na2S2O3. And we're starting with 81.99 milliliters, so 0.08199 liters. And the molarity is 0.1 moles per liter. This will yield 0.008199 moles of the Na2S2O3. Now, using the balanced equation and the stoichiometry, 0.008199 moles of the Na2S2O3 times 2 moles of the Na2S2O3 to 1 mole of I2. And moles of I2 we can find are going to be equal to we'll carry some extra sig figs here. 0.00409995 moles of I2. And now let's find out the mass of I2, which will be reacted, will be equal to 0.00409995 moles of I2 times 1 mole of I2 has a mass of 253.8 grams of I2, and this will yield I2 reacted of 1.04 grams. So that's the first part of the question. And then the mass of I2 in excess will be the starting amount, which is 1.27 grams minus the 1.04 grams. So this will yield 0.23 grams of I2 that would be present in excess. For part C, the iodine number in human milk fats would be equal to the mass of I2 times the mass of the fats times 100%, or just times 100. So we found that we have the 0.23 grams of I2 present in excess, and we have 0.500 grams of the fat times 100. So the iodine number works out to 46. And lastly, assuming a molar mass of 800 AMU, how many double bonds does an average molecule of milk fat contain? So let's first, for D, using the molar mass, let's calculate the mole of fat. So we have 0.5 grams and the molar mass is 800 AMU, or 800 grams per mole. So we can find that this is equal to 0.000625 mole of the fat, and we can find the mole of iodine present in excess, which would be 0.23 grams over 253.8 grams per mole is its molar mass. So this would be equal to 0.00091 moles of I2. And so the mole ratio between I2 and the fats would be 0.00091 over 0.000625, and this would yield a ratio of 1.4. So the average molecule of milk fat contains 1.4 double bonds.
Okay, so problem 38, we are asked to identify the dipeptide. Okay, so the only thing we want to do here is to find our R group, or our side chain, and identify the individual amino acids. Okay, and the way we do that is to find the main chain first. So again, I just want to remind what the main chain for amino acid is. So we have an NH2, we have a carbon and another carbon that is part of a carboxylic acid, right? And then we'll have that R group sticking out of it, and this is what we're interested in. Okay, of course there's that other hydrogen connected to that. All right, so our amine group is represented by a blue sphere. Okay, so that represents the nitrogen. So we see our nitrogen atoms here, and we have to find that carboxylic acid. Okay, so we see that there's this amine group right here, and this is the carbon that is double bonded to an oxygen, and we don't see the carboxylic acid part anymore, because once you get a dipeptide, you will have this amine group from the other amino acid connected to it. So this is still our backbone for the first amino acid, right? So this part right here, and then we continue on with the second amino acid. This would be the amine group for it, right? And there's our carboxylic acid right there at the end. Okay, so now everything I have outside the blue box would be our R group. Okay, so this is our first R group, this is our second R group. Okay, so our first R group has a CH2 connected to an OH, right? This is an oxygen atom. So that is the R group for serine, right? And the second R group right here, we see that we have a, let me try to highlight it. This part right here, we have a CH. Okay, so we have a CH, and then it's connected to two methyl groups. Okay, it's connected to two methyl groups, so CH3, and this R group is very characteristic of valine. Okay, the way I want to remember that is that it looks like the letter V, right? So this R group kind of looks like a letter V, which stands for valine. Okay, so let's rewrite that into our dipeptide. So I think we're asked to use the 3-letter abbreviations as well. So we're going to have SER for serine and VAL for valine. So this would be our final answer. Okay, so problem 39 is asking for us to identify the amine base. So the molecular models given here are bases that can be found in nucleic acids. Okay, so starting with part A here, we see that we have 2 rings in our structure. So whenever you have 2 rings, you could only have A or G. Okay, and what's our telling feature here is this carbon double bonded to oxygen, okay, and also this amine group right here. But more so, at least for me, this is what I looked for. Okay, so whenever I see 2 rings with a carbon double bonded to oxygen, that tells me that it is guanine. Okay, so that one is guanine. And of course, you have to make sure that you actually have a base that can be found in nucleic acid. Okay, so moving on to part B. Okay, part B, we have 1 ring only, right? So that tells us we could have C, T, or U. Okay, remember we have that uracil for RNA. Okay, so right off the bat, we got just 1 carbon double bonded to oxygen. Okay, so we only have 1 carbonyl group, and the other one is a amine group. Okay, so whenever you see this this combination of functional groups, then you know that you have cytosine. Okay, you have cytosine. And I say that because thymine and uracil both have 2 COO bonds. Okay, so you're gonna see 2 of these if you have thymine or uracil. Okay, so that would be our answer for 39.
In this problem, we are given with a galvanic cell, and we are given the shorthand notation for the galvanic cell, and we are asked to find out the balanced equation for the overall cell reaction, and we have to give a brief description of the galvanic cell, which is represented by that shorthand notation. So let's write down the shorthand notation first, and it is like this. Lead metal is oxidized to lead 2 plus ion, and here bromine, liquid bromine is being reduced to bromide ion, and by this platinum, we mean that this is the electrode for the cathode. To write down the overall cell reaction, first let's write down our half cell reaction for anode and cathode. So the anode half reaction will be for this one. So in this case, lead metal will be converted to lead 2 plus ion by releasing 2 of its outermost shell electrons, and this will be our, or this is our anode half reaction. And the cathode half reaction will be the conversion of bromide ion from liquid bromine. So the reaction equation will be liquid bromine taking those 2 electrons from the anode half reaction, and it will be converted into 2 bromide ions. So this is our cathode half reaction. So now we know our anode half reaction and cathode half reaction, and for the overall cell reaction, all we have to do is to sum up these 2 equations. So if we sum up these 2 half equations, we'll get the full or overall equation, and from here we can easily see that if we add them up, these 2 electrons and these 2 electrons will cut off, and the overall reaction will be so this is our overall cell reaction for this. And now we are asked to describe the galvanic cell, which is represented by this shorthand notation. So to represent or to describe the galvanic cell, we can draw the galvanic cell real quick. So if these 2 are our compartments, and if this is our anode compartment, this is our cathode compartment, we'll have 2 metal strip as anode and cathode. So in this case, our anode is a lead strip, so this is our lead anode, and the cathode is a platinum wire, which is mentioned by this PT here. So the cathode is platinum, and there will be a wire connection, 2 of them, and the electron will be produced here in the anode when these lead metals will produce lead ion and electron, and these 3 electrons will go this way, come here, and they will reduce the bromide to, they will reduce the liquid bromine to bromide ions, and here is the galvanic cell for this cell notation.
In case of lithium chloride, it ionizes, it forms lithium ion and chloride ion. 2 lithium chloride gave 2 lithium ion and 2 chloride ion. In case of inert electrode, the following reaction take place at anode. Oxidation take place, so the chloride ions form chlorine molecule and release 2 electron. On the other hand, at cathode, the lithium ion gain the electrons and form lithium. In case of copper sulfate solution, when it oxidizes, it forms copper ion and sulfate ion. The following reaction take place when the electrodes are inert electrodes at anode. Oxidation of the water molecule take place, where water molecule form oxygen, hydrogen ion and release 4 electrons. On the other hand, at cathode, 2 copper ions gain these 4 electrons, forming copper atoms. In case of potassium chloride sulfate, when it ionizes, it forms potassium ion and sulfate ion. At anode, using inert electrodes, at anode oxidation of the water molecule take place. Water form oxygen, 2 hydrogen ion and release 2 electrons. The potassium ions at cathode gain these 2 electrons, forming potassium atoms. The overall cell reaction in each case can be written by adding the anodic and cathodic half reaction. So we can, in case of lithium chloride, we can cross the electron on either side, so we can say that 2 chloride ions react with 2 lithium ions, forming chlorine gas and 2 lithium atoms. In case of copper, we can cross the electrons on either side, so we can write that 2 water molecule react with the 2 cupric ions, forming 2 copper atoms, an oxygen molecule and 4 hydrogen ions. In case of potassium sulfate, adding the 2 reactions, we can cross the electron on either side, so we can write that a water molecule react with the potassium ion, forming potassium atoms, oxygen gas and 2 hydrogen ions. And silver plating, silver is made the anode, and at anode the oxidation of the silver take place, where silver oxidizes to silver plus ion and electrons is released. On the other hand, at cathode, the same silver ion move from the anode toward the cathode, where it gain electron back and is reduced to silver metal. This is the electrolytic cell Electroplating cell for the silver. The anode is made up of silver, where oxidation takes place. Silver oxidizes and move toward the solution in the form of Ag+, while it moves toward the cathode. When the silver ion moves toward the cathode has negative charge, while anode has positive charge. So a non-spontaneous reaction takes place by the help of electric current or voltage supplied by the source. There is external source which supply the voltage. The silver spoon has negative charge over it. When the silver ion from the solution move toward the silver spoon, it reduces and a uniform coating of silver is formed over the silver spoon. AgNO3 silver nitrate is used as electrolyte in the electroplating cell of the silver. We can say a total n number of silver oxidizes, giving n number of electrons, where again the n number of silver reduces and form a uniform coat over the silver spoon.
So we're given a mixture of aluminum and cryolite. Okay. You have aluminum, then you have cryolite. Is a mixture. Then you're told that a current of 1 times 10 to the power 5 coulombs is passed for 8 hours. Okay. And remember, this time needs to be in seconds. Okay. So automatically, we need to can get the charge that was used. Okay, because charge is given as current multiplied by time. This time needs to be in seconds. Okay, so that means that this is going to be 1 times 10 to the power 5 multiplied by 8 hours multiplied by 60 to convert them into minutes, then again by 60, convert these into seconds. Okay, so this is going to be around 2.8 times 10 to the power 9 coulombs. This is a lot of charge for that particular electrolysis reaction. So from here you can get moles, because we know that from Faraday's constant, we know that 1 mole of electron equals 96,500 coulombs of charge. So we need to get how many moles of that were used for this particular reaction. Okay. So when you do the math, so we're going to equate about 2.8 times 10 to the power 9 coulombs of charge. So when you cross multiply, we're going to get that the most moles of electrons that were used here 22.9844 times 10 to the power 4 moles. Okay, but when you look at half cell reaction for this aluminum, you know that 3 moles of electrons were needed to for this reaction. So aluminum is going to gain 3 electrons so that we deposit aluminum metal. So this is what we need to find out, how much of this was deposited. That means we're going to divide this number of moles for by 3 electrons each, so that we get how many is for this particular reaction. That means we're going to have moles of aluminum used. So are going to be 2.9844 multiplied by 10 to the power 4 multiplied by 1 mole of aluminum divided by 3 moles of electron. So this is going to give us around 9,948.18 moles. Okay, these are just moles that we used to. So we have moles and you have gram of aluminum. Remember, gram of aluminum is metal is 26.98 grams per mole. That means when you want to get mass that we asked in kilograms, we're going to multiply gram, relative atomic mass, multiplied by the number of moles. So ram is going to be 26.98 grams per mole. Okay, multiplied by 948.18 moles. So per mole and moles are going to cancel out so that you get mass in grams. And this is going to be 268,418.62 grams. This when you divide by 1000 for convert them into kilograms, we're going to get around 268.42 kilograms of aluminum that will be deposited here. So there's a procedure for this particular question. So in this video, we are given silver, element silver. Okay. Then we are told that this silver is electrolyzed with the current of current is 0.1 amperes. Okay. This current is too small that it will take a lot of time for us to deposit a mass of 3 grams. Okay, it will take a very long time for us to deposit a mass of 3 grams with this current. It's very small. 0.1 is very, very small. Okay, but then we also need to understand that silver has a ram of 108 grams per mole. Okay, so we need to find out how many moles this mass of this particular per mole. Okay, we need to find out how many moles of silver are we talking about. Okay, so we're going to use the moles to divide the mass that is deposited. Okay, by the relative atomic mass, grams per mole. Okay, so this is going to give us around 0.02778 moles. Okay, this is just the moles of that are deposited, but then we understand also that 1 mole of electron gives us the Faraday's constant, which is 96,485 coulombs of charge. Okay, so we need to find out how much charge these particular moles that are involved give us. Okay, so about 0.02778 moles. How much charge are these going to give us? So when we do cross multiplication, you're going to get that this is same as saying 96,485 coulombs or ampere seconds multiplied by 0.02778 moles. Okay, divided by 1 mole of electron. Okay, this is going to give us around 2,000. Okay, 2,680 coulombs. But then we understand that charge in coulombs is the product of a current and time. So if there's a case, we're going to substitute that. So current multiplied by time. In this time should be in seconds. Okay. So the current we're given here is 0.1 amperes, and time, we don't have time. So we need to find time. Yeah, we find this. So we equate this equation so that we have 2,680 coulombs should be a product of 0.1 multiplied by a time in seconds. That means that our time is going to be 2,680, all right, divided by 0.1, which equals to around 26,801 seconds. So when you divide this by 1 hour, okay, when you divide this by 1 hour, you know that 3,600 seconds, we're going to get around 7.5 hours. So you see, for this current of 0.1 amperes, we really need a lot of time to deposit 3 grams of silver. So the time that is required is around 7.5 hours.
While anodizing titanium at anode, the oxidation of titanium take place where it form TiO2 plus 4 hydrogen ion and 4 electrons are released, where the oxidation potential of the titanium is 1.066 volt. On the other hand, at cathode, the reduction of hydrogen take place where 4 hydrogen ion gain 4 electrons, forming 2 hydrogen molecule. As we know that the reduction potential of the hydrogen is 0. So in writing the overall equation, we can write that titanium react with 2 water molecule. Here we can cross the hydrogen ion and the electron on both sides of the reaction, so it form titanium oxide and hydrogen gas is formed. Overall potential of the cell is the sum of the oxidation potential and reduction potential. So the sum of oxidation and reduction potential is 1.066 volt. As we know that the thickness of the layer of aluminum oxide is equal to 0.01 millimeter. To change it into centimeter, so we will divide it by 10, so it will be equal to 0.001 centimeter. The length of each edge is equal to 10 centimeter, so the area is equal to L square, so it is equal to 10 centimeter square. So the area of the sheet is 100 centimeter square. To get the volume, so volume is equal to area multiplied by thickness. So the area of the sheet is 100 centimeter square, where the thickness is 0.001 centimeter. So we get the volume 0.1 centimeter cube. This is the volume of the thin coat of aluminum oxide deposited over the plate. So as we know that the density of Al2O3 is equal to 3.97 gram per cm cube. To measure the mass of aluminum oxide, so we will multiply density with the volume. So the density is 3.97 gram per cm cube, where the volume is 0.1 cm cube. We can cross the cm cube with cm cube and multiplying 3.97 with the 0.1, so we get 0.397 gram. This is the mass of a layer of Al2O3 deposited over the sheet. Now we know that by Faraday law, we know that mass is equal to Z into Q, where Q is equal to I, the current applied, multiplied by T for the time. So it is the product of current into time, where Z is equivalent mass or mass equivalent divided by Faraday constant. So we can write that M is equal to E, equivalent mass, divided by Faraday constant, multiply by ampere current, multiply by time T. We also know that mass equivalent E is equal to molecular weight of the substance divided by N. So we can write that, rearranging the equation for the T, we can write that T is equal to mass first of all putting for the equivalent mass, we can write that M is equal to molecular weight of the substance divided by N into F multiplied by I into T. To determine the T, we will rearrange the equation, so we can write that T is equal to mass into N into F divided by molecular weight of the substance multiplied by current in amperes. As we have given the sheet of aluminum, so Al2O3 has molecular weight 102 gram per mole, where where in case of the reaction between aluminum and oxygen, so there is Al2 and aluminum has 3 plus charge, so it has lost 6 electron, therefore N is equal to 6. Faraday constant F is equal to 96,500 coulomb per mole of electrons, where the current I is given 600 ampere. Putting these values, so we can write that M is equal to 0.397 gram, where N is 6 mole of electrons. Faraday constant is equal to 96,500 coulomb per mole of electrons, where molecular weight is 102 gram per mole, and the current is 600 ampere. So calculating the above equation, we get that the time is 3.75 minutes. For an electrochemical cell which consists of lead and zinc electrodes, so there is zinc and lead electrodes, and this cell, as we know, at anode oxidation take place, and the oxidation potential of the zinc is greater than the lead, so the zinc will oxidize to Zn2 plus, will release 2 electrons, where the at cathode the lead ion Pb2 plus will gain the electron and will reduces to lead, because lead has greater reduction potential while zinc has greater oxidation. So we can write the overall reaction like that: zinc react with lead ion Pb2 plus, forming Zn2 plus and lead. So the zinc oxidizes where the lead is reduces. So this is a galvanic cell showing the two half cells. One is oxidation half, the second is reduction half. In oxidation half there is zinc electrode dipped in the zinc solution, so zinc will oxidizes and form Zn2 plus. So this is anode, and oxidation take place over here. Zinc will leave electron at the electrode, so here anode has negative charge on it because the cell is galvanic cell. On the other hand, there is reduction in the second half, so the reduction of the lead take place, so lead from the solution move toward the electrode. Pb2 plus gain electron and deposited in the form of Pb, so there is positive charge over the cathode. The electron will move from the anode toward the cathode. This is the flow of electron. There is a salt bridge made of sodium nitrate NaNO3. So the nitrate ions will move toward the oxidation half, while the sodium ions will move toward the reduction half. So this is the diagram for the galvanic cell showing the oxidation of zinc and reduction of lead.
In this problem, we are given with a galvanic cell, and we can see the galvanic cell here in this image, and we have 4 parts of this question. In the first part of this, we are asked to complete the drawing by adding any components essential for a functioning cell. So here we can see that we have 2 compartments, and we can assume that one of them is anode and one of them is cathode, and the anode and cathode are not leveled here, and we have to level that, and that's another part of this problem. But let's first complete the drawing by adding the essential part, which is a salt bridge. So without a salt bridge, a galvanic cell is incomplete, because in that case there will be an imbalance of the ions in 2 of the compartments, and that will create a short circuit of the cell, and it will eventually end up producing any more electron or current. So for the salt bridge, we actually add a U-shape tube here, and in this U-shaped tube we have an inert electrolyte solution. In this case, since we already have nitrate ions in the cell, so we can use any nitrate solution, and in this case we will use sodium nitrate. So we can write down sodium ion and nitrate ion, that will this salt bridge. So that's the essential part we are missing in this galvanic cell. Now in the second part, we are asked to level our anode and cathode. So from here, so we have to identify the anode and cathode. We can identify that from the flow direction of the electron. So from here we can see that the electron is flowing in this direction, and we know that electrons always go from anode to cathode since electrons are being produced in anode. So we can say that our aluminum strip here is our anode, and our cobalt strip here is our cathode. So these are anode and cathode, and we are also missing the sign of the anode and cathode. And as we know that electrons are being produced in anode, that means the sign for the anode will be minus, and since the charge for the cathode is plus, we have to put a plus sign here. We are also asked to indicate the ion flow direction. So since our electron is moving in this direction, these electrons will go here to neutralize cobalt 2+ ions. The cobalt ion will go in this direction, and at the same time producing electron here in this aluminum strip, and the aluminum Al3+ ions are being released to the solution here. And the aluminum ions go through this salt bridge here, and they come in a direct contact with the cobalt ion. In that case, we will not have the electron flow in this direction. So we have to prevent this aluminum ion from going through this salt bridge, and for that our nitrate ions from this salt bridge will come down in this direction, and those nitrate ions will react with aluminum to neutralize them or to keep them in the solution. The direction for the nitrate ion will be in this direction, and for the aluminum ion it will be in this direction. In our part C of the question, we have to write down a balanced equation for the cell reaction. So first we have to write down the anode and cathode half reaction. So our anode half reaction with the oxidation of aluminum metal. So aluminum metal will become Al3+ ion by giving up its 3 electrons, and our cathode half reaction will be cobalt 2 plus will take up 2 electrons to become neutral cobalt. So this is our anode and cathode half reaction, and but to write down the overall cell reaction, we have to have a balance in our number of electrons in cathode and anode half reactions node. And from here you can see that to make them a same number, we have to multiply the anode half reaction by 2, and we have to multiply the cathode half reaction by 3. 2L 3 plus 6 electron, have 3 CO2 plus 3 times 2 6 electron, and 3 cobalt. So now we have 6 electron in both cases, and add these two equations up, and when adding up we'll have these 6 electrons, and these 6 electrons will cut off, and the overall cell reaction will be 2 aluminium plus 3 CO2 plus equal to 2L3 plus 3 cobalt. So that's our overall cell reaction. And finally, if we have to write down the cell notation for this, so our anodic half reaction will be aluminum metal being converted into Al3 plus, and we have to give this vertical line in between these two to separate their phase. So this is our anode half cell, and then we will place the salt bridge notation in between anode and cathode, and then we'll start writing down the cathode half cell, and that will be our cobalt 2 plus in aqueous form, phase change to cobalt, solid cobalt. And this is our cell notation for this galvanic cell.
For a cell notation where copper oxidizes into Cu2 plus ion and it come towards the 1 molar solution. On the other hand, iron Fe2 plus in 1 molar solution, Fe3 plus in 1 molar solution, Fe3 plus in 1 molar solution reduces to Fe2 plus in 1 molar solution at platinum electrode. So in this, at anode, as we know, oxidation take place, so the copper oxidizes into Cu2 plus, releasing 2 electrons. On the other hand, at cathode, reduction take place, so 2 ferric ions Fe3 plus gain the 2 electrons released by the copper, and it change into 2 ferrous ion Fe2 plus. As the E oxidation of the copper is minus 0.34 volt, as the reduction potential of the copper in the electrochemical series is given, that is 0.34 volt. So when we writing the oxidizing, we will change the sign, so the E oxidation of the copper is minus 0.34 volt, while the E reduction of the ferric ion is plus 0.77 volt. To write the overall reaction, we will add the above two reactions, so overall reaction is like that copper react with 2 ferric ion. We can cross the electrons on both sides, so it form Cu2 plus and 2 ferrous ion Fe2 plus. E of the cell is equal to E cell is equal to E oxidation plus E reduction. So E oxidation is minus 0.34 volt, while E reduction is 0.77 volt. So we can subtract 0.34 from 0.77, so we get the potential that is 0.43 volt. This is E naught, standard potential of the cell. So this is the solution to part A. Now in part B, we have given the concentration of the copper Cu2 plus, which is equal to 1 molar, while the concentration of the Fe3 plus ferric ion is also 1 molar, while the concentration of ferrous ion Fe2 plus is 5 molar. So initially there is 1 molar, and when 5 molar is added, so the total concentration of the ferrous ion become equal to 6 molar. Now we can calculate E cell is equal to E naught minus 0.0592 over n log of Q, as Q is equal to the concentration of the product over the concentration of reactants. So we can see that in the cell, on the product side, there is the concentration of the Cu2 plus ion raised to the power their number of mole, that is 1. There is Fe2 plus ion which has 2 moles, so raised to the power 2, divided by, on the reactant side we has ferric ion Fe3 plus raised to the power their number of mole, that is 2. So putting the values, E is equal to E naught is 0.43 volt minus 0.0592, where n is the number of electron lost and gained, so n is equal to 2. We can write 2 over here, and log up instead of Q, we can write the concentration of copper, iron, and iron Fe2 plus divided by Fe3. So putting the values direct, we can write the concentration of copper is 1 molar, while the ferrous ion is 6 mole square, divided by the ferric ion is also 1 molar square. We can calculate E. E is equal to 0.43 volt minus 0.0592 0.592 divided by 2 multiply by log of 6. So when we divide 0.0592 by 2, it become equal to 0.0296, and log of 6 square is equal to 36. Log of 36 is equal to 1.5. Now multiplying 1.5 with 0.0296, so we will get that E is equal to 0.43 volt minus, multiplying these two we get it is equal to 0.046. So E is equal to 0.476 volt. This is the cell potential for the concentration when the concentration of the ferrous ion is 6 volt. Now in the part C we have given the concentration of copper, that is 0.1 molar, also of the ferric ion 0.1 molar, and the ferrous ion is also 0.1 molar. So the concentration of each is 0.1 molar. Again, using the same equation, we will write that E is equal to E naught is 0.43 volt minus 0.0592, where n is equal to 2, and log of the concentration of copper ion is 0.1 molar, multiply by ferrous ion 0.1 square, divided by the ferric ion is 0.1 molar square. So we can cross 0.1 with 0.1. We will take only log of 0.1. So we will write that E is equal to 0.43 volt minus 0.0592 divided by 2 is equal to 0.0296, and log of 0.1. So E is equal to 0.43 volt minus 0.0296, where log of 0.1 is equal to minus 1. So E is equal to 0.43 volt minus, multiply by minus, plus 0.0296, adding both, so we get that E is equal to 0.4596 volt. This is the potential of the cell. So from the calculations we get that this concentration is greater, so cell C has greater potential. Then all, as cell A has potential 0.043 volt, while cell B has a potential of 0.389 volt. In an electrolytic cell where electrolysis of copper bromide take place, so the copper bromide ionizes, forming cupric ions and bromide ions. At anode, the oxidation of the bromide take place, So the bromide ion oxidizes, forming bromine liquid and releasing the electrons, while at cathode copper ion reduces, gain 2 electrons and 2 copper metal. There is a positively charged electrode connected to a voltage source. So the positively charged electrode is called anode because this is an electrolytic cell. Anode has positive charge on it, while the negatively charged electrode is called cathode. Cathode has negative charge over at an electrolytic cell. Oxidation takes place at anode while reduction takes place at cathode. So the copper ion from the solution move towards the cathode where it gains electron and is reduces to copper, while the bromide ions from the electrode moves toward the anode where it oxidizes and forming bromine molecule. Here the electron moves from the anode through the external circuit toward the voltage source, and the electron from the voltage source moves toward the cathode. The net reaction or overall reaction for the two is that copper ion react with two bromide ions, forming copper and bromine.
In this problem, we are given with a galvanic cell reaction and we are asked to find out the shorthand notation for that cell reaction. So let's write down the reaction equation first. And the reaction equation is metallic iron reacting with stannous ion to produce ferrous ion and tin, solid or metallic tin. So now we have to find out the shorthand notation, and as we know that a shorthand notation is usually writing down the anode and cathode half reaction just side by side, having two vertical lines in between them as a salt brace. So for that, first you have to identify the anode and cathode half reaction, and the anode half reaction is the oxidation reaction in the overall cell reaction, and the cathode half reaction is the reduction reaction in the overall cell reaction. So let's find out which one is our oxidation part and which one is our reduction part. And as we know that for oxidation there will be an increase in the oxidation state of the species. So from here we can easily see that oxidation number of iron has increased from 0 to +2 here. So that means iron is being oxidized, and the oxidation number of tin has reduced from +2 to 0. That means tin is reduced here. So this is our oxidation half reaction, and this is our reduction half reaction. So if we just separate them now as anode and cathode half reaction, so anode or oxidation half reaction will be solid iron converting into ferrous ion while it will give up 2 of its electrons, and the cathode half reaction will be, or the reduction reaction will be Sn2 plus ion taking up that 2 electron from iron, and it will become metallic tin or solid tin. So these are our anode and cathode half reaction. Now we can write down our shorthand notation, and for the shorthand notation we'll start with the anode half reaction, and we will not write down this electron part, and we'll separate the species from both sides of the reaction by a vertical line. So we can write it down as solid iron, and we put this vertical line, and then we write down the final oxidized state of this, and then we will put 2 vertical lines as a salt bridge or as a separation in between 2 compartments, and then we will have Sn2 plus, since it is our form of this tin in the reactant side, and then we put another vertical line, and then we put the final state of this tin, which is metallic tin, and that is our, so that's how our shorthand notation for the given galvanic cell reaction will look like.
The cell shown in the diagram is an electrolytic cell. Because there is a voltage source. So the voltage is supplied by the voltage source. This is an electrolytic cell. Here electrical energy changes into chemical energy. So the cell shown in the diagram is an electrolytic cell because it is attached to the voltage source, that is battery. Here the positively charged electrode in the electrolytic cell is called anode. Anode has positive charge over it, and oxidation takes place at anode. The negatively charged electrode is called cathode. At cathode has negative charge, and at cathode reduction take place. In case of electrolysis of nickel sulfate, at anode the hydroxyl ions from the aqueous solution oxidizes, forming a molecule of water, and oxygen gas is released. It also releases 2 electrons at cathode. The nickel ion gain these 2 electrons. Here at reduction take place and form nickel. The net reaction for the both is that Ni2 plus react with the 2 hydroxyl ions. We can cross the electrons on the opposite side of the 2 reactions, forming nickel metal, water molecule, and oxygen molecule. Nickel from the solution move toward the cathode where it reduces to nickel. On the other hand, the hydroxyl ion from the aqueous solution move toward the anode where they oxidizes. The electron flow from the anode side toward the voltage source and through the voltage source toward the cathode. In case of electrolysis of titanium oxide, which ionizes form Ti4 plus and 2 oxide ions at anode. The oxidation of oxide ions take place where they form oxygen molecule and release 4 electrons. On the other hand, at cathode, the reduction of titanium ion take place, which gain the 4 electron released by the oxide ion and form titanium. In overall reaction, we can write that titanium ion Ti4 plus ion react with the 2 oxide ions forming titanium and oxygen. We can cross the electrons at both sides of the reaction. Here at anode, oxidation take place, so the oxide ions from the solution move toward the electrode where they oxidizes forming oxygen, while titanium ion from the solution move toward the cathode where its reduction take place and changes into titanium. The reaction take place in the presence of calcium chloride Ca2 plus and Cl minus solution. The electron moves from the anode toward the voltage source and through the voltage source toward the cathode. In case of electrolysis of titanium oxide, which ionizes form Ti4 plus and 2 oxide ions at anode, the oxidation of oxide ions take place where they form oxygen molecule and release 4 electrons. On the other hand, at cathode, the reduction of titanium ion take place, which gain the 4 electron released by the oxide ion and form titanium. In overall reaction, we can write that titanium ion Ti4 plus ion react with the 2 oxide ions forming titanium and oxygen. We can cross the electrons at both sides of the reaction. Here at anode, oxidation take place, so the oxide ions from the solution move toward the electrode where they oxidizes forming oxygen, while titanium ion from the solution move toward the cathode where its reduction take place and changes into titanium. The reaction take place in the presence of calcium chloride Ca2 plus and Cl minus solution. The electron moves from the anode toward the voltage source and through the voltage source toward the cathode. We have given a Daniell cell in which there is a zinc electrode dipped in 1 molar solution of zinc sulfate ions, and on the other hand is a copper electrode which is dipped in copper sulfate ions. As we know that at anode the oxidation of the zinc take place. At anode, zinc oxidizes into Zn2 plus and release 2 electron, where E oxidation of the zinc is 0.76 volt, while at cathode reduction take place and cupric ion Cu2 plus gain the 2 electron forming Cu, and the E reduction of the copper is 0.34 volt. Combining the two equations, we can write overall reaction that zinc react with the copper ion forming zinc ion and copper, where E naught of the cell is the E oxidation plus E reduction. Adding the two, we will get 1.1 volt cell potential. Now we have given in part A that 5 molar copper sulfate solution is added to cathode. When 5 molar copper sulfate is added to cathode, as already there is 1 molar solution in the cathode. This is cathode, cathodic half, and this is anodic half. There is a salt bridge. Anode has negative charge because the zinc oxidizes, leaving electrons at the electrode, while cathode has positive charge because the copper reduces, gaining electron. So when 5 molar copper sulfate is added to the cathode, the total concentration becomes 6 moles because 1 molar solution is already present, so the copper sulfate is now 6 molar. To determine the potential of this cell, we can write that E cell is equal to E naught minus 0.0529 divided by N into log of Q. As we know, N is the number of electrons gains or lost. So in this cell, we see that there are 2 moles of electrons, so N is equal to 2, where Q is equal to the concentration of the ions to the product side divided by the concentration of the ions on the reactant side. So there is zinc ion on the product side, zinc 2 plus ion, while there is copper ion on the reactant side. As both have 1 mole, so each raised to the power 1. So for Q we can write the concentration of zinc and copper ion. Now E cell will be equal to E naught, where E naught is 1.1 volt minus 0.0592 divided by 2, where log of Q is the concentration of zinc, which is 1 molar. Zinc ion is 1 molar, while the copper ion is 6 molar. So E cell is equal to 1.1 volt minus 0.0592 divided by 2 is equal to 0.0296, where log of 1/6 is equal to minus 0.778. E cell is equal to 1.1 volt. Multiplying the two, we will get minus multiplied by minus plus, and 0.0296 multiplied by 0.778, this is equal to 0.023. Adding the two, we will get E cell is equal to 1.023 volt. This is the potential in case of cell A. Now in case of cell B, we have given that in part B we have given that 5 molar H2SO4 is added to the cathode compartment, to the cathodic half compartment half cell. So when 5 molar H2SO4 is added, so there are 5 multiplied by 2 molar hydrogen ions. As the hydrogen ions are present in the cathodic half, so we will write it in the log of Q is equal to the concentration of the product over reactant. So on the reactant side there is no hydrogen ion concentration raised to the power 2 because there are 2 moles of the hydrogen ions. The total concentration of the hydrogen ion is 5 2s are 10 molar. So putting this value for, we can now instead of log of Q we can write the concentration of the zinc, which is 1 molar. So concentration of the zinc is 1 molar, while the concentration of the copper is also 1 molar, while the concentration of the hydrogen ion is 10 molar square. So we can calculate the equation. E is equal to 1.1 volt minus 0.0592 divided by 2 is equal to 0.0296, where log of 1/10 square is equal to 100. So we can write minus 0.0296, where log of 1/100 is equal to, so log of 1/100 is equal to minus 2. Multiplying these two, we will get E cell is equal to 1.1 volt minus multiply by minus is equal to plus. This is equal to 0.0592. Adding this, we will get E cell is equal to 1.1592 volt. This is the potential of the cell in case of P. Now in case of C, we have given that 1 molar zinc nitrate is added to the anodic compartment. So when 1 molar ZnNO3 is added to the anodic half, so the total concentration of zinc nitrate become equal to 2 molar, as 1 molar is already present. So writing this equation for, so we can write log of Q instead of log of Q, we can write 2 molar concentration of the zinc divided by 1 molar concentration of the copper. So log of 2 is equal to 0.3. Multiplying by 0.3 with 0.0296, so we will get that minus 0.0088, subtracting the 1.1 from 1.10 0.0088. when we subtract, so we get the answer 1.0912 volt. This is the E cell in case of case C. We have given a Daniell cell in which there is a zinc electrode dipped in 1 molar solution of zinc sulfate ions, and on the other hand is a copper electrode which is dipped in copper sulfate ions. As we know that at anode the oxidation of the zinc take place. At anode, zinc oxidizes into Zn2 plus and release 2 electron, where E oxidation of the zinc is 0.76 volt, while at cathode reduction take place and cupric ion Cu2 plus gain the 2 electron forming Cu, and the E reduction of the copper is 0.34 volt. Combining the two equations, we can write overall reaction that zinc react with the copper ion forming zinc ion and copper, where E naught of the cell is the E oxidation plus E reduction. Adding the two, we will get 1.1 volt cell potential. Now we have given in part A that 5 molar copper sulfate solution is added to cathode. When 5 molar copper sulfate is added to cathode, as already there is 1 molar solution in the cathode. This is cathodic half, and this is anodic half. There is a salt bridge. Anode has negative charge because the zinc oxidizes, leaving electrons at the electrode, while cathode has positive charge because the copper reduces, gaining electron. So when 5 molar copper sulfate is added to the cathode, the total concentration becomes 6 moles because 1 molar solution is already present. So the copper sulfate is now 6 molar. To determine the potential of this cell, we can write that E cell is equal to E naught minus 0.0529 divided by N into log of Q. As we know, N is the number of electrons gains are lost. So in this cell, we see that there are 2 moles of electrons, so N is equal to 2, where Q is equal to the concentration of the ions to the product side divided by the concentration of the ions on the reactant side. So there is zinc ion on the product side, zinc 2 plus ion, while there is copper ion on the reactant side. As both has 1 mole, so each raised to the power 1. So for Q, we can write the concentration of zinc and copper ion. Now E cell will be equal to E naught, where E naught is 1.1 volt minus 0.0592 divided by 2, where log of Q is the concentration of zinc, which is 1 molar. Zinc ion is 1 molar, while the copper ion is 6 molar. So E cell is equal to 1.1 volt minus 0.0592 divided by 2 is equal to 0.0296, where log of 1 over 6 is equal to minus 0.778. E cell is equal to 1.1 volt. Multiplying the two, we will get minus multiply by minus plus, and 0.0296 multiplied by 0.778, this is equal to 0.023. Adding the two, we will get E cell is equal to 1.023 volt. This is the potential in case of cell A. Now in case of cell B, we have given that in part B we have given that 5 molar H2SO4 is added to the cathode compartment, to the cathodic half compartment half cell. So when 5 molar H2SO4 is added, so there are 5 multiplied by 2 molar hydrogen ions. As the hydrogen ions are present in the cathodic half, so we will write it in the log of Q. Q is equal to the concentration of the product over reactant. So on the reactant side there is no hydrogen ion concentration, raised to the power 2 because there are 2 moles of the hydrogen ion. The total concentration of the hydrogen ion is 5 2s are 10 molar. So putting this value for, we can now instead of log of Q, we can write the concentration of the zinc, which is 1 molar. So concentration of the zinc is 1 molar, while the concentration of the copper is also 1 molar, while the concentration of the hydrogen ion is 10 molar square. So we can calculate the equation. E is equal to 1.1 volt minus 0.0592 divided by 2 is equal to 0.0296, where log of 1 over 10 square is equal to 100. So we can write minus 0. minus 0.0296, where log of 1 over 100 is equal to, so log of 1 over 100 is equal to minus 2. Multiplying these two, we will get E cell is equal to 1.1 volt minus multiply by minus is equal to plus. This is equal to 0.0592. Adding this, we will get E cell is equal to 1.1592 volt. This is the potential of the cell in case of P. Now in case of C, we have given that 1 molar zinc nitrate is added to the anodic compartment. So when 1 molar ZnNO3 is added to the anodic half, so the total concentration of zinc nitrate become equal to 2 molar, as 1 molar is already present. So writing this equation for, so we can write log of Q, instead of log of Q we can write 2 molar concentration of the zinc divided by 1 molar concentration of the copper. So log of 2 is equal to 0.3. Multiplying by 0.3 with 0.0296, so we will get that minus 0.0088, subtracting the 1.1 from 1.10 0.0088. when we subtract, so we get the answer 1.0912 volt. This is the E cell in case of case C. In a fuel cell, a special type of cell is called proton exchange membrane cell, PEM. In PEM, at anode, oxidation takes place where the hydrogen molecule oxidizes, form hydrogen ions and release electrons. As we know, the reduction potential of hydrogen is the oxidation potential of hydrogen is 0 volt, while on the other hand reduction at cathode take place and the oxygen molecule gain 4 electrons released by the hydrogen. It form 2 oxide ions. Here the reduction potential of the oxygen NPEM proton exchange membrane is 1.23 volt. The net reaction is like that. Overall reaction is that two hydrogen molecule react with an oxygen molecule forming 2 water molecule. We can cross the electron on both hand side, and E cell over here is equal to E oxidation plus E reduction, where E oxidation is 0 volt while E reduction is 1.23 volt. So the net potential of the cell is 1.23 volt. The hydrogen from the outer side enter and to the right compartment, where it oxidizes to hydrogen ions. Here oxidation take place, so the electrode at the right hand side is anode. The hydrogen ion then cross the membrane. This membrane is called proton exchange membrane. Proton exchange membrane. The hydrogen move from the right side toward the left side, crossing the membrane, where oxygen enter from the outer side, where it reduces at cathode. It form oxide ion. The hydrogen ion and the oxide ions combine together, forming water molecule. The water leave this compartment and move outside. The electron move from the anode through the external circuit toward the cathode.
Question number 35 is in reference to how you read a standard reduction potential table in terms of identifying the strongest oxidizing agent, the strongest reducing agent, what will oxidize what will reduce what, and so forth. So we have our 4 reduction half reactions with their corresponding reduction potentials as shown here. Normally with these types of reduction tables, our strongest oxidizing agent will be the one that wants to be reduced the most, so that would be A+, and then our strongest reducing agent is going to be the product of the one that wants to be reduced the least, which would be D. So the answer to part A is the strongest oxidizing agent will be A+, and the strongest reducing agent will be D. For part B, it wants to know which substance can be oxidized by B+. Well, B+ can oxidize anything with a lower reduction potential, such as C2, such as C-, it becoming oxidized to C2, and D becoming oxidized to D3+. It then also asks, what can be reduced by D? Well, D we identified as the strongest reducing agent, so from what is shown here, D can reduce anything above it, A+, B2+, and C2. The last part of this question wants you to write the chemical reaction for a process that has a voltage of 1.53 volts. If we were to take the last two reactions, flipping the last one, so this serves as the cathode, this will serve as the anode. To cancel the electrons, we need to multiply the first one by 3 and the second one by 2. We would then get this chemical reaction. Because this is our cathode and this is the anode, we would then take the cathode potential minus the anode potential to determine the cell potential, which is 1.53, which was what was requested.
In a galvanic cell, spontaneous redox reaction take place. Therefore, at anode, oxidation take place, and at cathode, we know that reduction take place. At anode, zinc oxidizes, forming Zn2 plus ion and leave the electron at the electrode. So zinc from the electrode move toward the solution in the form of zinc ion. On the other hand, at cathode, the copper ion from the solution gain electron at the cathode and forming copper. So the copper move from the solution toward the electrode where it gain electron and is reduces. As the reactions take place spontaneously, so the anode has negative charge while the cathode and the galvanic cell has positive charge, and the electron move through the external circuit from the anode toward the cathode. As a result of this spontaneous reaction, some voltage is produced.
So if you're given a say galvanic cell, if you're given a galvanic cell with all the components intact, we have the cathode, anode. Okay, so let's say this is one beaker, and this is another beaker, say beaker B. Okay, and each one of these beakers have electrodes. So these are electrodes. Okay, these are electrodes, and each one of these is filled with an electrolyte. Okay, electrolytes. Electrolyte is a liquid that allows for ions to be exchanged. Okay, so you'll notice that this circuit isn't complete, despite the fact that we have a connecting wire here, okay, that measures volts. This circuit is not complete because we need to add a salt bridge. So a salt bridge is the one that will complete these particular circuits. So salt bridges are like bridges connect to points. Okay. So once this salt bridge is put here, okay, this will be a salt of compound. that conducts electricity, that will allow ions to flow, because we expect, if this is anode and this is the cathode side, okay, this is where oxidation takes place, this is where reduction takes place, okay. We expect that electrons will flow from anode to cathode, so we expect electrons to flow this way. But then you expect ions to flow in the opposite direction, say copper or so ions. Okay. We expect ions to flow in opposite directions to electrons. Okay. So the role of salt bridge is to finish to connect two particular half cell reactions here. Okay. To allow for the exchange of electrons and ions in the opposite directions.
In a galvanic cell, when cadmium react with the tin ion, where cadmium react with the tin ion, cadmium is oxidized to Cd2+, where Sn2+ is reduced. In this reaction at anode, cadmium is oxidized to Cd2+ and release 2 electrons, while at cathode Sn2+ gain the electron released by the cadmium and is reduced to 10. So the oxidation of the cadmium take place at anode, cadmium oxidizes. At electrode, it comes toward the solution in the form of Cd2+ ion. It leaves the electron at the anode, so the anode in this case has negative charge, while the tin from the solution move toward the electrode, where it reduces. So gain of electron take place at cathode. Electron moves through external circuit from anode toward the cathode. In case of aluminium, when it reacts with the cadmium, ions, aluminium is oxidized while cadmium is reduced. In this reaction, aluminium oxidizes, forming aluminium ion, releasing electrons. The reaction takes place at anode, while cadmium gain the electrons released by the aluminum. Its reduction take place at cathode. Cadmium is reduced. In the cell, aluminum oxidizes, so it moves from the electrode toward the solution in the form of Al3 plus ions and leave the electron at the anode. Here the anode has negative charge, while the cadmium from the solution move toward the electrode, where it reduces at the electrode, gaining electron. So at cathode, reduction take place. The electron moves from the anode side toward the cathode through the external circuit. In case of chromate ion Cr2O7, -, when it reacts with the ferrous ion, so the reduction of the chromium take place in the presence of hydrogen ions, acidic medium. So chromium is reduced from +6 oxidation state in the chromate to 3+ oxidation state, where the iron is oxidizes, ferrous ion as oxidizes to ferric ion, Fe3+, and 7 water molecule is formed in the reaction. Here the chromate ion in the presence of hydrogen ions gain the electron released by the iron, so their reduction take place at cathode, where Cr3+ ions is formed and 7 water molecule is formed. On the other hand, the ferrous ions oxidizes at anode, forming the ferric ion and releasing electrons. So at the anodic half, ferrous ion oxidizes at electrode to ferric ion, while the chromate ion chromium in the chromate ion chromium is reduced to Cr3+. As oxidation take place at anode, so anode has negative charge, while reduction take place at cathode. So here the cathode is positively charged because the reactions are spontaneous, and the electron moves through the external circuit from the anode toward the cathode.
In this problem, we are given with a galvanic cell, and we can see the galvanic cell here in this image, and we have 4 parts of this question. In the first part of this, we are asked to complete the drawing by adding any components essential for a functioning cell. So here we can see that we have 2 compartments, and we can assume that one of them is anode and one of them is cathode, and the anode and cathode are not leveled here, and we have to level that, and that's another part of this problem. But let's first complete the drawing by adding the essential part, which is a salt bridge. So without a salt bridge, a galvanic cell is incomplete, because in that case there will be an imbalance of the ions in 2 of the compartments, and that will create a short circuit of the cell, and it will eventually end up producing any more electron or current. So for the salt bridge, we actually add a U-shape tube here, and in this U-shaped tube we have an inert electrolyte solution. In this case, since we already have nitrate ions in the cell, so we can use any nitrate solution, and in this case we will use sodium nitrate. So we can write down sodium ion and nitrate ion. That will this salt bridge. So that's the essential part we are missing in this galvanic cell. Now in the second part, we are asked to level our anode and cathode. So from here, so we have to identify the anode and cathode. We can identify that from the flow direction of the electron. So from here we can see that the electron is flowing in this direction, and we know that electrons always go from anode to cathode since electrons are being produced in anode. So we can say that our aluminum strip here is our anode, and our cobalt strip here is our cathode. So these are anode and cathode, and we are also missing the sign of the anode and cathode. And as we know that electrons are being produced in anode, that means the sign for the anode will be minus, and since the charge for the cathode is plus, we have to put a plus sign here. We are also asked to indicate the ion flow direction. So since our electron is moving in this direction, these electrons will go here to neutralize cobalt 2 plus ions. The cobalt ion will go in this direction, and at the same time producing electron here in this aluminum strip, and the aluminum Al3 plus ions are being released to the solution here. And the aluminum ions go through this salt bridge here, and they come in a direct contact with the cobalt ion. In that case, we will not have the electron flow in this direction. So we have to prevent this aluminum ion from going through this salt bridge, and for that our nitrate ions from the salt bridge will come down in this direction, and those nitrate ions will react with aluminum to neutralize them or to keep them in the solution. The direction for the nitrate ion will be in this direction, and for the aluminum ion it will be in this direction. In our part C of the question, we have to write down a balanced equation for the cell reaction. So first we have to write down the anode and cathode half reaction. So our anode half reaction with the oxidation of aluminum metal. So aluminum metal will become Al3 plus ion by giving up its 3 electrons, and our cathode half reaction will be cobalt 2 plus will take up 2 electrons to become neutral cobalt. So this are our anode and cathode half reaction, and but to write down the overall cell reaction, we have to have a balance in our number of electrons in cathode and anode half reactions node. And from here you can see that to make them a same number, we have to multiply the anode half reaction by 2, and we have to multiply the cathode half reaction by 3. 2l 3 plus 6 electron, have 3 CO2 plus 3 times 2 6 electron and 3 cobalt. So now we have 6 electron in both cases, and add these two equations up, and when adding up we'll have these 6 electrons, and these 6 electrons will cut off, and the overall cell reaction will be 2 aluminium plus 3 CO2 plus equal to 2L3 plus 3 cobalt. So that's our overall cell reaction. And finally, if we have to write down the cell notation for this, so our anodic half reaction will be aluminum metal being converted into Al3 plus, and we have to give this vertical line in between these two to separate their phase. So this is our anode half cell, and then we will place the salt bridge notation in between anode and cathode, and then we'll start writing down the cathode half cell, and that will be our cobalt 2 plus in aqueous form, phase change to cobalt, solid cobalt. And this is our cell notation for this galvanic cell.
In a galvanic cell, when copper ion reacts with the chromium ion, the chromium so the copper is reduced while the chromium is oxidized to Cr3 plus ion. In this reaction, at anode, oxidation of the chromium take place. Your chromium oxidizes to Cr3 plus and release electrons. So their oxidation take place. On the other hand, at cathode, the copper is reduced gaining the electron released by the chromium. Copper. As the oxidation of the chromium take place at the cathode, so the chromium from the at the anode, so the chromium from the electrode moves toward the solution in the form of Cr3 plus ions. Their oxidation take place at anode, so it leaves the electron at the anode. Therefore, anode has negative charge. This is a galvanic cell and a spontaneous process. On the other hand, at cathode, reduction of the copper take place. So copper move from the solution toward the cathode where it reduces, it gains the electron. Here the cathode has positive charge. The electron moves from the external through the external circuit from the anode toward the cathode. In another cell, when lead react with hydrogen ions, lead oxidizes to Pb2+, while hydrogen gas is released. In this reaction, at anode, lead oxidizes to Pb2+ ion, releasing the electrons, while at cathode, the hydrogen ions gain the electron released by the lead, so it reduces to hydrogen gas. Here the oxidation of the lead take place at anode, so lead move from the electrode toward the solution in the form of Pb2+ ion. This reaction take place at anode. As it leaves the electron at the anode, therefore anode has negative charge. On the other hand, at cathode, the hydrogen ion from the solution move toward the electrode, where it gains electron and change into hydrogen gas. The electron move from the anode toward the cathode through external circuit. In a cell, when tin react with Sn2+ ion, react with chlorine gas, Sn2 oxidizes to Sn4+, and chlorine is reduced to chloride. Here at anode, the oxidation of the Sn2+ take place, with change to Sn4+, releasing 2 electrons. On the other hand, at cathode, the chlorine molecule gain these electrons released by the tin. It changes to chloride ions. Here oxidation of the Sn2+ take place at anode, where it changes to Sn4+. At anode, as oxidation take place spontaneously, so the tin leave electrons at the anode, therefore anode has negative charge. On the other hand, the chlorine molecule gain electrons at the cathode and change into chloride ions. Here reduction take place at cathode. Electron moves from the anode toward the cathode through external circuit. To write the standard cell notation for each cell, the first one is that cadmium react with the Sn2+ ion to form cadmium 2+ ion, and tin is reduced in this reaction So to write the cell notation, we first write the oxidation half. So in the oxidation half, the cadmium oxidizes to Cd2+, and we also write the molarity of the solution, that is 1 molar solution. The double lines show the salt bridge, and on the right of the salt bridge we write the reduction half. So in the reduction half, the Sn2+ from the 1 molar aqueous solution reduces to Sn solid, 10 solid form. For the second cell, the reaction is that 2 aluminium react with the 3 cadmium ion so aluminium oxidizes to form Al3+ ion while the cadmium is reduced. So to write the cell notation for this reaction, we will write the oxidation half first. So in the oxidation half, the aluminium and the solid form oxidizes to aluminium 3+ ion, and in the 1 molar solution it comes to the solution. The double line show the salt bridge, and now we will write the reduction half. So where the cadmium 2+ ion present in 1 molar solution reduces to form cadmium solid. For the third cell, where the reaction is the diachromate ion Cr2O7 2- present in the aqueous solution react with the ferrous ion present in aqueous solution, and in the presence of hydrogen ions to form 2 Cr3+ ions, ferric ion, and water molecule. So in this reaction, the ferrous ion present in 1 molar solution oxidizes to ferric ion, and 1 molar solution the reaction takes place at platinum electrode, while on the other hand the diachromate ion reduces to chromium 3+ ion at platinum solid electrode. So these are the cell notation for the given 3 reactions. The redox reaction, where copper ion react with the chromium, copper is reduced where chromium is oxidized. and this reaction as the chromium has been oxidized. So in the cell notation we will write the chromium oxidation half first. So we write that chromium oxidizes to Cr3 plus, and with the ion we will write the solution molarity, that is 1 molar. On the other hand, in the reduction half, the copper is reduced, so copper 2 plus ion is present in the 1 molar solution. It is reduced to copper. In another reaction where lead react with the hydrogen ions, lead is oxidized to Pb2 plus, where the hydrogen ions are reduced to hydrogen gas. In this reaction, writing the oxidation half first, so Pb oxidizes to Pb2 plus and 1 molar solution, where the hydrogen ions are reduced to hydrogen gas at inert platinum electrode. And the other reaction where Sn2 plus react with chlorine, forming Sn4 plus 2 chloride ion, as Sn2 plus is oxidizes to Sn4 plus. Such reaction take place at inert electrode. Platinum is normally used. Both the ions are present in 1 molar solution. Reaction take place at inert electrode, that is platinum. On the reduction half, the chlorine molecule changes to chloride ion at platinum electrode. So these are the cell notation for these reactions. In a reaction which take place at platinum electrode, so at platinum electrode, a bromide ion from the aqueous solution oxidized to bromine liquid state, while the chlorine molecule is reduced to chloride ion, which come toward the aqueous solution. This reaction also take place at platinum. Platinum is used as inert electrode. There are different purposes of using inert electrode like platinum, but whenever there is the reaction of non-metals, that is bromine and chlorine, so we will use an inert electrode like the platinum. In the reaction we can see that at anode oxidation take place, so 2 bromide ions oxidizes into bromine molecule and release 2 electrons, while at cathode the reduction take place where the chlorine molecule gaining the electrons released by the bromine, it reduces to chloride ions. The overall reaction is like that, combining the two equations, we can cross the electron on the opposite side. So we can say that two bromide ions react with a chlorine molecule, forming bromine molecule where bromine has been oxidized, reducing the chlorine. As we know that chlorine is a strong oxidizing agent than bromine, so it oxidizes the bromine and reduce by itself. In the cell we can see that bromide ion in the solution changes to bromine liquid where oxidation take place. This side is anode. As we know, oxidation take place at anode. On the other side, the chlorine molecule gain electrons from the electrode, forming chloride ions. Here reduction take place. So this side is cathode. The electron move from the anode toward the cathode through the external circuit. Here chlorine, as we know that the cell potential E cell is always equal to E oxidation plus E reduction. So we know that the oxidation of the bromine take place, where the oxidation of bromine can produce a voltage of minus 1.09 volt, while the reduction of chlorine produce a voltage of plus 1.36 volt. Adding the two voltage, we can get a cell of voltage 0.27 volt, which is the potential of the cell. We have given a cell reaction between the iron and the iodine to form ferrous ion and iodide ion. So in this reaction, the iron oxidizes while the iodine gain the electron and reduces to form iodide ions. And to write the cell notation for the two half cell reactions, so we will write the oxidation half to the left, where iron oxidizes to ferrous ion and it come towards the solution, so we will write the molarity of the solution. On the other hand, the iodine reduces to form iodide ion. So this reaction take place at platinum electrode. This is the cell notation for the above half cell reactions. In a cell having anodic half, the hydrogen molecule changes to hydrogen ion, while at the cathodic half, the silver ion is reduces to silver. The net reaction for the anode is that the hydrogen molecule oxidizes to hydrogen ion releasing 2 electrons, while at cathode 2 silver ion gain the electron, forming silver molecule, forming silver. Overall reaction for the two half is adding the above two equations, so we can write that hydrogen molecule react with silver ions, forming hydrogen ions, and silver is reduced. And these reactions we can cross the electron on either side of the electrode. Here at anode, oxidation take place where hydrogen is oxidizes to hydrogen ions and release electrons at the electrode. Therefore the anode is negatively charged, while at cathode the reduction of the silver take place. So silver from the solution move toward the electrode, which is called cathode, where it gain electron and is reduces. The electron from the anode move toward the cathode through an external circuit. The shorthand notation for the above cell is we can write the oxidizing half first, so at platinum electrode hydrogen molecule oxidizes to hydrogen ion, while at the reduction half silver ion is reduces to silver. Silver ion present in the 1 molar solution is reduces to silver. This is the shorthand notation for the above cell. For a galvanic cell where at anode zinc oxidizes to zinc 2 plus ion, where at cathode the chlorine molecule reduces to chloride ions. So the complete reaction for the anode is zinc oxidizes into Zn2 plus, releasing 2 electrons, while at cathode the chlorine molecule gain the electron released by the zinc and form 2 chloride ions. Overall reaction for the two half cell is adding the two equations, so we can cross the electrons on either side. So we can say that zinc react with the chlorine molecule, forming Zn2 plus ion and 2 chloride ions. So the right hand side shows anode where a spontaneous oxidation reaction take place and zinc oxidizes, moving toward the solution in the form of Zn plus 2, leaving the electrons at the electrode. Therefore anode has negative charge. On the other hand, the chlorine molecule is reduces at the cathode, forming chloride ions. The electron move from the anode toward the cathode through the external circuit. We can write the shorthand notation for the cell, writing oxidizing half first. So here zinc oxidizes into Zn2 plus in 1 molar solution, where at the second site chlorine molecule reduces to chloride ion at platinum electrode. For a cell in which cobalt solid oxidizes into cobalt 2 plus ion in aqueous solution, and the copper 2 plus ion from aqueous solution reduces, forming copper solid. So at anode, as we know, oxidation take place, and in the cell notation we writing oxidizing half first. So the cobalt solid has been oxidizes into cobalt aqueous 2 plus ion and has released 2 electron. On the other hand, at cathode, we are writing the cathodic half to the right hand side of the cell notation. So in cathode reduction take place, and the copper 2 plus ion from the aqueous solution gain 2 electrons, reduces to copper. As this is the anodic half, where cobalt from the electrode move toward the solution, forming cobalt 2 plus ions, leaving electrons at the anode. So the anode has negative charge, and here oxidation take place, anode has negative charge. On the other hand, in the cathodic half, which is also called reduction half, copper ion from the solution move toward the electrode, gains electron at the electrode and deposited. So the cathode, where reduction take place, has positive charge in the galvanic cell. The two cells are connected through a salt bridge for the ion concentration balance, where the electron flow through the external circuit from the anode toward the cathode. In a cell where iron solid oxidizes into ferrous ion, moving toward the aqueous solution, and on the other hand, oxygen react with the hydrogen ion present in the aqueous solution, where hydrogen ions reduces, forming react with oxygen, forming water. The reaction take place at platinum electrode. Here at anode, oxidation take place and 2 iron atoms oxidizes, forming 2 ferrous ions, releasing 4 total electrons. On the other hand, at cathode, where reduction take place, So 4 hydrogen ions gain these 4 electrons and react with oxygen, forming 2 water molecule. This is the anodic half, and this is the cathodic half. At anode, ion from the electrode move toward the solution in the form of Fe2 plus. Here oxidation take place, so anode has negative charge, while on the other hand at platinum cathode, the reduction of the hydrogen ion take place, so the cathode has positive charge. The two cells are connected through a salt bridge, and the electron moves from the anode toward the cathode in this direction. For a cell in which manganese oxidizes form Mn2 plus ion in the aqueous solution, and the lead from the aqueous solution reduces, forming Pb solid. Here at anode, oxidation take place, so manganese oxidizes form Mn2 plus and release 2 electrons, where at cathode reduction take place and the Pb2 plus gains 2 electron, forming Pb solid. So this is the anodic half, and this is the cathodic half. In the anodic half, manganese from the electrode moves toward the solution where oxidation take place at anode, and manganese leave the electrons at the electrode, so anode has negative charge in this case. On the other hand, at cathode, the lead ions from the solution move toward the electrode and deposited in the form of lead. This is cathode. On cathode reduction take place, and here cathode has positive charge. The two cells are connected for the ion concentration balancing through a salt bridge, and the electron moves from the anode toward the cathode. The overall reaction for the two cells is that manganese react with the lead ion, forming manganese Mn2 plus ion and lead, and we can cross the electron on either side of the reaction. In case B, we have given that at platinum electrode, hydrogen oxidizes, forming hydrogen ions in aqueous solution, while on the other hand Cl minus of the AgCl, where Ag plus of the AgCl reduces to Ag0. So at anode, where oxidation take place, so hydrogen oxidizes into hydrogen ion, releasing 2 electrons at cathode, where reduction take place, so 2 silver ions gain these electrons, forming silver atoms. The overall reaction is like this, that hydrogen ions react with the two silver ions. We can cross the electron on either side, so it forms two silver atoms which deposited over the electrode, and hydrogen ions come toward the solution. This is the anodic half, in which there is a platinum electrode. So the hydrogen molecule oxidizes at the anode. At anode, oxidation takes place, leaving electrons at the electrode. On the other hand, at cathodic half, this is cathode made up of silver, so the silver ions from the solution moves toward the cathode, where it gains electrons and is reduced. This is salt bridge. The electrons move from the anode toward the cathode through the external circuit or wire. Conditions which must be fulfilled for when E of the cell is equal to E naught of the cell. So to prove this equation, we know that we are taking the example of a Daniell cell. Let's suppose in a Daniell cell, zinc oxidizes into Zn2+, releasing 2 electrons at anode. Oxidation takes place. On the other hand, at cathode, the copper ions gain electrons at cathode. Here the reduction takes place and it changes to copper. So E cell is equal to E naught minus 0.0592 over n, and to log of Q. As we know, log of Q in this case is equal to the number of ions on the product side, the concentration of ions on the product side, to the concentration of ions on the reactant side. So on the product side, we have the concentration of zinc ion, while on the reactant side we have the concentration of copper ions. So to calculate that, E must be equal to E naught, so 0.0592, where n is equal to 2, and log of Q is equal to concentration of the zinc ion divided by concentration of the copper ion. So if the concentration of zinc ion is equal to 1 molar and that of concentration of the copper ion is also equal to 1 molar, so then E will be equal to E naught minus 0.0296 when we divide 0.0592 by 2, and log of zinc by copper concentration is equal to 1 molar divided by 1 molar. So this is equal to log of 1. As we know, log of 1 is equal to 0, so E is equal to E naught minus 0.0296 multiplied by 0, so this term will become 0 and the E will be equal to E naught. So when we have to make the cell potential equal to standard potential, we will take the concentration of ions equal to 1 molar, which is standard concentration for the each cell.
So in this problem we are given with a reaction between aluminium metal and chromium 3 ion, and we are given the standard cell potential for this reaction as at 25 degrees C as 0.92 volt, and we are asked to find out the standard free energy change for this reaction at 25 degrees C. So let's first write down the reaction equation, which is aluminium metal reacting with chromium 3 plus ion, and that will give us aluminium 3 plus chromium. And to find out the standard free energy change, we can utilize the formula of del G equal to minus NF del E naught, where N is the number of moles of electrons transferred between the reactants, F is the Faraday constant, and del E naught is the standard cell potential. So we know the value of del E, which is given as 0.92 volt, and we know the Faraday constant, which is 96,484 coulomb per mole electron. And then what we have to do is we have to just plug in these values in this formula, and we need the value of N, and we can find the value of N from the reaction equation. So from the reaction equation we can see that the oxidation number for aluminium in the reactant side is 0, and in the product side it's +3. So for aluminium we have a change in oxidation number of +3, and for chromium it was +3 in the reactant side and 0 in the product side. That means there is a decrease in the oxidation state in case of chromium, and from here we can see that the number of electrons transferred in between aluminium and chromium is 3 mole. So 3 moles of electrons are transferred in between. That means then the value for N is 3 mole. So now we know the value for all of these entries here, so we can just plug in the values to find out the value of del C, and that will give us minus 3 mole electron, and we'll multiply it by the value of F, which is 96,484 coulomb per mole electron, times 0.92 volt. 1 volt equal to 1 joule per coulomb. We can write down it as 0.92 joule per coulomb. Now if we just multiply them, it will be 266, 295.84, and the unit will be joule. So the electrons will be cut down, and the coulomb per coulomb will be cut down, so only joule will remain there. And if we want to convert it to kilojoule, the value will be 266.296 kilojoule. So that's the standard free energy change for the reaction given.
Standard reduction potential of any galvanic cell standard reduction potential of any galvanic cell is the sum of the standard reduction standard half potentials for oxidation at anode and standard half potential for reduction at cathode. Or it may also be defined as the potential of any electrode measured against the standard hydrogen electrode when an electrode is dipped in 1 molar solution of its own ions. For example, when zinc is dipped in zinc sulfate solution or copper in the copper sulfate solution, so when they are connected to the high standard hydrogen electrode, the oxidation of the zinc take place and zinc oxidizes into Zn2 plus, releasing 2 electron. So its standard reduction E0 reduction for the zinc is minus 0.77 volt, while when copper is connected to the standard hydrogen electrode, the reduction of the copper take place, it change into copper, so E0 reduction of the copper is plus 0.34 volt. The silver oxide and zinc battery, where zinc react with the silver oxide to form zinc oxide and silver. The cell voltage is 1.60 volt. We have to calculate the free energy change delta G naught for the reaction. To determine delta G naught for the reaction, we will use the equation that delta G naught is equal to minus NF E naught. As we know, when zinc oxidizes, it forms Zn2 plus and release 2 electrons, so N in this case is 2 mole of electron, while F is Faraday constant, which is 96,500 coulomb per mole of electrons. Putting the values in equation, we get that delta G naught is equal to minus, where n is 2 moles of electrons, F is Faraday's constant 96,500 coulomb per mole of electrons, and E naught is the potential, which is equal to 1.6 volt. Delta G naught is equal to minus 2 into 96,500 coulomb multiplied by 1.6 instead of volt, as 1 volt is equal to 1 joule per coulomb. So we will write the unit of joule per coulomb. So multiplying all the values, we get delta G naught is 308,800 joule. To change it into kilojoule, we will divide it by 1000. So the delta G naught will become 308 minus 308.8 kilojoule. So this is the cell potential, and this is the standard free energy for the given cell potential. This is the required solution to this question. For a cell in which the lead and lead oxide react with the hydrogen ions in the presence of H2SO4, it forms 2 PbSO4 and 2 water molecule. This is the reaction for the lead storage battery. In this, the lead oxidizes into Pb0 oxidizes to Pb2 plus. So we have to calculate delta G naught for this cell, where E naught is given, which is 1.924 volt. As we know, here is the loss of 2 electrons, so N is equal to 2. We know that the delta G naught is equal to minus N F E naught. So delta G naught is equal to minus, where N is equal to 2, where F is Faraday constant and it is equal to 96,485 coulomb per mole of electron, which is approximately equal to 96,500 coulomb per mole when we round to the nearest 100. So this is the 2 moles of electrons. So 2 moles of electron, F is Faraday constant, it is 96,500 coulomb per mole of electrons, multiply by E, where E is equal to 1.924 volt. So delta G naught is equal to minus 2. We can cross moles of electron with the moles of electron. 2 into 96,500 coulomb multiplied by 1.924 volt. As we know that 1 volt is equal to 1 joule per coulomb. So instead of volt we can write joule per coulomb. So we can cross coulomb with coulomb, multiplying all we get delta G naught multiply 2 with 96,500 and 1.925, so we get this is equal to 371,332 joule. To change it into kilojoule we will divide it by 1000, so we will get delta G naught is equal to minus 371.332 kilojoule. This is the delta G naught for this. For an arbitrary type of equation we have given that A plus B into x plus n form A x plus n and B. So here at anode oxidation of the A take place, which form A x plus n and x number of electrons are released. On the other hand, at cathode B x plus gain these x number of electrons and is reduces to B. Here the E naught of the cell is given, which is 1.43 volt, and delta G naught is also given, which is equal to minus 414 kilojoule. To find out the x, where x is equal to n, we have to calculate it by the equation that minus n f E naught is equal to delta G naught. So minus n, where f is Faraday constant and it is equal to 96,500 coulomb, multiply by the voltage of the cell is 1.43 volt is equal to delta G, where delta G is equal to minus 414 kilojoule. We can cancel the minus sign from both sides, so we will change into plus n. So n is equal to n multiplied by 96,500 coulomb multiplied by 1.43 instead of volt. 1 volt is equal to 1 joule per coulomb, so we can write the unit joule per coulomb. We can cross the coulomb with coulomb, and n is equal to multiplying 96,500 with 1.43, we get 137,995 joule, and this is equal to 414 kilojoule. To change the joule into kilojoule, we will divide it by 1000, so n multiply by this is equal to 137.995 kilojoule is equal to 414 kilojoule. To calculate the n, we will divide both sides by 137.995 kilojoule. So we get the n, where n is equal to 3. It means that x is equal to 3. So we can write the equation like this, that A plus A changes into A 3 plus, where 3 electrons are released, and the B 3 plus gain 3 electrons, it is reduces to B. This is the solution of this question. For an arbitrary type of equation in which 2a x plus react with 3b, forming 2a plus 3b y plus. So in this reaction at anode, the oxidation of 3b take place, where 3b oxidizes into 3b y plus y number of electrons are released. On the other hand, at cathode, reduction take place, where 2a x plus gain x number of electrons and form 2a. Here the cell potential is given, standard cell potential is given, so the standard cell potential E naught is equal to 0.91 volt, while delta G is also given, which is minus 527 kilojoule. We have to calculate N. To find N, we will use the equation that minus N F E naught is equal to delta G naught. Minus N, where F is Faraday constant, which is equal to 96,500 coulomb per mole of electrons, multiply by E naught of the cell is equal to 0.91 volt, is equal to delta G, where delta G naught is minus 527 kilojoule. We can cross the minus sign from both sides, so N multiply by 96,500 coulomb, and instead of 0.91 volt, we can write that 1 volt is equal to 1 joule per coulomb. So we can write joule per coulomb instead of the volt, is equal to 527 kilojoule. We can cross the coulomb, so N multiply by multiplying 96,500 with 0.91, we will get that it is equal to 878155 joule, is equal to 527 kilojoule. To make the unit same on both sides, we will divide the left hand side with 1000, dividing by 1000, so N multiply by 878.155 kilojoule. Sorry, this is equal to 87815 joule, so it become 78.85.815 kilojoule, is equal to 527 kilojoule. Dividing both sides by 87.815, kilojoule. So we get N is equal to 6. So N is equal to 6. It means that y is equal to 2 and x is equal to 3. So 2 multiplied by 3 is equal to 6. So the above equation can be written that 2a 3 plus gain 3 electrons to form 2a. On the other hand, 3b form 3b 2 plus and release 6 electrons. This is the solution to the question. For the reaction in which hydrogen react with oxygen to form water molecule, delta G naught for the reaction is minus 237.2 kilojoule. Now to determine the E naught of this cell, we will use the equation that delta G naught is equal to minus N F E naught, where E naught is equal to delta G naught divided by minus N F. So E naught is equal to, putting the value for the delta G naught, that is minus 237.2 kilojoule divided by E naught F minus N, where 2 electrons are lost in the reaction, that when hydrogen oxidizes it form a 2 hydrogen ion releasing 2 electron, and the oxygen molecule gain electron forming oxide ion, half oxygen molecule, so forming oxide ion. So in the balance reaction 2 electrons are released or gained. So where N is the number of electron, which is 2 mole of electrons. So N is equal to 2 mole of electrons, where F is Faraday constant and F is equal to 96,500 coulomb per mole of electrons. So putting the value of Faraday constant 96,500 coulomb per mole of electrons. Cutting the negative sign with the negative, so E naught is equal to 237.2 divided by 2 and divided by 96,500. We get the answer, that is 1.22 into 10 raised power minus 3 kilojoule per coulomb. To change the unit from the kilojoule to joule, we will get E naught is equal to 1.22 into 10 raised power minus 3 multiplying with 1000, that is 10 raised power 3. We will get the unit joule per coulomb. So cutting the 10 raised power minus 3 with 10 raised power 3, so E naught is equal to 1.22 joule per coulomb. As we know, 1 joule per coulomb is equal to 1 volt. So E naught is equal to E naught is equal to 1.22 volt, which is the required solution to the question. This is the answer, which is the required solution to the question. For a reaction in which methane CH4 react with 2 mole of oxygen forming carbon dioxide and water molecule. To determine the delta G naught of the reaction, so the delta G naught of the reaction is equal to delta summation of the delta G naught of the products minus summation of the delta G naught of reactants. So the delta G naught for the reaction will be equal to the sum of the delta G naught of carbon dioxide plus the delta G naught of water, delta G naught of 2 moles of water minus delta G naught of the methane plus delta G naught of the oxygen. Is the delta G naught for the carbon dioxide is minus 394.4 kilojoule. For water, it is equal to minus 237.2 kilojoule, and for the methane gas, it is equal to the value is given in table 16.3, which is minus 50.8 kilojoule. Putting the values, we will get that minus 394.4 plus 2 into minus 237.2 minus 50.8 kilojoule. So minus 394.4 plus 2 into 237.2, 2 into 237.2 is equal to 474.4 and plus 50.8 kilojoule. When we add the two values, so we will get minus 868.8 plus 50.8 kilojoule. We will get the value of delta G naught, which is minus 818 kilojoule. This is the value of delta G naught in kilojoule. If we change it into joule, we will multiply it with 1000. So the value will become minus 818,000 joule. Now to calculate the standard cell potential E naught, we will use the equation that delta G naught is equal to minus NF E naught. Rearranging this equation for E naught, we will get that E naught is equal to minus delta G naught divided by NF. Putting the values, we will get that E naught is equal to minus, where delta G naught is minus 818,000 joule divided by N, where N is the number of electron lost and gained. So we can see that in CH4 the carbon changed to carbon dioxide, where in CH4 its oxidation state is -4, while in carbon dioxide its oxidation state is +4. So there is the loss of 8 electrons, therefore N is equal to 8 mole of electrons. So N is equal to 8 mole of electrons, while F is Faraday's constant, which is 96,500 coulomb per mole of electrons. Calculating the value of E naught, we get the value of E naught is plus 4.238 joule per coulomb, or E naught is equal to 4.238 volt. This is the required potential for the given cell reaction. For a reaction in which zinc oxidizes into Zn2 plus, an aqueous solution, and where Eu3 plus, an aqueous solution, reduces to Eu2 plus an aqueous solution at platinum electrode. So in this reaction at anode, the zinc oxidizes into Zn2 plus, where it releases 2 electrons. The E oxidation for the zinc is 0.76 volt, where in the electrochemical series E reduction value for the zinc is minus 0.76 volt. To change the reduction value into oxidation, we will just change the sign. So the E oxidation for the zinc is 0.76 volt. On the other hand, at cathode, the reduction of the Eu3 plus ions to gain 2 electron changes into Eu2 plus ions. The E reduction value for this is to be determined, while the E naught of the cell is given, which is equal to 0.40 volt. As we know that E naught of the cell is equal to E naught of oxidation plus E naught of reduction. To determine E naught of reduction, which will be equal to E naught of the cell minus E naught of oxidation. So E naught of the cell is 0.40 volt, while E oxidation is 0.76 volt. Subtracting the values, we will get the E reduction for the Eu3 plus into Eu2 plus, which is equal to 0.36 volt minus 0.36 volt. So the E reduction value for the EU3 plus ion is minus 0.36 volt, which is the required solution to the given question. For a cell in which the cupric ion Cu2 plus react with the silver ion Ag and in the presence of bromide ion solution to form Cu and 2Ag Br, the E naught of the cell is given, which is 0.27 volt. In this reaction at cathode, the reduction of the copper ion take place into copper, where the E reduction for the copper ion in the electrochemical series is given 0.34 volt, while at anode the oxidation of two Ag plus 2 Br minus to form 2 Ag Br. So the E oxidation for this reaction we will have to determine. So as we know that E naught of the cell is equal to E oxidation plus E reduction of the two half cell. So E oxidation is equal to E naught of the cell minus E reduction. So E oxidation is equal to E naught of the cell is 0.27 volt minus E reduction is 0.34 volt. Subtracting the two values, so we will get E oxidation is equal to minus 0.07 volt. So the value for the Ag E oxidation is minus 0.07 volt. Or if we write the reaction in this form, that Ag Br to gain electron forming Ag and Br minus, then the electrode potential E reduction will be equal to 0.07 volt. Just changing the sign of this from E oxidation to change into E reduction, the value will be 0.07 volt. So this is the required solution to this answer, to this question. In order to compare the oxidizing strength of the different substances, for example, we have given bromine. When bromine gain 2 electrons, form 2 bromide ions, so the standard electrode potential, reduction potential for the reduction of the bromine is 1.09 volt. That is for MnO4 minus ion in the presence of 8 hydrogen ions to gain 5 electrons, form manganese from +7 oxidation state reduced to 2+ oxidation state, forming 4 water molecules. So the E reduction is for the manganese is 1.51 volt. On the other hand, for the SN 4+ to gain 2 electrons, form SN2+, the E reduction is 0.15 volt. If we arrange them in an order, so the E reduction for the manganese MnO4- is greater than for the E reduction of the bromine, which is greater than for the E reduction of SN4+. As we know that oxidizing agent is the agent which reduces itself but oxidizes other. So an oxidizing agent reduces itself but oxidizes other. Among the 3 ions given, the one which has high E0 reduction value will be stronger oxidizing agent. So MnO4- is strongest oxidizing agent, while SN4+ is weakest oxidizing agent. Because the MnO4 has the highest value of the standard reduction, that is 1.51.
So in this problem we are given with the standard potential for a galvanic cell, which is aluminium 3+, Cr3+, Cr galvanic cell, and we have to calculate the standard reduction potential for the Cr3+ Cr half cell, while we have to find out the standard reduction potential for the aluminium 3+ Al half cell reaction from the table. To calculate the standard reduction potential for Cr3+ Cr, let's first write down the reaction equation here. Aluminium metal reacting with Cr3+, and this will give us aluminium 3+ plus Cr, and we have to find out the oxidation and reduction half reaction here, and the oxidation reaction or the reaction in the anode will be from aluminium metal. So aluminium metal will convert to Al3 plus by releasing 3 of its electrons, and at the cathode the reduction will be chromium 3 plus will take up those 3 electrons to become chromium. So now we know our oxidation and reduction half reaction. From the formula we can write down the standard cell potential as standard oxidation potential plus standard reduction potential. The standard oxidation potential here will be oxidation potential of this reaction, and if we look up at the table as suggested, we'll see that the oxidation potential for this reaction is 1.66 volt, and we are given the standard cell potential as 0.92 volt. So if we just plug in the values in the equation, we'll get 0.92 volt equal to 1.66 volt plus the standard reduction potential, and from here we will get the standard reduction potential for this reaction in the galvanic cell, and it will give us minus 0.74 volt.
In order to find that which species is strong reducing agent, so to find that which one is the strong reducing agent among the aluminum 3 plus, which gain 3 electron to form Al, aluminum solid, where the E reduction value is minus 1.66 volt. For lead Pb2 plus, to gain 2 electron forming lead, the E reduction value is minus 0.13 volt. Similarly, for the ferrous ion, to form iron, the E reduction value is minus 0.45 volt. So if we arrange them in order, so Al3 plus has the greatest value, then Fe2 plus is greater than the Pb2 plus. We have arranged, this is the highest value for the aluminum, while the lowest value for the lead iron is in the middle. As we know that a reducing agent is the one which oxidizes itself but reduces other. So among the three, the one which has highest among the three which has the lowest E reduction value is the strongest reducing agent. So if we look at to them, aluminium has minus 1.66 volt, so it is the lowest value, while the iron has minus 0.45 volt and lead has 0.13 volt. As the sign is negative, so the aluminium has the lowest reduction value, therefore it is the strongest reducing agent. This is the strongest reducing agent, while the lead has the largest value, therefore it is weakest reducing agent. We can also change the E reduction value for aluminium, iron and lead into oxidation value. So for the aluminium it will be 1.66 volt, for the iron it will be 0.45 volt, just changing the sign, and for lead it is 0.13 volt. It means aluminium has greater potential for the oxidation, so it will have stronger ability for the reduction of the other agent. Among the following, to find that which one is the strongest oxidizing agent, we will compare their electrode potential values, reduction potential values. So iodine gain electron to form iodide ion. Its reduction value is 0.54 volt. On the other hand, iron Fe2 plus, to form iron it has E reduction value minus 0.45 volt. The chromate diachromate Cr2O7 2 minus diachromate ion in the presence of 14 hydrogen ion gain 6 electron, where the chromium from +6 oxidation state change into Cr3 plus 3 oxidation state and form 7 water molecule. So the E reduction for this reaction is 1.36 volt. Now if we arrange them in an order, so we can find that the E reduction value for the Cr2O7 2 minus is greater than for the E reduction value of iodine, which is greater than for the E reduction value of iron Fe, as the value for the diachromate ion is 1.36 volt, for iodine it is 0.54 volt, and for iron it is minus 0.45 volt. As we know that oxidizing agent is the one which reduces itself but oxidizes other. Among the three, the one which has high value the one which has a highest value for E reduction is strongest oxidizing agent. So chromate ion has the highest reduction value, it is therefore strongest oxidizing agent. While the iron is the weakest oxidizing agent. In order to find that which one is the strongest reducing agent among the following, so we will compare their electrode reduction potentials. So for the iron, Fe2 plus, when it oxidizes and form Fe3 plus to release an electron, its electrode potential is E0 reduction value for this is minus 0.77 volt. For the 10 SN2 plus to oxidizes into SN4 plus and release 2 electron, the E reduction value for this is minus 0.15 volt. And for the iodide ion to oxidizes into iodine and release the electron, its E naught reduction value is plus 0.54 volt. Now a reducing agent is the one which oxidizes itself and reduces other substances. So the one which has highest value for E0 reduction is a weak reducing agent. So among the three, the highest value is for the iodide ion, then for the SN2 plus, and then for the Fe2 plus. As the value for the iodide ion is 0.54 volt plus 0.54 volt. For the 10 it is minus 0.15 volt, and for the iron it is minus 0.77 volt. So the iron has the lowest value for the E reduction, therefore it is strongest oxidizing reducing agent. The iodine has the highest value for the E reduction, therefore it is the weakest reducing agent. 3 half-cells reactions are given. Number 1, that CO2 plus ion, cobalt 2 plus ion gain 2 electrons, forming cobalt where the E naught reduction for this is minus 0.28 volt. A second one reaction is for the iodine, which gain electrons, forming 2 iodide ion. So the E naught reduction value for this is 0.54 volt. And a third one is the copper ion, Cu2 plus, when gain electron, forming Cu. So the E reduction value, so the E naught reduction for the copper is 0.34 volt. So among these three, which two should be combined to gain a maximum voltage of the cell potential? So combining equation 1 and 2, we will get the maximum potential, that is when CO2 plus we will write the equation first in the reverse direction. So cobalt oxidizes into CO2 plus, release 2 electron. So instead of E reduction, we will write E oxidation for the cobalt, and the sign of the value will be changed, so it will be 0.28 volt. For iodine, we will write the same reaction. Iodine gain 2 electron, forming 2 iodide ions. So the E reduction value for this is 0.54 volt. Combining the two equations, that is cobalt react with the iodine, forming cobalt 2 plus and 2 iodide ion, where E naught of the cell is E oxidation plus E reduction. Combining the two values, we will get 0.82 volt. Now we have to determine the delta G naught for the value. So as we know that delta G naught is equal to minus N F E naught. So N is the loss and gain of electron. So the loss and gain of electron is 2. N is equal to 2 mole of electrons, where F is Faraday constant and it is equal to 96,500 coulomb per mole of electron. And we can also write the E cell as 0.82. Instead of volt, we can write joule per coulomb, because 1 volt is equal to 1 joule per coulomb. So putting the values minus 2 mole of electrons into 96,500 coulomb per mole of electrons, multiply by 0.82 joule per coulomb, cancelling the mole of electron with mole and coulomb with the coulomb, multiplying the value, we get the value minus 158,260 joule. To determine the value in kilojoule, we will divide it by 1000. So we get the value minus 158.26 kilojoule. This is the value of delta G naught. This is the required solution to this question. Among the three equations, that is number 1, when cobalt two plus ion gain 2 electron and reduce to cobalt, the E naught reduction for this equation is minus 0.28 volt. And the second case, when iodine combine gain 2 electrons forming 2 iodide ions, so the E reduction for this is 0.54 volt, while in case of cupric ion, to reduce into copper gaining 2 electron, the E naught reduction value for this is 0.34 volt. Among these two, we will combine which of the two to gain the least potential. So combining equation 2 and 3, we will get the least potential. So in this case, the copper has lowest reduction potential value, then iodine. So we will write the copper reaction in the reverse direction. So the copper oxidizes into Cu2 plus to release 2 electron, and we will change the E reduction value into E oxidation. Will change the sign, so it will be minus 0.34 volt. For the iodine, we will write the equation as such as it is. So the iodine gain electron forming 2 iodide ions. Its E reduction value is plus 0.54 volt. Combining the two equations, we can write that copper react with iodine forming copper 2 plus and 2 iodide ion, where the E naught of the cell is adding the above two values. So adding the above two values, we will get the E naught of the cell 0.2 volt. Now to find out the delta G naught for the reaction, which is equal to minus NF E naught of the cell, as we know N is the number of electron lost and gain, which is 2 mole of electrons. F is Faraday constant, which is 96,500 coulomb per mole of electrons, and instead of E naught 0.2 volt, we can write 0.2 joule per coulomb, as we know that 1 volt is equal to 1 joule per coulomb. So delta G naught is equal to minus 2 mole of electrons multiplied by 96,500 coulomb per mole of electron into E naught is equal to 0.2 joule per coulomb. Cutting the unit of coulomb with coulomb and mole of electrons with mole of electrons, multiplying the values, we will get delta G naught is equal to minus 38600 joule. To change it into kilojoule, we will divide it by 1000. So delta G naught is equal to minus 38.6 kilojoule. This is the required answer to the question. To calculate the standard cell potential E naught of the cell, and delta G naught for the cell, a reaction is given in which cadmium oxidizes into Cd2 plus, releasing 2 electrons. So the E naught oxidation for the cadmium is minus 0.40 volt. As in the electrochemical series, the value is given E reduction, which is plus 0.040 volt. But to write it in the reverse direction, we will write E oxidation, so we will change the value. So now the value is minus 0.40 volt. For the 10 SN2 plus, to gain the 2 electrons to form SN0, the E naught reduction is minus 0.14 volt. To calculate the E cell, we will combining the two reactions, so we can write that Cd plus Sn2 plus form Cd2 plus Sn, where E naught of the cell is the sum of the E oxidation plus E reduction, which is minus 0.54 volt. When E naught has negative value, then delta G naught will have positive value, and in this case the reaction is non-spontaneous. To calculate delta G naught for the reaction, so delta G naught is equal to minus NF E naught, as N is the number of electrons lost and gained, so that is 2 mole of electrons. F is Faraday constant, which is 96,500 coulomb per mole of electrons, and we can also write E naught of the cell, that is minus 0.54 volt. Instead of volt, we can write joule per coulomb, as 1 volt is equal to 1 joule per coulomb. So putting the value minus 2 into 2 mole of electron into 96,500 coulomb per mole of electrons, multiply by minus 0.54 joule per coulomb. So we can cancel the coulomb unit with coulomb and moles to mole. Multiplying the negative signs, we will get the positive sign, and multiplying all the values, we will get delta G naught, that is equal to 104,220 joule. To change it into kilojoule, we will divide it by 1000, so we will get delta G naught for this reaction, that is plus 104.22 kilojoule. This is the required solution to the part A of this question. Now in case of part B, where 2 aluminium react with the 3 Cd2 plus to form 2 Al3 plus 3 cadmium. So in this reaction, aluminium oxidizes into Al3 plus, releasing 2 aluminium, release a total of 6 electron, where the E naught oxidation for the aluminium is 1.66 volt. As the sign given in the electrochemical series is negative, that is the reduction potential, so we change it into oxidation, So we will write it minus 1.6 plus 1.66 volt. In case of the cadmium, the 3 CD plus gain 6 electrons from 3 cadmiums. Here its E reduction is minus 0.40 volt. Combining both the equation, we can write 2Al plus 3 CD2 plus form 2Al3 plus 3 CD, zero oxidation state. E naught of the cell is the sum of the E naught oxidation plus E naught of reduction. So combining the two values, adding the two values, we will get it is equal to 1.26 volt. Now to find delta G naught, it is equal to minus NF E naught, as E naught is plus 1.26, so delta G naught value will be negative and the reaction will be spontaneous. So in this reaction, N is the number of electrons lost and gain, which is 6 mole of electrons. F is Faraday constant, which is 96,500 coulomb per mole of electrons, while we can write the E naught as 1.26 instead of volt. We can write joule per coulomb, as we know 1 volt is equal to 1 joule per coulomb. So delta G naught is equal to minus 6 and 2, and that is 6 moles of electrons. Where F is 96,500 coulomb per mole of electrons, and to E naught is 1.26 joule per coulomb. We can cross the coulomb unit and the mole of electron, and multiplying all the values we get minus 729,540 joule. To change it into kilojoule, we will divide it by 1000. So delta G naught is minus 729.54 kilojoule, which is the required solution to this question. In the third part, at part C, the diachromate ion Cr2O7 2- react with the 6 ferrous ion in the aqueous solution in the presence of 14 hydrogen ions to form 2Cr3 plus. Here chromium has been reduced from +6 to +3 oxidation state, and iron has been oxidized to ferric ion. 7 water molecules form in the reaction, and this the iron ferrous ion oxidizes to ferric ion, releasing a total of 6 electrons. So the E oxidation for this reaction is minus 0.77 volt, while the chromate ion Cr2O7 in the presence of hydrogen ions gain 6 electrons, forming 2 Cr3 plus ions and 7 water molecules. So the E reduction for this reaction is plus 1.36 volt. Combining the two equations, we can write that 6Fe2 plus react with the Cr2O7 2 minus and 14 hydrogen ions also take part in the reaction, forming 2 Cr3 plus 6 Fe3 plus 7 H2O, where E naught of the cell is the sum of the E oxidation plus E reduction. So adding the two values, we get the answer 0.59 volt. This is the E naught of the cell. Delta G naught of the cell will be equal to minus NF E naught of the cell, where N is the number of electrons, which is 6 moles of electrons lost or gained in this reaction. F is Faraday constant, which is 96,500 coulomb per mole of electrons, and instead of E naught 0.59 volt, we can write joule per coulomb is 1 volt is equal to 1 joule per coulomb. So putting the values, minus 6 mole of electrons into 96,500 coulomb per mole of electrons into 0.59 joule per coulomb, we can cross the coulomb unit and mole of electrons. So delta G naught multiplying all the values will be equal to minus 341,610 joule. To change it into kilojoule, we will divide it by 1000. So minus 341.60610 kilojoule is the value of delta G naught, which is the required answer to this question. For a reaction in which the copper ion react with the chromium to form copper and chromium ion, as the chromium oxidizes into Cr3 plus ions, releasing a total of 6 electrons. E oxidation for this reaction is 0.41 volt. On the other hand, the copper reduces, gaining electrons into copper, where the E reduction for the copper is 0.34 volt. Combining the two equations to write the E cell, so 2Cr plus 3Cu2 plus, we can cross the electron on either side. So 2Cr3 plus 3Cu, where E naught of the cell is the sum of the E oxidation plus E reduction, which is equal to 0.76 volt, 0.75 volt. Now to calculate delta G naught for the reaction, which is equal to minus NF E naught, is N is 6 moles of electrons in this reaction, while F is Faraday constant, which is 96,500 coulomb per mole of electrons, and E naught is 0.75. Instead of volt, we will write joule per coulomb is 1 volt is equal to 1 joule per coulomb. Putting the values, we will get minus 6 mole of electrons and to 96,500 coulomb per mole of electrons, and E naught is 0.75 joule per coulomb. We can cross the units above and below, and multiplying the values we will get delta G naught is equal to minus 434250 joule. To change it into kilojoule, we will divide it by 1000, so it will be equal to minus 434.25 kilojoule. This is delta G naught of the reaction, where E naught, as we have calculated above, is 0.75 volt. This is the required solution to this part of the question. Now to calculate the same values for the reaction in which the lead react with hydrogen ions forming Pb2 plus and a hydrogen gas. In this reaction, lead is oxidizes into Pb2 plus, releasing a total of 2 moles of electron. E oxidation for the lead is 0.13 volt, while the hydrogen ion gain the electrons forming hydrogen gas. As we know, E oxidation or reduction for the hydrogen is 0 volt. Combining the two equations, we can write that lead react with the two hydrogen ions. We can cross the electron on both sides, form Pb2 plus and hydrogen gas, while E naught of the cell is equal to 0.13 volt, which is the sum of E oxidation and E reduction of this reaction. To find delta G naught, which is equal to minus NF E naught, as N is the number of electrons, which is 2 moles of electrons lost and gain in this reaction. F is Faraday constant, which is 96,500 coulomb per mole of electrons, and E naught is 0.13 instead of volt if we write joule per coulomb, because 1 volt is 1 joule per coulomb. So delta G naught is minus 2 mole of electrons into 96,500 coulomb per mole of electron into 0.13 joule per coulombs. We can cross the units above and below. Delta G naught will be equal to minus 25090 joule. If we divide this by 1000, so we will get minus 25.09 kilojoule. This is the value of delta G naught, as E naught of the reaction is 0.13 volt, which we have calculated above. This is the required solution of this part of the questions. Now to calculate for the third part, that is Cl2 react with SN2 plus to form SN4 plus plus 2Cl minus. In this reaction, 10 2 plus ion oxidizes into 10 4 plus ions, releasing 2 electrons. The E oxidation for this reaction is minus 0.15 volt, while on the other hand the chlorine is reduced, gaining the electrons lost by the 10 So the chlorine molecule gain the electrons, form two chloride ions, where E reduction for the chlorine is 1.36 volt. Combining both the equations, we will get that Sn2 plus Cl2, crossing the electrons on either side, form Sn4 plus 2 chloride ions, where E naught of the cell is the sum of the E oxidation plus E reduction. So this is equal to 1.21 volt. Now to find the delta G naught for the reaction, which is equal to minus NF E naught, as N in this case is 2 mole of electrons lost and gained in the balanced reaction. F is Faraday constant, which is 96,500 coulomb per mole of electrons, and E naught of the cell, instead of volt 1.2 volt, we can write in joule per coulomb, as 1 volt is equal to 1 joule per coulomb. So we can putting the values in the equation, minus 2 mole of electron into 96,500 coulomb per mole of electrons, and E naught is 1.21 joule per coulomb. Crossing the units above and below, we will get delta G naught for this reaction, which is equal to minus 233,530 joule. To change into kilojoule, dividing by 1000, so we will get minus 233.53 kilojoule. This is the value for the delta G naught, where E naught of the cell is 1.21 volt, which we have calculated above. This is the required solution to this part of the question. For a reaction in which the ferrous ion react with the lead ion, both in the aqueous solution, forming two ferric ions in the aqueous solution, and lead is reduced to the solid state. So in this reaction, the iron Fe2 plus oxidizes into 2Fe3 plus. It release 2 electrons. E oxidation for this reaction is minus 0.77 volt, as the value given in the electrochemical series is positive, which is E reduction value. To change into E oxidation, we will write the reaction in the reverse direction and the sign will be opposite. On the other hand, the lead ion gain 2 electrons to form Pb, so the E reduction for this reaction is minus 0.13 volt. Combining both the equations, we will write that 2Fe2 plus Pb2 plus, crossing the electrons on both sides, form 2Fe3 plus Pb, and E naught of the cell is equal to the sum of E oxidation and E reduction. So the sum of the two values is 0.90 volt with a negative sign. Now to find the delta G naught for this reaction, which is equal to minus NF E naught, as N is 2 moles of electrons in this reaction, F is Faraday constant, which is 96,500 coulomb per mole of electrons, and E naught of the cell we can write minus 0.90 instead of volt. We can write joule per coulomb as 1 volt is equal to 1 joule per coulomb. So putting the values in the equation, delta G naught is equal to minus 2 mole of electrons and to 96,500 coulomb per mole of electrons, and to E naught is minus 0.90 joule per coulomb. We can cross these units above and below, multiplying the values, so we will get delta G naught, which is equal to plus 173,700 joule. To change it into kilojoule, we will divide it by 1000, so it will be equal to plus 173.7 kilojoule. This is the value of delta G naught. As delta G naught has positive value and E naught of the cell has negative value, these are the conditions for the non-spontaneous reaction. So the reaction is non-spontaneous in this case. This is the required solution to this part of the question. Now to find for another part of the question where magnesium react with the nickel to form magnesium ion and nickel solid state. In this reaction, magnesium oxidizes into Mg2+, releasing 2 electrons. So E oxidation for the magnesium is 2.37 volt, as the value in electrochemical series is minus, and the reaction we have written in the reverse direction, where we have changed the E reduction to E oxidation, so we have changed the sign from the minus to positive. On the other hand, nickel ion reduces from nickel. The E reduction for the nickel is minus 0.26 volt. Combining the both equations, we can write that magnesium react with nickel 2+, crossing the electrons on opposite side, form magnesium 2+ plus nickel. So E naught of the cell is the sum of the E oxidation plus E reduction, which is equal to 2.11 volt. To find the delta G naught for the reaction, which is equal to minus NF E naught, as N is equal to 2 moles of electron. F is Faraday's constant, which is 96,500 coulomb per mole of electrons, and E naught, instead of volt we can write 2.11 joule per coulomb, as we know 1 volt is equal to 1 joule per coulomb. So putting the values, we can write delta G naught is equal to minus, where N is equal to 2 mole of electrons. F is Faraday's constant, which is 96,500 coulomb per mole of electrons, and E naught is equal to 2.11 joule per coulomb. Crossing these units, we can write delta G naught is equal to minus 407,230 joule, and to change it into kilojoule, dividing by 1000 minus 407.23 kilojoule. As delta G naught has negative value and E naught has positive value, these are the condition for the spontaneous reaction. So the reaction is spontaneous. This is the solution to this part of the question. For a reaction in which the silver ions react with the manganese 2 plus ion, for water molecules also take part in this reaction to form reduce silver into Ag solid form, and Mn2 plus is oxidized to MnO4 minus, where the oxidation state of manganese is +7, so it loses 5 electrons, where the silver gain the 5 electrons, and 8 hydrogen ions in form in the reaction. So in this at anode where oxidation take place, so Mn2 plus in the presence of 4 water molecule form MnO4 minus plus 8 H plus. The E oxidation of this reaction is minus 1.51 volt, where at cathode where reduction take place, so the 5 silver ions, here 5 electrons are also lost in the oxidation of manganese, so the 5 electrons are gained by the silver, forming silver metal. The E reduction for this reaction is plus 0.80 volt. Combining the two equations, so we will get E naught of the cell, which is equal to E oxidation plus E reduction. Adding the two values, we will get minus 0.71 volt, which is the voltage of the cell. To calculate delta G naught, which is equal to minus N F E naught, so N is the number of electrons, which is 5 moles of electron. F is Faraday constant, which is 96,500 coulomb per mole of electrons, and we can also write E reduction, E cell, as minus 0.71 joule per coulomb, as we know 1 volt is 1 joule per coulomb. So putting the values minus 5 into 96,500 coulomb per mole of electrons, this is 5 moles of electrons, and E naught is minus 0.71 joule per coulomb, cutting the coulomb with coulomb and mole of electrons with mole of electrons. Multiplying both the value, we will multiply the negative sign, so we will get plus, and the answer is 361.875 joule, or plus, to change it into kilojoule, we will divide it by 1000, that is equal to plus 361.875 kilojoule. As delta G naught is positive and E naught of the cell is negative value, in such case when G naught is positive, E naught is negative, the reaction is non-spontaneous. So this reaction is non-spontaneous reaction. This is part A of the question. Now moving toward the part B. In part B of the question, we have given that 2H2O2 aqueous form O2 gas and 2H2O liquid. So we can also write that H2O2 form 2 hydrogen ions, 2 electrons and an oxygen. The E reaction for this reaction is minus 0.70 volt, while the H2O2 to gain the 2 hydrogen ions and the 2 electrons form 2H2O. So the E reduction for this reaction is 1.78 volt. Adding both equations, we can write that 2H2O2, we can cross the hydrogen ions and electron on both sides, form O2 and 2H2O. Adding the two values, we can write that E cell is equal to 1.08 volt, adding the above two values. Now to find the delta G naught for this reaction, delta G naught is equal to minus NF E naught, where N is the number of electrons, which is 2 moles of electrons. F is Faraday constant, 96,500 coulomb per mole of electrons, and E naught we can also write 1.08 joule per coulomb, as 1 volt is equal to 1 joule per coulomb. Putting the values minus 2 into 96,500 coulomb per mole of electrons into 1.08 joule per coulomb, we can cross the coulomb with coulomb and mole of electrons with mole of electrons above and below. Multiplying both the values, it is equal to minus 208,440 joule. To change it into kilojoule, we will get minus 208.44 kilojoule. This is delta G naught. As delta G naught for the reaction has negative value, while E naught for the reaction has positive value, in such case the reaction is spontaneous. A spontaneous reaction is the one which has positive value for the E naught and negative value for the delta G naught. This is the required solution to the question. To know where the oxidation of SN2 plus aqueous by bromine aqueous is spontaneous or not. So in this reaction at anode, SN2 plus oxidizes into SN4 plus, releasing 2 electrons. So the E oxidation for this reaction is minus 0.15 volt, as the E reduction value is plus 0.15. To write the reaction in the reverse direction and to change the E reduction value to E oxidation, we will change the sign. So we have put the sign minus 0.15 volt. At cathode, reduction of the bromine will take place, which will gain the 2 electrons and will form the 2 bromides ion. So the E reduction for the bromine is plus 1.09 volt. To find the E cell, we will add the two equation SN2 plus plus Br2. We can cross the electrons, so form SN4 plus and 2 Br minus, where E naught of the cell is the sum of the above E oxidation and E reduction values, which is equal to 0.94 volt. Now to calculate delta G naught, which is equal to minus NF E naught, as N is the number of electrons last end gain, which is equal to 2 moles of electrons. F is Faraday constant, which is 96,500 coulomb per mole of electrons, and E cell we can write 0.94 volt instead of volt. We can write joule per coulomb, as 1 volt is equal to 1 joule per coulomb. Putting the values in the equation, we will get minus 2 mole of electrons and to 96,500 coulomb per mole of electrons, multiply by 0.94 joule per coulomb. We can cross the coulomb and mole of electrons. Multiplying the values, we will get minus 181,420 joule. To change it into kilojoule, we will divide this value by 1000. So we will get delta G naught minus 181.42 kilojoule. As delta G naught has negative value while E naught has positive value, therefore the reaction is spontaneous. This is the required solution to this question. To find where the reduction of nickel 2 plus ion is by the SN2 plus ion is spontaneous or not, we can write that SN2 plus will oxidizes into SN4 plus and will release 2 electrons. So the oxidation potential for this reaction is minus 0.15 volt, where Ni2 plus will gain 2 electron to change into nickel. So the E reduction for the nickel is also minus 0.26 volt. Combining both equations, so SN2 2 plus react with Ni2 plus to form SN4 plus and nickel 0 oxidation state. E of the cell is equal to E oxidation plus E reduction. Adding the above values, we will get minus 0.41 volt. Now to find out delta G naught for the reaction, which is equal to minus NF E naught, where N is the number of electrons, which is 2 moles of electrons, F is Faraday constant, which is 96,500 coulomb per mole of electrons, and E of the cell is minus 0.41 joule per coulomb, as 1 volt is 1 joule per coulomb. Putting the values, we will get minus 2 mole of electrons into 96,500 coulomb per mole of electrons, and to E naught is minus 0.41 joule per coulomb. We can cross the units. We will get that it is equal to plus 79130 joule. To change into kilojoule, dividing by 1000, so we will get plus 79.13 kilojoule. This is delta G naught for this. As delta G naught has positive value and E naught has negative value, this is the case for the non-spontaneous reaction. So the reaction is non-spontaneous. In the third case, to find where the reduction of iodine by H2SO3 is spontaneous or not. So in this reaction, the oxidation of the H2SO3 in the presence of water take place to form SO4 2 minus plus 4 hydrogen ions and 4 electrons are released. E oxidation for this reaction is minus 0.17 volt, while on the other hand 2 iodine gain the 4 electrons, form 4 iodide ions, so the E reduction for the iodine is 0.54 volt. Now combining the two equations, we will get that H2SO3 at H2SO3 react with the iodine in the presence of water. We can cross the electrons on either side, so we will get that 4 iodide ions are formed, a sulfate ion and 4 hydrogen ions. E naught of the cell is equal to the sum of the E oxidation plus E reduction, so the sum of the two values is 0.37 volt. Now to find delta G naught, which is equal to minus NF E naught, where n is the number of electrons lost and gain. So the total number of electrons lost and gain in the reaction is 4 moles of electrons. F is Faraday constant, which is 96,500 coulomb per mole of electrons, and E naught in this case is 0.37 volts. So instead of what we can write joule per coulomb is 1 volt is equal to 1 joule per coulomb. Putting the values minus, where n is 4 moles of electron, F is Faraday constant 96,500 coulomb per mole of electrons, and E naught is 0.37 joule per coulomb. Cutting the units above and below, we can get that delta G naught is equal to minus delta G naught is equal to minus 142,820 joule. To change it into kilojoule, we will divide it by 1000, so minus 142.82 kilojoule. This is delta G naught. As delta G naught has a negative value while E naught has positive value, this is the case for spontaneous reaction. So the reaction is spontaneous reaction. This is the required solution to this question. Now in the case where the oxidation of silver by lead ion is spontaneous or not. So in this case the silver has been oxidizes into silver ion. Now the silver has been oxidizes into silver ion. Releasing 2 electrons. So the E oxidation for the silver is minus 0.80 volt, while the lead ion has been reduced into Pb. So the E reduction for this is equal to minus 0.13 volt. To write the net equation and to find the E cell, so 2Ag react with Pb, 2 plus we can cross the electron on either side, form 2Ag plus and a lead atom. E naught of the cell is equal to the E oxidation plus E reduction, which is equal to minus 0.93 volt. To find delta G naught for this reaction, which is equal to minus NF E naught, as N is the number of electrons, which is 2 moles of electron lost and gain in this reaction. F is Faraday constant, which is 96,500 coulomb per mole of electrons, and E naught of the cell, instead of volt we can write minus 0.93, instead of volt we can write joule per coulomb. Joule per coulomb is 1 volt is equal to 1 joule per coulomb. Putting the values over here and the delta G naught, we will get minus 2 molab electrons into 96,500 coulomb per molab electrons, into E naught is minus 0.93 joule per coulomb. Cutting the units above and below, so delta G naught is equal to plus, adding multiplying the negative sign, it will, so the sign will be positive, plus 179,490 joule, and to change it into kilojoule we will divide it by 1000, so delta G naught is equal to plus 179.49 kilojoule. As delta G naught has positive value while E naught of the cell is negative value, which is the condition for the non-spontaneous reaction. This is the required solution to this part of the question.
So in this problem we are asked to find out which one is the stronger oxidizing agent among chlorine and silver ion, and we have to find out which one is the stronger reducing agent among iron and magnesium. First we have to write down their half cell reactions for each of the oxidizing and reducing agent with their cell potential for that half reaction, and from there we will be able to say that which one is stronger oxidizing and which one is stronger reducing. So the half cell reaction for the chlorine will be one chlorine molecule will take up 2 electrons to give us 2 chloride ions, and the cell potential for this half cell, if we look at the table, it is 1.36 volt. And then if we write down the half cell reaction for the silver ion, and the half cell, the cell potential for this reaction is 0.80 volt. So as we know that the higher the cell potential for a reaction or a half cell, higher the chance that it will be a stronger oxidizing agent, because the higher the value of the cell potential, the higher the chance that a species will be reduced itself mean it will work as a stronger oxidizing agent. So from here, these two cell potential values, you can see that the cell potential for the chlorine half cell is higher than the cell potential for the silver ion half cell. So that means chlorine will be stronger oxidizing agent among these two. Now if we look at the half cell reaction and cell potential for the given reducing agents, so first one is iron 2 plus, plus 2 electrons. Iron 2 plus will take up 2 electrons to give us metallic iron, and the standard cell potential for this half cell is minus 0.45 volt, and for magnesium it is magnesium 2 plus plus 2 electron, and same as it will give us the neutral magnesium. And the cell potential for this reaction is minus 2.37 volt. So in case of the reducing agent, the thing will be just the opposite. The lower the value of the cell potential, the stronger the reducing agent. And here we can see that among these two cell potential values, magnesium has more negative value of cell potential. That means it has the least chance of being reduced itself. That means the highest chance of working or acting as a reducing agent. So the strength of magnesium ion as a reducing agent will be higher than the strength of Fe2 plus ion as a reducing agent.
For a reaction in which the reduction of Pp2 plus aqueous solution by nickel solid take place. So in this reaction, nickel will oxidize into nickel 2 plus, will release 2 electrons. So E oxidation for the nickel is 0.26 volt, while the reduction of the Pb2 plus to gain 2 electrons will form Pb. So the E reduction will be equal to 0 minus 0.13 volt. Combining the two equations, so nickel react with Pb2 plus, forming nickel 2 plus and Pb0. E naught of the cell is adding the E oxidation and E reduction, which is 0.13 volt. As E naught has positive value, so the reaction is spontaneous. For another cell in which oxidation of Aurium plus ion in aqueous solution by the Mn2 plus ion in aqueous solution take place. So in this reaction, Mn2 plus will gain electron and will reduce to Mn0. So the E reduction for the Mn is manganese is minus 1.18 volt, while Aurium plus ion oxidized to Au3 plus, releasing 2 electron. So the E reduction, the E oxidation for the Aurium is minus 1.40 volt. Combining the two equations, we can write them that Mn2 plus plus Au plus, crossing the electrons on both sides, form Au3 plus and manganese in zero oxidation state. E naught of the cell, adding the above two values, E oxidation and E reduction, we will get minus 2.59 volt. As the E cell is negative value, so the reaction is non-spontaneous. For a third type of cell in which reduction of iodine by manganese take place. So in this reaction, manganese oxidizes into Mn2 plus, releasing 2 electrons. So the E oxidation is equal to plus 1.18 volt, while iodine gain the 2 electrons forming 2 iodide ion. So the E reduction for the iodine is plus 0.54 volt. To combine both the equations, so manganese react with iodine, crossing the electrons on either side form Mn2 plus and 2 iodide ion. E naught of the cell is the sum of the E oxidation and E reduction, which is equal to 1.72 volt, as the value of the E naught of the cell is positive, so the reaction is spontaneous reaction. For the fourth type of cell, in which oxidation of iron (2 plus) by bromine is taken place. So in this reaction, the 2 ferrous ion oxidizes into the ferric ion, releasing 2 electrons. So the E oxidation for this reaction is minus 0.77 volt, while bromine gain the electrons, reduces to 2 bromide ions. The E reduction for the bromine is plus 1.09 volt. Adding the two equations, we can write that 2 ferrous ion react with the bromine molecule, crossing the electron on either side, form 2 ferric ion and 2 bromide ion. E naught of the cell is the sum of E oxidation and E reduction, which is equal to 0.32 volt, as the value of E naught cell is positive, so the reaction is spontaneous. If you like to find delta G naught, we can use the equation minus NF E naught, but there is no need for the determination of delta G naught. If somebody find out the delta G naught, so if the delta G naught has positive value, the reaction will be non-spontaneous. For those reactions where E naught is negative value, so delta G naught will be positive, and for the reactions for which delta G naught has negative value, reaction will be spontaneous. In this case, E naught will have positive value. To know that which of the following reaction will occur spontaneously, so we have given that when zinc is added to PbNO3, so where it will form zinc nitrate and lead will be reduced. So when zinc oxidizes, it forms Zn2 plus and release 2 electrons. The E oxidation for the zinc is 0.76 volt, while when lead is reduced to form lead 0, the E reduction for the lead is minus 0.13 volt. To combine the two equations, we get the cell potential E naught of the cell is 0.63 volt. As E naught value of the cell is positive, therefore the cell reaction will be spontaneous, and this reaction will occur in the forward direction. For another reaction in which ferrous sulfate is exposed to oxygen, so where the following reaction will take place or not. So when iron Fe2 plus oxidizes to Fe3 plus and release electrons, the E oxidation for the iron is 0.77 volt, minus 0.77 volt. While to balance the equation, we will multiply this equation with 4. Now for the oxygen, in the presence of hydrogen ion gain the electrons and form water molecule, the E reduction of this reaction is 1.23 volt. Combining the two equations, we will get the E naught of the cell, which is equal to E oxidation plus E reduction. So the sum of the two values is 0.46 volt. As again the E naught value for the reaction is positive, therefore the reaction is spontaneous and will take place in the forward direction. For another reaction in which when silver is added to nickel chloride solution, so will this reaction take place to form AgCl and to reduce nickel. In this reaction, when silver oxidizes to Ag plus 1 and release electron, so the E oxidation of the silver is minus 0.80 volt, while for the nickel, to reduce the reduction potential for the nickel is minus 0.26 volt. The oxidation potential for the silver is less than for the oxidation potential of the nickel, therefore silver cannot reduce Ag cannot reduce nickel 2 plus ion, therefore the reaction is non-spontaneous. On the other hand, adding the two values, we will get the E naught value, which will be negative. So when E naught is negative, the reaction will be non-spontaneous. So this reaction will not take place in the forward direction. For another reaction, in which hydrogen gas is bubbled, in cadmium nitrate solution. So when hydrogen gas is bubbled in the cadmium nitrate solution, So in this reaction, the cadmium 2 plus ion to gain electrons to form CD, the E naught reduction for the cadmium is minus 0.40 volt, while for the hydrogen gas to oxidize and form two hydrogen ions and electron, the E oxidation is 0 volt. So adding the two values, we will get E naught of the cell, which is minus 0.40 volt, as the E naught value of the cell is negative. Therefore the reaction is non-spontaneous, and this reaction will not take place in the forward direction. To know that which of the following reaction will occur spontaneously, so we have given that when zinc is added to PbNO3, so where it will form zinc nitrate and lead will be reduced. So when zinc oxidizes, it forms Zn2 plus and release 2 electron. The E oxidation for the zinc is 0.76 volt, while when lead is reduced to form lead 0, the E reduction for the lead is minus 0.13 volt. To combine the two equations, we get the cell potential. E naught of the cell is 0.63 volt, as E naught value of the cell is positive. Therefore the cell reaction will be spontaneous, and this reaction will occur in the forward direction. For another reaction in which ferrous sulfate is exposed to oxygen, so where the following reaction will take place or not. So when iron Fe2 plus oxidizes to Fe3 plus and release electrons, the E oxidation for the iron is 0.77 volt, minus 0.77 volt, while to balance the equation, we will multiply this equation with 4. Now for the oxygen, in the presence of hydrogen ion, gain the electrons and form water molecule, the E reduction of this reaction is 1.23 volt. Combining the two equations, we will get the E naught of the cell, which is equal to E oxidation plus E reduction. So the sum of the two values is 0.46 volt, as again the E naught value for the reaction is positive. Therefore the reaction is spontaneous and will take place in the forward direction. For another reaction in which when silver is added to nickel chloride solution, so will this reaction take place to form AgCl and to reduce nickel. In this reaction, when silver oxidizes to Ag plus 1 and release electron, so the E oxidation of the silver is minus 0.80 volt, while for the nickel, to reduce the reduction potential for the nickel is minus 0.26 volt. The oxidation potential for the silver is less than for the oxidation potential of the nickel. Therefore, silver cannot reduce, Ag cannot reduce nickel 2 plus ion. Therefore, the reaction is non-spontaneous. On the other hand, adding the two values, we will get the E naught value, which will be negative. So when E naught is negative, the reaction will be non-spontaneous. So this reaction will not take place in the forward direction. For another reaction, in which hydrogen gas is bubbled, in cadmium nitrate solution. So when hydrogen gas is bubbled in the cadmium nitrate solution, so in this reaction, the cadmium 2 plus ion to gain electrons to form Cd, the E naught reduction for the cadmium is minus 0.40 volt, while for the hydrogen gas to oxidize and form two hydrogen ions and electron, the E oxidation is 0 volt. So adding the two values, we will get E naught of the cell, which is minus 0.40 volt, as the E naught value of the cell is negative. Therefore, the reaction is non-spontaneous, and this reaction will not take place in the forward direction. For a reaction in which the silver ions react with the tin, forming silver and Sn2 plus, in this reaction the tin oxidizes into Sn2 plus, releasing 2 electrons. So E oxidation for the tin is 0.14 volt, while the silver Ag plus gain the electron released by the tin reduces to silver solid. Its E reduction is equal to 0.80 volt. Combining the two equations, we will get the E of the cell. So Sn plus 2 Ag plus, crossing electron on both sides, form Sn2 plus 2 Ag. Here E naught of the cell is equal to sum of E oxidation plus E reduction, so the sum of the both cell is 0.94 volt. Now to find E cell, non-standard cell potential is equal to E naught standard cell potential minus 0.0592 divided by n log of Q, as Q is the concentration of the ions on the product side divided by concentration of the ions on the reactant side. So Q is equal to, on the reactant side there is SN2 plus ions, while on the product side there is Ag plus, there are 2 moles, so we will write the moles in power. N is the number of electrons lost and gained, so here 2 moles of electrons are lost or gained. So putting the values for the Q and N, so we will get that E cell is equal to E naught cell, as we know, is equal to 0.94 volt minus 0.0592, instead of n we will write 2, where log of Q is equal to 10 2 plus concentration divided by Ag plus concentration square. As in this reaction we have given the SN2 plus concentration is equal to 0.2